Unmute your mics, now's a good time.
Okay, I think it'll be fine. So is Henrik talking with Dave at the telescope?
So there's some trouble at the RTF.
Oh boy.
The support under the primary mirror, they've put in a new. Oh, sorry, they're talking here. It's a new system, so anyway, I'll mute myself.
Okay. Okay, cool. Yeah, we should take the flats and darks and stuff, right?
Yeah, I'm doing it.
Perfect.
asked, can we be heard?
So.
Okay, fine. Okay, we can be heard.
Hello, everyone.
Hello, everyone. Good morning, at least from the UK.
Hi.
It's a lovely day out here. I hope everyone else is having some lovely weather. We are just currently sorting out some technical bits and bobs, but hopefully we'll be able to shortly show everyone our setting up of the instrument.
We are also waiting on some issues at the telescope itself, because if this kind of astronomy was easy, then everyone would do it. So right now, the engineers at IRTF in Hawaii are at the summit working on changing out some of the fixing for the primary mirror. So that was changed earlier in the day and needs to be rejigged a little bit. So that's going to put some kind of delay on our observations. We're not quite sure how much of a delay, but this is the constant life of an astronomer. You must always be very tranquil in the fact that something may change your observations at any moment. So what we're hoping is that that won't take too long and we can get to Jupiter fairly soon.
So I believe I've just shared our stream that we've got running at the moment, which here you'll see we've got the view of both of our, I suppose, instruments. Carl and Cartman are instruments in their own way, which is basically the visual guide on the left-hand side. And on the right-hand side, already right middle, we have Cartman, who is our spectrogram. On the very far right side, bottom right, we have kind of the sky view over IRTF, so that's essentially off in Hawaii. I believe the right-hand side of that image, we're actually seeing part of the Milky Way.
That's right.
I was having a look at that earlier. And then, yeah, we've got a little bit of a time lapse just above it of basically inside IRTF over, I think, about 2-3 hours. Just shows you basically kind of the quick rotations that they end up doing for telescope, or at least shutting down for a little bit as they changed over instruments.
So the one advantage for now of the fact that they're having to work on the telescope is that you get to see the lights on inside the dome, which doesn't happen very often during the night. And you can see a really good view of the inside of IRTF, which is a 3-meter telescope. So that the diameter of the mirror is 3 meters and it's housed inside that big cream colored framework, which is what they're working on right now. The Milky Way comes out really clearly tonight as you look at the bottom right, the sky view. We do have some clouds around, but they're intermittent, so we're hoping that that won't affect our observations too much. There's a lot of complex stuff going on in the main view that you can see. Obviously, the guider is not doing anything right now. We're not guiding on anything on the sky, but in order to understand all the data that we take and be able to properly analyze it, we have to understand a lot about what the instrument does. And so in order to do that, we have a whole slew of observations of effectively of nothing. We're observing a lot of nothing in order to understand what the instrument sees when it's not looking at anything, so we can subtract all of that out from the observations when we do see things on the night sky. So you can see a very colorful picture inside this Cartman view. That is the spectra over many, many wavelengths split up, basically like a rainbow, but it's a double rainbow. What does it mean? It means that we're spreading out in both directions the wavelength. So there's a lot of wavelength in the up and down direction, and a much more finely spread wavelengths in the left and right direction. And you can see that the instrument has a very different response at different wavelengths. So this is basically just a lamp that we put in that's supposed to be completely uniform, and the instrument should just have a completely boring response to this, and it should show us just completely similar light across all of these wavelengths. But it's not doing that because there is a change in response depending on how the light is falling on the instrument itself. So by putting in a really boring lamp that doesn't show you anything, we can look at the fact that actually it's showing us quite a lot that we don't want to see, all of these variations. And so when we take data on the planet itself, this same variation will be in those data as well. So we can basically subtract this out by taking this data. So this is some of the early data that we've taken. And something else that we also do is basically take data with absolutely no illumination at all. And that's called taking darks. And you take darks basically to see what the instrument sees if there is no light, because again, that's going to come in whenever we take observations. So in order to get really nice, clean data on the planet, we have to do a whole range of these calibrations in order to be absolutely exact in the kind of measurements that we're getting at the end. So that's what we've been doing. We can do that while they're working on the telescope because the instrument is its own beast. It shuts down. There's a shutter that closes and it's basically sealed off from the dome. There's no light that gets in until we open that shutter up. And you can see maybe down in the bottom right, it's very small, but there's a little icon which is like a light bulb. That's the arc, the light that we use to calibrate with, but there's also information there about the fact that the window cover is shut. So our windows are shut, the instrument's sealed off. So even as they work in the dome, we're able to take very exact science data. We've set up all of the settings that we want for the night for all of our instrumentation. So we've put in all of the different settings that we want to use. So we're basically ready to go. And as soon as we've finished working, or as soon as the telescope have finished working through fixing the problems that have come up through the night, we'll get back to a position where we can start going onto the night sky. The very first thing we're going to do is focus. Just like if you're taking pictures outside, you want a clear and crisp picture of the sky. So we're going to go to a star. Stars are great for planetary science because they're really boring. Not all stars are really boring, but we pick particularly boring stars. Stars where we know everything we can know about those places. And so we can use those to make as crisp a picture as possible. We can also use those to understand how much light is coming into the instrument. Again, another form of calibration. So the first thing we'll do tonight is we'll have the telescope operator go to a star. They have an automated process that looks at images of the star and they change the focus until it becomes as crisp as possible. There's some shortcuts there that they know the kind of focus that they need. But once they've done that, we'll know that we're very crisp on the sky. Then we'll move straight to Jupiter and we'll start positioning up on Jupiter. Hopefully we'll be able to see the shadow of Ganymede on the disk of the planet, and we'll position our instrumentation over that and start taking data. So that's what we're going to do in the next, hopefully, half an hour. We will see whether that comes out. As always, you have to take a leap of faith when you try and do observing at a giant telescope like this. The process of getting to this point is quite long and laborious, but you have to forget all of that work that you've put in when you get to the telescope, because 1,000 things can go wrong, and often do. So you have to be very prosaic about how you feel about these observations that up until today have been incredibly important to you, because letting go of time on the telescope is one of the hardest things to do. But if you can't do that, you'll never make it as an astronomer, because we have to do it all the time. There will always be other opportunities, almost always, for observations that we take. In a very few occasions, there is no second chance, but next year, if we have to, we can always come back. Ganymede has been orbiting Jupiter for 4 billion years. It can wait another year if it needs to. So we hope that we will not have to do that, but there's always another chance. So that's what we're doing right now. It looks like our calibrations are finished, so we are just waiting for the nod from the telescope that everything is fixed, and then we can get on with doing some actual astronomy.
just noticed something on the IRTF time lapse. You can actually see a person on the telescope, on the base of the telescope. It gives you right in the beginning.
Oh, yeah.
It gives you a sense of scale of how large this telescope is.
I think we have a quick question from John Morel, who asks, what time does the shadow of Ganymede cross Jupiter today?
So the shadow of Ganymede is, Ganymede is approaching the disk of Jupiter right now. It's about to reach the face of Jupiter. The direction of the sun is slightly, as we look up at the night sky, it's slightly to the right of us. So the sun's slightly to the right. The shadow on the face of Jupiter is slightly to the left. So it's likely to fall onto the limb. It's going to move into a frame onto the disk of Jupiter about 11:30 UK time. So in about 15 minutes. And then it will continue as Ganymede moves across the face of Jupiter. And Ganymede is moving across the face of Jupiter at almost the same rate as Jupiter is rotating. So it's about half a day on Jupiter, and Jupiter has a very fast rotation rate compared to Earth. It rotates a full rotation every 10 hours or so. So it rotates for about 5 hours. So we're hoping that basically for the entire time that we're observing today on Jupiter, until Jupiter sets, we'll have a view of the shadow on the disk of Jupiter. So our event with the RAS is timed basically for the time that we're going to be able to see Jupiter in the night sky. Jupiter is very high in the night sky in Hawaii right now. In the UK, it's somewhere down below us. We can't see it because the sun is up and the Earth is in the way. But fortunately, we can look out of telescopes on various places around the world at any time. So right now, it should be coming up and we should be able to see not only Jupiter, hopefully the Great Red Spot on Jupiter, but also the moon Ganymede, which will be so bright that we won't really see any details or features on it. It won't be like some of the Hubble observations we've seen, where beautiful, crisp images of the surface of Ganymede. To us, Ganymede is going to be so bright that it's going to be super illuminated, and all we'll see is something that looks like a very fat star. But then hopefully the light that is reflecting back off of us from the surface of Ganymede is not falling onto the disk of Jupiter. And so Jupiter itself will have a dark spot on it. And that should last for about 4 hours or so, I think.
Awesome.
So we've got another quick question from Marcus, who asks to explain why the focus of the telescope needs changing. Is it dependent on the orientation of the instrument rather than the distance of the object?
So it's partly the distance between the telescope and the instrument itself. So each instrument is going to have a different focal point, but these are incredibly fine scale observations. So it actually also depends mostly on the temperature inside the dome, because as the temperature changes inside the dome, so each day there will be a slightly different atmospheric temperature, and that changes your focal, both because the instrument and the telescope itself is flexing differently, and also the way the atmosphere is affecting the light coming through. So obviously the distance to the object is fairly insignificant. We're effectively looking into infinity for any astronomical object that we're looking at. But it's the back end that is the really important aspect of that. And we're looking with such narrow variability so that focus can shift if there's a very strong change in temperature. So sometimes if the weather conditions are pretty unstable on a night, you will actually focus multiple times in a night. But one of the reasons we love observing in Hawaii so much is it's one of the more stable places in the world in terms of temperature. generally speaking, it's very calm in terms of the weather conditions. So it allows you to have a much more stable temperature change. And so there is actually automated processes within the focusing system that allow you to adjust for temperature, but they're not incredibly exact. So it is always worth refocusing each night to be sure that you are as exact as you can be.
Got another question whilst we're making our way towards about 20 past, if I remember correctly, is when we're introducing.
Emma, do you want to try and pull up that view of IRTF larger so that we can see the telescope in a bit more detail?
Yeah, I can sort that.
Because
There
then we might be able to see people moving around. I can see them, but I can understand why people are struggling to see it because it's quite small.
I've got it to take up the whole screen.
Perfect.
Oh.
So hopefully now the orange part of the telescope is the frame mount that holds the secondary mirror. And below that, and also inside of that is at the bottom in the large orange section is where the primary mirror is held. So the light comes in from the telescope, hits this big mirror, the 3-meter mirror, bounces up to that secondary and down through a hole in the center. And hopefully you can see in the bottom left-hand side every so often, there very brief flash of a human being, and the human being is about halfway up, reaching up to halfway up the orange box. So the large orange frame holding that telescope, the vertical size of that orange frame is the height of a human. These telescopes are very large. Some of the more recent telescopes, IRTF is a telescope from the 1970s and is still producing fantastic and amazing science. There are larger telescopes in Mauna Kea now that are 8 meters or 10 meters in size. And if they were built like IRTF is built, which is incredibly stable because it's this huge frame, they would probably collapse under their own weight. So more modern telescopes tend to look a bit more like a spider's web because they've got all of these different frames that are built to provide the strength without the weight. But IRTF is just small enough that it doesn't need to do that. And instead, it works on having an enormous amount of stability because it's just built out of a huge amount of metal. I don't know if this is true, but we have always been told that it was made out of an Italian battleship that was decommissioned. And one of the big advantages for us in that is that it is weighty. So if the weather conditions are particularly bad on the telescope, on the mountain, it is generally speaking able to observe in a way that other telescopes are not. So I've often been at the summit and we've been the only people observing on the whole mountain, just because if the winds are very severe, most telescopes have to close, but IRTF is able to battle on with its much heavier footprint. So that can be very useful.
Okay, I am just going to start to welcome people to our event today. I'm going to share my screen really quickly. So sorry to take you away from the amazing work that we're seeing happen out in Mauna Kea. But I want to make sure that people who are joining us know what we're doing, who we are working with, and who all these wonderful scientists are. So I'm just going to go ahead here. I've got, there we go. So welcome to a live broadcast of Chasing Shadows at Jupiter, a live stream observation from the summit of Mauna Kea. This event is in collaboration with the University of Leicester School of Physics and Astronomy and is part of the Royal Astronomical Society's bicentenary in 2020. Yes, we are 200 years old. Hello, I am Lucinda Offer, Education Outreach and Bicentenary Events Officer for the Royal Astronomical Society. Thank you for joining us today to observe Jupiter as Ganymede cast its shadow on the planet. And we will be observing it all remotely from this historic NASA infrared telescope facility in Mauna Kea, Hawaii, put in place to support the Voyager missions, as Tom just mentioned, where we got our first close-up view of Jupiter back in 1979. We are here today with astronomers from the Department of Physics and Astronomy at the University of Leicester. Dr. Tom Stallard, who's Associate Professor in Planetary Astronomy, who explores Jupiter's auroras and their interaction with the upper atmosphere, and Dr. Henrik Melin, an STFC research fellow who exploits infrared and ultraviolet observations to explore the variability of Jupiter's climate and the origin and formation of the giant planet. And I should also note that we have the fantastically wonderful Emma Thomas, who is making sure all of this happens and runs smoothly. She's doing an amazing job. Thank you, Emma. Also from the University of Leicester, studying astronomy with Dr. Stallard, who's making the remote observation happen for us. Thanks, Emma. And now back to Dr. Stallard and Dr. Melin, who is going to explain to us what we will be looking at and what we were looking for in today's observations. And obviously we're seeing here some of the things that can happen when you're doing remote observations. I did want to mention, I will be introducing him later as well, but we also have Nahid Chowdhury, who's a third-year PhD student at Leicester, working with this team. Welcome everyone, and thank you so much for being here. I'm going to give the screen back to Emma. You guys are doing a fantastic job. I'd love to know an update of I was kind of what has happened with the telescope. Can you share what might be the issue?
Henrik, do you want to try and explain what's going on?
Yeah, as far as I understand, they put in a new system. So there's a system that sits under the primary mirror. The primary mirror is 3 meters in diameter, so it's a massive, heavy thing. So they have a system that regulates the pressure underneath this mirror so it doesn't just fall off when the telescope is highly tilted. So they're putting a new system which hasn't properly deployed. And so they're having to revert to the old systems. There's 2 engineers on the summit right now trying to fix this issue. We're hoping it won't be too long, but these things happen and they can take time. So hopefully, yeah. I'm not an expert on the details of all this, but yeah, hopefully they can solve it for us. That'd be great.
So, I mean, we can certainly talk about the observations, but it might be better to wait until Jupiter is actually visible. If it doesn't happen soon, then we can start talking about it, but maybe it'd be fun to talk about all the ways we haven't got observations in the past. Certainly, every astronomer has battle stories about why they didn't get observations. Henrik, what's the best reason you haven't gotten observations in the past?
Well, the best and worst, I suppose. So me and Tom were on the summit. This is quite a few years ago, maybe 5 years ago. And we were observing Saturn, I think, on this instrument called Seashell. It was iShell, I can't remember. But it's a high resolution spectrograph. And we're observing, everything's fine. The weather is amazing. We're getting some fantastic data of Saturn, the aurora of Saturn. And suddenly there's this massive bang inside the dome, which is unusual. Things should not go bang inside the dome. It's a telltale sign that something is very off, right? And so we walk into the dome and there's the instrument that's shattered, it's exploded. And so one of the instruments, an imager called NSF cam, had exploded on the summit. And this was caused by a buildup of pressure inside the instrument. And, it's just a shocking thing to see. And, you know, as tragic as it was quite spectacular to see it happen, you know, or to hear it happen right there. And there were shards of this instrument. This is a massive dome, right? Maybe about 20, 30 meters in diameter. And it was shards of this instrument, like everywhere. It was, it's a night to remember for sure.
What was amazing to me was the response that IRTF had when that happened. Within an hour of this unprecedented event happening, there were engineers at the summit working to fix things. They were we'd given up on the observations instantly, but they were desperately trying to get us back on the telescope, which is the dedication that they have to trying to get astronomy to work. I think ultimately we decided with them that maybe we'd wait for a night, but we did get back on the telescope the next night, which is pretty insane, to be honest, that they were able to get things working that quickly. So that's one thing that can happen. The instrumentation can break, and that's probably the most dramatic time that that's happened. The least dramatic time it ever happened was also at IRTF, when one time an Ethernet cable came unplugged, and it took us 2 hours. It took the team at IRTF 2 hours tracing through all of the wires, and believe you me, there are a lot of wires in that telescope, thousands and thousands of them. They were crawling on their knees trying to find them, and they eventually found the one that had come loose and replugged it, and we were able to start taking data again. Other things that can happen are more widespread than that. Obviously, this year we've lost time because of the current crisis, but we've also lost time because of IRTF being in Mauna Kea, which is in Hawaii, and Hawaii is one of the most active volcanoes in the world. So we have been in the position before where we were waiting to go to the summit, and the IRTF, the volcano that the IRTF isn't on, the other large volcano on that island, erupted. I don't know, Henrik, Nahid, maybe one of you want to talk about that experience?
Well, as you say, you're in a location where you're susceptible to earthquakes, pretty much. So occasionally, I guess, they can be terrifying. But in the case that we were, I think it was 2017 in May. It was on the news at the time in the UK. Because I remember, my mum was sort of ringing me up, and she was a little bit distressed because on the news usually sometimes things kind of get blown out of proportion, so to say. But it was quite a mild earthquake, I suppose, in some cases. But it can be scary, and often these earthquakes can disrupt observing plans because observatories might have to close on the summit. So, yeah.
The problem with earthquakes is that these instruments are so finely built that it doesn't take a lot to cause non-obvious damage. So it doesn't have to be big cracks in the dome or anything. It can be just a very slight shift in the instrument, and you have to check for that because it can be damaging to the instrument to do that. I've had earthquakes in Hawaii, and I've had earthquakes in Chile when I've been observing that have stopped. In Chile, there's a giant label on the wall which says when the last earthquake occurred and what size it was. So you always know how long it's been since the last earthquake. And I was there. It was a very small earthquake. It was, I think, a 3.5 magnitude earthquake, but it was enough to shut down for the rest of the night just to make sure that everything was good. Through the rest of the day, the engineers checked everything, and it worked. Got back to working very well by the next day. But that can be very difficult to get past as well.
Hi, Tom. This is Lucinda. We've got some questions here from the RAS YouTube, and I just want to thank everyone for joining us on Zoom and also on YouTube. But a really good question has come in because I mentioned that we're looking at Ganymede as it crosses the disk of Jupiter. But Stephen has asked, he wants to know, are we just observing the shadow? What's the part of the scientific data that's being gathered today? So maybe we could talk a little bit more, I don't know if you have yet, about the science that we're hoping to gather today.
Absolutely happy to talk about the science. I have a whole slew of different slides that I could show. Maybe I should do that now, and then we can talk in a bit more detail about what we're doing, or I could talk very lightly about what we're doing. I guess the general answer of what we're doing is that we're trying to look at the very top of the atmosphere of Jupiter. Just like Earth, when you look at the different atmospheric layers, lots of things are happening differently at different layers in the atmosphere. And there is a boundary layer right at the top of both Earth and Jupiter, where everything starts getting very thin and you start getting ions and electrons separating out into a plasma, and that means they can conduct just like a wire in a circuit. And so when you have this massive magnetic field extending out into the surrounding space, on Earth at least, that magnetic field starts interacting with the sun, and then you start getting all sorts of currents build up, and that drives the aurora on Earth. You see this current system that drives all the pretty northern lights that you see if you go into Alaska, or you go up into Norway. You can see these wonderful auroral displays. When they're particularly strong, we can even see them in the UK. And so that interaction layer is really interesting at Earth, because it really gives us a view of all of those dynamic interactions out further out in space. Jupiter is more complicated than that, because as we all know, Jupiter's atmosphere is much bigger. It's basically all atmosphere. And so its atmosphere is more boisterous. Basically, when you look at the top of the atmosphere on Earth, it's all very thin, and it gets bossed around by the solar wind, the sun, telling it what to do. Whereas when you go to Jupiter, you've got this massive atmosphere underneath that doesn't like being bossed around. And so there's this much more complicated interplay between what the atmosphere wants to happen and what the surrounding space wants to happen. And there's a battle in the layer that we're looking at that causes, I mean, all sorts of really interesting interactions. And so that layer is really interesting for understanding the aurora, but also what we're finding more recently, it's really interesting for finding out what's happening down in the equatorial regions as well. And so what we want to do, and I can show more details about that in a bit, is really understand that better. And one of the fundamental things we don't know is just the really basic information, which is how quickly does the ionosphere get made and how quickly does it disappear again? There's all of these different balances between what is making all of the ions in the top of the atmosphere and then what is taking them away again. So when you move on to the night side of either Earth or Jupiter, you're moving from a sunlit side to a side that isn't lit by the sun. The sun has a whole range of different wavelengths that it throws out light in. Obviously for us, it's the visible that is most dominant. If I open a window, suddenly there's a blinding amount of visible light hitting me. But on the surface of Earth, we're really lucky. We don't have any of the really high energy light that the sun kicks out, because we have an ozone layer in the atmosphere, at the top of the atmosphere of the Earth. And that absorbs all of that high energy light, which is very lucky. So that light gets trapped by the top of the atmosphere and saves us from all of that damaging energy. And so in doing that, it's absorbing all of that light, and that light is dumping a load of energy in the top of the atmosphere. And so when you look at the very top of the atmosphere above the layer of the ozone layer, where it's sucking up all of that light, that energy is still pounding through the atmosphere and causing all sorts of damage to the top of the atmosphere. It's ripping apart all of the molecules on the top of the atmosphere, and that causes you to have a lot of ions, because all of the electrons get pulled off of the neutrals and you produce this ionosphere. So even away from the aurora, across the whole disk of Earth, you have an ionosphere on the day side, on the side facing the sun. But as soon as you move into the night side, you turn off that source of ionization, and it drains away. So as you go through the night, you see less and less ionosphere. There's still other sources for those ions to be generated, but it drains away as you remove ions. So there's all sorts of things that destroy ions. And so that's something that we understand really well at Earth, because we're on Earth. So we can look at the sky in the daytime and we can look at the sky in the nighttime, and you can see what the ionosphere is doing. But we are not on Jupiter. We're looking at Jupiter from very far away. And the really important point is that we're really close to the sun compared to Jupiter. So as we orbit around the sun, we never really get a very good view of the night side of Jupiter. We're always looking at the same face, the face that looks back at the sun. So we can get a really good measure of what's going on the day side of the ionosphere of Jupiter. but it's really hard to see the night side. So we really don't know what happens as you move from day to night. And so we have to think about a way to do that. And we've used spacecraft as they fly by to try and do that, to very limited success. I've tried sneaking a view on either side, as where the Earth is all the way over on one side of the sun or on the other. That hasn't really worked either. So this is my last shot, basically. This is my last hope.
Today was a really unique opportunity then to observe this. Is that correct?
Well, exactly. Basically, if any of you have been in an eclipse, it's an amazing experience. I was very lucky to be in an eclipse, but unlucky that the clouds were over it when it happened. Back in 1999, I'm sure a lot of older viewers were around for the eclipse that crossed Europe. So I was able to see that from somewhere near Paris, and it was a beautiful day right until about 10 minutes before the eclipse happened, and then a cloud that was following the eclipse crossed the sky and we didn't see anything, but you could still have the overall effect of what happens, which is as the sun moves behind the moon, it starts getting darker and darker. You see a partial blocking of the sun and then a full blocking of the sun, and all the birds come out because they think it's nighttime. They start singing, they start flying into the trees. It gets colder. You feel the chill from the fact that the sun isn't there. And it doesn't last very long at all. It lasts a minute or so. Everything gets very strange and sullen, like a sudden twilight. And then the sun switches back on again and all the birds get incredibly confused. And then you're back out of your eclipse. Earth, it doesn't take very long to happen. It's only a minute or so. But it's quite a shocking experience to go through if you're not prepared for it. This feeling of it suddenly being nighttime. So
oh, sorry. I was just going to say, I know that we're having some issues today with the telescope, so it's fingers crossed that we can get this sorted in enough time so that we can take advantage of this observing time, because I know it's limited, even though we have an opportunity to view it for about 3 hours, I think you said. Possibly.
Yeah. So I'm very hopeful that we'll still be able to get a good amount of time on the telescope. We have already had one night of observing. We were able to last week take observations of Callisto crossing the disk of Jupiter. So Callisto and Ganymede are two moons around Jupiter. They're similar in size, but Callisto is further away. And what that means is that Ganymede is a strangely unique position. It orbits about the same speed as the planet rotates, which means that as it crosses the disk, the surface is moving at the same speed. So unlike the moon, where you have maybe a 1 minute period of darkness, you have nearly an hour of darkness underneath Ganymede's shadow if you were to be in a balloon in the atmosphere of Jupiter. Callisto was further out, so it has a much shorter time. It's maybe 25 minutes. So the idea has been to try and compare those two and understand what the difference is in how quickly the ionosphere disappears and reappears again as you move into darkness and out again. And we took some very nice data, which I can show some of. So if we don't get anything at all, we at least have some results from last week, but I'm fairly confident we'll be able to get on the telescope in the next few minutes or so.
I wanted to mention that we have the Dr. James O'Donoghue, who I know you know, who has joined us on YouTube. I think you mentioned he's in Japan, but he made this really great comment there. He says there are only thousands of practicing astronomers in the world, so about 1 per 1 million, and you're looking at them in their element like a safari. So it's almost like astronomers in their environment. So that was a pretty funny comment. Thank you for that. And then also, Amisha's asking, is there a public link to the sky view over IRTF that we see bottom right at the screen? And thank you, Dr. Melin shared a link. So I'm going to try to post that to the YouTube page, and it's a really good question. Would that allow our viewers on YouTube and Zoom to be able to view it themselves at home while they're watching this?
Yeah, it's a fantastic resource for us as astronomers, but it's also amazing to, as the viewing public, every night you have 20 or 30 separate cameras on the summit of Mauna Kea looking in all sorts of directions at the telescope and at the sky. So you can see some fantastic things in those views every day.
Permitting the weather.
Well, one of the things that we find is that the sunsets and sunrises in Mauna Kea are prettiest when we're not going to get very good data. So if you've got perfect conditions, the sky is completely clear, the sunsets are a little dull, but if you know that you're not going to get any good observations, then you're at least given a little gift before a very frustrating night of a fantastic display of beautiful sunset.
So I wanted to ask Tom, if we were viewing it right now, what would we be observing? Because I think we were meant to kind of be able to view something off Jupiter at, I'm looking at the time here at 11:30 possibly.
Yes, okay, so let me see if I can pull up a wonderful animation that James O'Donoghue, who you just mentioned, has made. If I can share the screen. Let's see. I think this will do it. I don't know if you can see that. I think not.
Yes, I can see it. Looks great.
Okay. Okay, perfect. So this is the view of Jupiter from Earth. You can see, we can see a beautiful disk. Now, I'll show you in a second what we saw when we looked at Callisto, and it's not nearly this pretty, but you can still see this structure, and you can see Ganymede off to the left, and you can see the timing at the bottom. So this is about 10 o'clock. We in UT, which is the time of that all astronomers use, and that's basically Greenwich Mean Time. So we're an hour ahead of that because we're still in British summertime. So this is at 11:05, and then we are now at 11:40, somewhere about here. So you can see that the shadow of Ganymede has moved onto the disk right now.
I misspoke there, Tom. We are in presenter view here, so I'm wondering if there's any way you can make that big for us.
Don't know if that will work.
Oh, that's perfect.
There you go. Perfect. So you can see that when we were supposed to start, which is about 10:30, the shadow was just coming onto the limb, and now we're here at 11:40. But you can see that as the night goes on, we have a fair amount of time to continue to observe all the way through till about 2:15, 2:30, I think, when we'll see it move away. So we have got a little bit of time still to take some good data. And the longer we get, the better, obviously, but hopefully we'll have a good amount of time. If I then go to here, this is the movie that we took last week. You can see the shadow is now off to the right, not the left, because then the sun was in a different direction. And you can see, if I just pause this video for a second, you can see the disk of Jupiter. This is in the infrared, so it looks very different to what you would see from a telescope with your eye. The equatorial region is very bright. You can see the really bright great red spot right at the bottom. This is saturating out, and then all sorts of weird structures because the great red spot's undergoing some very odd transformations in the last couple of years. And so some of that is still coming through. There's also some other minor spots on the surface you can see here. What you see at the pole is this weird haze that we get. There's a haze of particles that cause it to be more reflective, but this looks quite bright, but actually this is nearly all incredibly dark. You can see that because, you know, this is Ganymede here. It's incredible, sorry, Callisto. It's very, very bright obviously Jupiter should be way brighter than this tiny moon, but actually the atmosphere is filled with methane. And as we know, methane is an incredibly powerful global warming gas. And so it's very effective at capturing infrared light. So as the infrared light hits it from the sun, it soaks up all of that light, and only a small amount of it gets reflected back to us. And so that's why the moon, the tiny moon, is vastly brighter than Jupiter. And it's also why the Great Red Spot is so bright, because it sits above that methane, and so it's very bright. But what you can see is that there's this cutout inside of the movie, and that cutout is actually where the light goes into the instrument and where we do our science. And you can see that we've put that cutout directly over the shadow. So if I go back, you can see that as we watch the data, we're able to try and follow that spot through the night and get observations that allow us to take data both outside and across that shadow on the planet. So the light is coming into this slit and getting split up into multiple wavelengths, and that gives us a measure of what's going on. I can show you what that looks like when we get it into the instrument. This is, again, that very complicated view. And what you might think you're seeing here is Jupiter, but actually what you're seeing here is Earth. We're measuring in the infrared, and the Earth's atmosphere is hot. And so nearly everything you see in the telescope, coming into the telescope, is actually from Earth and not from space. So this is just a single frame of data, and there's all of these emission lines through this data that's showing you what we see without doing any correction. So what we'll do is we'll take frames on the planet and take frames off of the planet, and you can see it every so often blinks away, it goes dark. And when it's going dark, we're moving to a really boring bit of the sky and taking some data on the very boring sky, so that we can subtract out all of the stuff that we're seeing from Earth's atmosphere and only get material back from Jupiter itself. So the next frame is 20 times weaker than this one. And you can see we've subtracting out, it's not a perfect subtraction, you can still see the residual lines coming from the Earth's atmosphere, but there's this reflected sunlight coming from the disk of the planet, and we're getting a whole array of different spectral features. So what I've done is I've added those together to get a better signal and zoomed in a bit. So you can see that the slit here, I've rotated around 90 degrees because that's how the data comes out. So now we're looking from top to bottom, from the limb down across the disk of the planet. And so the sunlight is hitting and reflecting back to us, and that's what all of this broad light is coming back as. But there's big gaps in it, and those big gaps are all of those methane absorption lines soaking up and heating the lower atmosphere. And that's really useful for us because it makes that region completely dark. Basically, the whole of Jupiter is completely transparent in that region. And all we see is the glow above the planet. And you can see that there's one very thin line right in the middle here. That's Jupiter's ionosphere. So that's the light from the ionosphere. As it's gotten hot, it's glowing, and we're measuring the glow very brightly. And you can see that hopefully that there's this hole all the way through this data, and that hole is the shadow. So in the reflected sunlight, it's a very deep hole. There's very little light coming in because there's no reflected sunlight when there's no sun. And you can see hopefully also that there is a dip in the brightness of the ionosphere, but it doesn't drop away in the same way as the surrounding sunlight. It is fading and coming back. So it's going to take me a lot more work over a lot more time to properly understand and analyze what this dip is, but it's the first time we've ever seen a dip. Whenever we've done these experiments before, we've just not been able to measure any change across this, because mostly it's because we were using Io, and Io has a very much shorter eclipse time. So it has eclipse time of maybe 8 or 9 minutes, and as a result, the ionosphere just didn't have time to fade away. So that gives you a view of hopefully what we're hoping to see again at Ganymede. But Ganymede is slower, so it should have a deeper, darker hole.
I think we have some news for you, Dr. Stallard.
Okay.
Yeah, I just spoke to Dave, our telescope operator at the telescope, and they fixed it, and so we'll be on Sky in a few minutes. So we're going to start
fantastic news,
and then go to Jupiter. So
brilliant.
this might still happen.
As I said, you have to be very prosaic and not hope too much, but
yeah, right.
It's still a delight when you do get observations.
There's lots of fingers crossed out there for us, so that's great news, really great news.
Yeah.
Hey, Naheed, I was wondering if there are any questions out there from your end. Oh, your sound is off.
Yep, got it, thanks. So I've had one question. Someone's asked, why are Jupiter's poles hot in the infrared image? And they ask, is it because of an unstable magnetosphere?
Henrik, you know more about the mid and low atmosphere than I do. Do you want to take this question?
So the question was, why are Jupiter's poles hot in the infrared image? And is it related to its magnetosphere?
So if I remember this correctly, you have on the top of the poles, you have a haze layer in the stratosphere. So that's basically a thin layer of cloud of very small particles, micron-sized, and they really light up at these wavelengths. So it looks bright. Now it's true at the poles you also get the aurora, where the magnetosphere connects down to the atmosphere, throwing particles out the atmosphere. But we don't see that at these wavelengths so much. You can see it in the ultraviolet and some very narrow bands in the near infrared. So what we're seeing here is just a bright polar haze in the stratosphere. So basically a cloud layer that's specific to the poles.
I think I have a movie showing what it looks like in the region that we look at. Now, I described how methane gets absorbed. So what happens is the atmosphere is so dark, basically no light gets through. And so if you have a very narrow filter and you put it over the wavelength region where you see the ionosphere, you see something that looks like this, which is fantastic. Nearly any other wavelength in the whole of the spectra of Jupiter, you'll see the fantastic views of the underlying atmosphere. But this is the aurora at the pole. It's very oddly shaped, and this is where the Juno space mission is really revolutionizing our understanding of what's happening at Jupiter, because it's able to take vastly more detailed observations than we can from Earth. This is about the highest level detail we can take from the Earth. If we move into space, we can take better observations with the Hubble Space Telescope, and in the future, the James Webb Space Telescope should take equally fantastic observations from Earth. But you can see that the equatorial region is the region away from the pole is really kind of boring, and then there's these fantastically bright auroral displays. They're vastly more bright and continuous than you see at Earth, because they're controlled by the volcanic moon Io, and the material flying off of Io is happening all the time. It's so volcanic that there's always eruptions happening. Whereas at Earth, it's to do with the links with the sun, and the sun has these flares that fly out. So the interactions with that material as it flies out through space can vary a great deal with time. Whereas at Earth, at Jupiter, it's continuous. So what Henrik was talking about is a haze, and the haze comes from this aurora, and this is at the top of the atmosphere, but some of it gets deeper and makes a haze. It's not actually hot. It's more that the fact that it is a cloud, a haze that sits above all of that absorption from the methane that sits underneath, and so it's reflecting the Earth's sunlight back at us, but from above that thick, soupy methane layer that is drawing out all of the light from Jupiter. So we're able to measure this and get a really good understanding of what's going on, both at the pole and towards the equator. So that gives you a view of kind of what we would see if we had an imager. And when we're taking data, it's taking a slice through that layer. So 99% of the time, we would want to not look at this really somewhat dull region of the equatorial region. Obviously, there's these beautiful aurora, but what we found recently is that if you do look at that really boring bit for long enough, you're actually able to show that that region away from the poles is really exciting. So you can see that there's a lot of aurora that's so bright that we just turned it white now. We've scaled right down. And actually, there's this huge variability over the poles. So this is a region that no one's really talked about very much. James O'Donoghue, who we've mentioned several times now, is one of the world experts at looking at this region. This is some observations that were taken 20 years ago that I spent a little bit of time looking at, basically those images that we just saw. And you can see there's an awful lot of variability. So the equator of Jupiter is just as interesting as the poles. It's just that it's so much harder to see. So we're really focusing now on two aspects, the aurora and the equator. The Juno mission is producing these fantastic and amazing images of the pole because it's in a polar orbit. It's swooping over these regions and producing fantastic details. But that makes it much harder for it to look at the equator. So actually, we're in a position on the ground to do unique science that even these space missions are not able to do. And that's everything that we do is in collaboration across the scientific community. Spacecraft at the planet, orbiting the planet, can do amazing and profound things that we could never do from Earth. But the instrument that the team at ITF have put onto the telescope is about 1 meter by 1 meter by 2 meters. It's an enormous instrument, and other instruments on Earth telescopes can be even bigger than that. And that's because there's no real limit on the size of the telescope, of the instrument you use on a telescope. You can make it as large as you want, which means you can engineer this fantastic piece of equipment that has no constraints on it. And if you want to fly to another planet, you have enormous constraints in terms of the weight of those instruments and the size of those instruments, because you have to launch them from Earth up through the gravity well of Earth and then out through the gravity well of the solar system. So you can have an incredibly good view of a planet from a spacecraft. But this is an example of some of the constraints I was talking about. This is a view that we took of Jupiter as we flew by with Cassini. Cassini was a spacecraft going to Saturn, obviously, but it's actually quicker to get to Saturn often if you fly past other planets, and Cassini flew past Venus, Earth twice, and Jupiter to get to Saturn. And in order to make the instrumentation light enough and to work well enough, you can see that the instrument itself was only 64 by 64 pixels, and because we flew quite a long way away from Jupiter, we were only able to take very coarse data. When you move into really close orbit at Saturn, that produced fantastic observations. And of course, the images, where the imaging instrumentation was able to produce much higher resolution than this. But this is the infrared instrument called VIMS, which produced some of the most profound results that we have received from Saturn. But when it flew past Jupiter, even though it was vastly closer than we are, it was still very limited. You can see the aurora, this time in green, wobbling as the planet rotates. This is a whole planetary rotation, and the aurora is wobbling around. This is the day side in blue, and you can see that the day side is glowing. And then the night side, this is one of the other ways I tried to look at the night side of Jupiter, and you can see that it was incredibly difficult. What I was able to show was that there's not a lot going on the night side, but that was an incredibly loose definition. Not a lot going on doesn't tell you very much. In order to understand the transition from day to night, we're only looking at a single slither of pixels somewhere on the disk here. And basically that was impossible to use to really understand what we want to know, which is how quickly does the ionosphere die away? And then as the planet rotates back into sunlight, how quickly is it regenerated? So that's why, even though we're much further away, we're able to potentially look at the planets much better. And of course, the other thing is we've got a 3-meter telescope. That's a lot more light you can gather than the, I think it's 70-centimeter dish that VIMS had. And potentially we can move up in the future to 30 or 40-meter telescopes, which you would never be able to launch into space, not in our lifetimes anyway. So
Tom, those are amazing images. Sorry to just interrupt there really quickly. I wanted to make a couple of announcements. One, it looks like Dr. James O'Donoghue may be able to join us. So I've sent him an invite to join us as a panelist.
Fantastic.
One, fantastic. And the second thing is, you can see some people have their hands up in Zoom, and we'd like to give you an opportunity if you'd like to ask a question. With we'll turn your audio on, but I think what we would want you to do first is put your question in the Q&A. We see your hand is up, so when we see your name posted in the Q&A, then we will, and we see what your question is, then we'll open up your audio and we'll have Nahid take that on for us. So thank you, Nahid, for that. He'll manage anyone who wants to, again, I'll say it again, anyone who wants to ask a question in person, please post your question, write it up in the Q&A box, and then we will release your audio so you could ask it in person. So sorry for those interruptions, Dr. Stallard, go ahead. And oh, maybe I should just say it is 12 o'clock, just slightly afterwards, and this was when we were going to start discussing the science being done. I don't know if that was the presentation you were already showing us with those fantastic images of the data you've received. But I'm going to get it back to you. Coming up is a direct Q&A at 12:30 so get your questions ready, put them in the chat box. We're going to be getting ready for starting at 12:30 with that. But again, if you'd like to speak to them directly, there is an opportunity. Thank you.
Okay, I see still a hand or two up. I don't know if we've had any questions yet.
I can add a telescope just opened, and we're going to move to a star to focus up. So we can switch view maybe to show.
Yeah, that would be good.
Telescope controls.
If Emma can put up the view from the telescope, we can actually see what's happening. Emma may need to dip out at some point soon and actually start working.
So you can see that little dot right in the middle of the screen. That's the star we're focusing on. So as the focus changes, this star, which should just be a bright spot, it's going to get blurrier and blurrier. And so by changing it, we'll establish what is the optimal position of the focus.
Sorry, Dr. Melin, just wondering which panel should we be focused on? I think I see a cursor near
Yeah.
that star that you want us to look at. Okay.
Yeah, it's an image of a star, essentially. So a star is just a pinpoint of light in the sky. So it shouldn't spread out at all because of the atmosphere and the instrument. It does. And so by making that pinpoint as sharp as possible, we know we have a really good focus. So with a good focus, we can see Jupiter really well as well.
So some people wonder why the stars twinkle in the night sky, and the reason they twinkle in the night sky is nothing to do with the star at all. It's because the Earth's atmosphere, again, is hot, and that causes all sorts of turbulence. So we get heat bubbling in the top of the atmosphere, which we can't see very well with our own eyes because it's quite small scale, but we can see it sometimes when we're looking at stars. They jostle around, and it means that sometimes they dip in brightness a little bit. With a telescope, you're able to look at that in incredible detail, and you'll see them jumping around. So that means that when you take an observation of a certain amount of time, it smears out. So these stars are so far away that they really should just be 1 pixel in size. We can't resolve the disk of any stars other than some of the very closest and very largest stars in the galaxy. Practically all the stars in the galaxy are so far away that we would only see a single pixel of light if we had a perfect instrument, but we are sitting in Earth, and we have to try and counter that fact. And that's why space telescopes are so good, and that's why space missions are so good, because they don't have to combat the fact that the Earth's atmosphere is so crazy and distorted. But that's why they spread out in that way. So even when you get a perfect focus, you're still going to see a smearing out of light. And that's why, again, Mauna Kea is such a wonderful place to observe. The amount of smearing is largely dependent on how hot the atmosphere is. So if you're on a large continental mass like South America or Europe, the whole of the Earth gets heated up, and they get a lot of heat radiating upwards, and it causes all sorts of chaos in the atmosphere. Mauna Kea on Hawaii is in the middle of the Pacific, so there's vast tracts of ocean that are not heating the atmosphere, and that air blows across from that ocean over the top of the island, and you get much cleaner air. It's also really tall. It's 4,000 meters high, 13,000 foot high. So that means there's less atmosphere to look through. So as a combination of those two things gives us this really clear view of the night sky. It's probably the second best view of the night sky anywhere in the world. For a long time, people claimed it was the best, but we found a place somewhere in Antarctica that is vastly better, because there it is very cold and you get beautifully clean air. It's maybe 5 times clearer than the air at Mauna Kea in Hawaii, but it's in Antarctica. So it's almost impossible to get to. You can't see the planets from there at all, because it's looking out downwards from Earth. And of course, the Earth spins in the same axis as the sun. So the zodiac for us near the equator, it's on the equatorial plane. We can just look up and see things go past very easily. But if you're on the South Pole, you can't see that at all. So technically, the best place in the world to observe is in the very cold Antarctic plains. But it's impossible to get big telescopes there. It's impossible to go and observe there, and you can't see most of the night sky. If you exclude that, Mauna Kea is probably the best place in the world to observe, partly because it has this beautiful, clean, crisp air in a way that nowhere else other than a few islands on Earth have, partly because it's so tall. Mauna Kea is the tallest mountain in the world. It is higher from its base than Everest. It's just, 2/3 of its base is in ocean. It's in the US, it's very close. It's about an hour's drive from the airport. So it's got very good communication links. It's wired up incredibly well. It's very easy to build a telescope, run a telescope, and have all the communication links that we need in order to do our observations from the other side of the world. So that's all down to this wobbliness of the star, effectively, and trying to combat that.
How are things going with the telescope, Dr. Melin? Do we have any updates? Or is this...
Yeah, we're still focusing, and then we'll move to Jupiter. Yeah.
I was wondering, I know there's a question here. Sorry, Nahid, if I mess you up here. Because it's kind of an interesting question. It might be good. Marcus Hope, who's in charge of our Royal Astronomical Society Friends lectures. I wanted to see if I could get his question online. Nahid tried to answer it here, but I thought it might be good for our viewers to know, to explain why the focus of the telescope needs changing. Is this dependent on orientation of the instrument rather than the distance of the object?
Yeah, it's Tom touched upon this earlier, but basically Jupiter is so far away, it's basically an infinite distance. It's more about the telescope itself. If you turn the telescope, you put different pressures on it, and so you have to change the focus for that reason. But the most important reason is the temperature of the telescope, because that expands the metal in the truss that holds the secondary mirror. So the primary mirror sits at the bottom, is this 3-meter mirror. There's a smaller mirror up top. And the distance between those two changes as the metal expands in the trusses and contracts when it's cold. It's actually quite well characterized. You can plot focus versus temperature and get quite well understood behavior. But having said that, you have to focus quite often because things change in a predictable way as well. So, yeah.
Lucinda, if it's okay, I'm going to take one really quick question from Eddie. In fact, I'm going to let him ask his question, if that's okay.
Yeah.
All right, so Eddie, stand by. I'm going to allow you to talk. All right.
I've unmuted. Can you hear?
Yeah.
Yes, we can hear you. Please go ahead and ask your question.
No, I often observe Jupiter in the 4 moons, and they are very large moons, more or less planet size, like Mercury. But then there's about, I'm not sure how many now, 70 or 80 very small moons. Some of them just a few meters across or a few miles across. But there's nothing in between. There's no middle-sized moons. I mean, with Saturn, you get some middle-sized moons and large and small, but not with Jupiter. There's just 4 large and then umpteen small moons. Any reason for that? Why there's no middle-sized moons? It seems though all the moons were actually like captured asteroids.
So there's 3 kinds of moon at Jupiter. You've got the captured asteroids called the irregular satellites, and they sit far out and they spin in all sorts of directions. And nearly all big planets have those irregular moons. And in fact, even the Earth has them sometimes. They sometimes appear and disappear again. We often get announcements that we have a second moon before it rather flippantly disappears from our orbit around the Earth. But you've also got these near-in moons that are regular satellites that are moving close in. It's an interesting question. I think potentially one of the real questions is more why Saturn has middle-sized moons. There's some really interesting research done recently about why Saturn might have some strange things going on in it. And if you think about Saturn, the obvious strangeness about Saturn is that fantastic ring system. And some of the work that James O'Donoghue worked on, James is now in as a panelist, was to look at the ionosphere of Saturn. And when you look at the ionosphere of Saturn, there's some really weird things going on. And that's because all of this stuff from the rings is falling into the ionosphere and changing the ionosphere of Saturn. And when James looked at that in detail, he showed that that's happening at a really alarming rate, a rate at which if we allowed it to continue, it would mean that the rings would disappear in a time span of maybe 50 or 100 million years, which is an enormous amount of time for us. But it's a very short amount of time compared to the solar system as a whole. And at the same time as that work that we've done, where we maybe shown that the rings are really young, there's been people working on the dynamics. And that means that potentially the dynamics of the system also suggest that the rings are really young, but may also have really important roles to play in those middle-sized moons, and maybe have a story to tell about the generation of those moons. But it is fascinating that all of the planetary systems, all of the giant planets, have very different moon systems. Uranus has only small to mid-sized moons, and that may have a really important role to play in the reason why Uranus is tilted over. It may be that it used to have moons and they got ejected or crashed into the planet itself. Neptune has one enormous moon. It's a very large moon called Triton, but that appears to be an irregular satellite that was captured, and it's effectively as if Neptune captured a Pluto-like world. And in fact, Triton is larger than Pluto. So this level of dynamics is really interesting because it harks back to this really early period in the formation of the solar system, where there was so much going on that I think each planet tried to form moons around it in its own way, but then all of the chaos of the formation of the solar system changed the configuration for each planet. Things have calmed down now somewhat, but there is, according to Saturn at least, the potential for really crazy havoc to still reign. And it's quite possible only 100 million years ago, sometime during the period of the dinosaurs, something happened at Saturn and created this ring system and maybe changed the configuration at Saturn as well. But yeah, understanding the way those moons are distributed and why they're so different is a fascinating subject, for sure.
Thank you for that, Tom. And thank you, Eddie, for your question too.
We were about to get our first view of Jupiter right now.
Ah, yes. Fantastic. I can see it.
See the shadow as well. It's not showing up in the Twitch stream quite yet.
Apologies, it should be coming over shortly. There's a slight delay.
That's okay. I wanted to mention that James O'Donoghue has joined us as well. I believe
James
from Japan. Dr. O'Donoghue.
Hi, James.
Hello, how are you doing? I'm in Japan. Here's the proof. It says Okinawa on it. It's cool, right?
Very cool.
I got it because you've got many shirts like this, Tom.
Thank you.
Yeah, I'll give it you as a gift one day.
So right now, I don't know who is it. Is it Henrik moving the telescope, or is it Emma?
Yeah, I'm doing it.
Okay, so Henrik is positioning up the shadow on that cutout, that horizontal cutout, which is the hole in the imager that the light goes through and goes into our instrument and allows us to spread the light out and take data. But before we can do that, we need to make sure that Jupiter doesn't move around too much. And if you remember back from when I showed that video, and I can show it again in a bit, actually, Jupiter does wobble around quite a lot. The Earth's atmosphere causes it to move, and also because we can estimate what the position of Jupiter is very accurately, but that doesn't account for the fact, again, that the telescope flexes as you move through the night sky. This is a hugely heavy piece of equipment, so as you move through the night sky, the exact positioning actually shifts inaccurately compared to where we've calculated where Jupiter should be. And so in order to correct for that, we use a system that has a guiding system that calculates an exact position on an object that we understand and corrects. So usually we will use a star outside of Jupiter, and we'll position up in a way that gets us a nice, clear, clean view of Jupiter, and we'll do whatever observations we want. But we're very lucky here because we want to look at the shadow. And so we need to position up on the shadow, and right next to the shadow is Ganymede. And Ganymede is giving us a lovely, bright source that effectively looks like a star. So we're using a guiding instrument that basically calculates the exact location of Ganymede in any particular image, and it moves the telescope if that object is away. And you can see perhaps down in the bottom right panel, a little purple box and a little line, and that line is pointing towards where the purple box is. And so every time we take an image, the instrument says, I want to get back to that purple box. I want us to be directly on that position, and let's line it up. And so we're lining up on Ganymede continuously in order to make sure we never move away from that. And the shadow is slightly offset, so our slit is slightly offset from the center of that. So it allows us to sit and look at the shadow as we take data. And if there's any motion away from that position, we can go back to it. So once we get that guiding system working and we're confident with it, we can actually start taking data.
Seems to be a few minute delay on the screen compared to the TCS.
Yeah, I apologize. It's my lowly internet at home is trying its best. But I will do my best to try and fiddle around as we go. But thank you everyone for bearing with this.
Could share the, what's it called? The video control system instead, maybe?
If you mean sharing both Carl and Cartman?
We could just share Carl for now, and people can directly see the instrumentation. That would be fine, I think.
I may need a couple minutes to do that because it's two different laptops at the moment.
Okay. So whenever we're observing away from the telescope, it's always a little bit complicated. You kind of need at least two big monitors to do it because you've got these two instruments. So it can be quite difficult. And before these last few months, I would have gone to my office at work with a really stable internet connection. I'd have had at least two screens up just to get things working, then maybe a third screen to talk with the telescope operator. Now we're trying to talk to all of you guys and show you what's going on at the same time. So not only do we need those two screens, we've got another screen so that we can talk on the Zoom panel. Then we've got another screen to talk to each other so that we can make sure that things are going on. There's another Zoom link that links between us and the telescope. So it's become interestingly complicated in the last day or so trying to figure out how to set all of this up. But hopefully what we can do is be able to show you what's happening in terms of the planet and the observations that we're taking.
I wanted to ask a question on behalf of some of our viewers from YouTube. Some of them are newbies, and so they do request, if you're speaking about something that's being presented, that I don't know if it's Emma, who only has a cursor, who can just point to things. She seems very busy right now. Yeah, so poor Emma. I wish I could reach out and help you there.
So I think part of the problem is that we do have a pointer and we can point, but if there's a long delay, then what you're seeing and what we're pointing at doesn't tie in particularly. So hopefully once we get a more direct view of what's going on, that should make things a little bit easier in terms of being able to see what's going on.
Okay, thank you for that.
I will try and describe things in as much detail as possible.
This is like one of the backgrounds you have in a movie, but actually everything in the background is actually real. It's not just made up stuff. It's it is confusing. Yeah, after a while you get used to it all.
I guess I can talk through what we're seeing. So I don't see the stream right now. So are we able to see the guider completely, or is it just one frame of the guider?
We're currently seeing A and D. But I can, well, it should be moving over shortly, but unfortunately due to the delay, it will be probably another 2-3 minutes.
So, I mean, inside A and D, you can see hopefully a very colorful picture of Jupiter. The colors that we use are predetermined by the instrumentation itself. And I think that that's probably the most controversial thing that we fight about regularly in all of the observations we take. Which color scheme are we going to use? All of us have our own preferences for the color schemes. Today we are on color scheme B, which is this black to blue to red to yellow to white color scheme. So it's just a measure of brightness. We've got an instrument that has basically a filter, and that filter filters out all of the light except for a certain wavelength, and that wavelength is called a window in the Earth's atmosphere called K. And that's about 2 microns. So it's a much longer wavelength than we see with our eyes. It's in the infrared. And so all you would really see is a brightness from no brightness up to a maximum. And it's really just varying that brightness. And so we're seeing different colors assigned to different brightnesses. And you can see that the brightest thing in the image is Ganymede by a long way. And that again is because the methane in the lower atmosphere is absorbing all of the light in the atmosphere. And so Jupiter is actually less bright than Ganymede. The next brightest thing is a really long band, a big fat cigar, and that's the equator of Jupiter. And that's really bright just because the layers of cloud at Jupiter in that region are very high up. And so because they're very high up, they're above most of that methane absorbing all the light. And so they're reflecting more of the sunlight back at us. And then you can see the disk of Jupiter. So you can see that we're seeing reflected sunlight across the whole region. You can see some weather bands across that. There's that haze at the poles. That again is a region where there's more material above the absorption of methane. And then what you cannot see particularly clearly is the shadow of Ganymede sitting immediately to the left of Ganymede. You can see a thin letterbox slither cut out. And the way that works basically is there is literally a slit. The instrument has a polished mirror that reflects light back with a hole cut in it. So what we're seeing in the imager is that reflected sunlight reflecting off of this mirror. And in the hole, the light isn't reflecting, it's going through. And as it goes through, it goes into the instrument and where we take data. So that's now working through. And hopefully, at some point soon, we will actually start using that to take spectral data. I don't know, Henrik, have we started observing with
Well, actually, Dr. Stallard, we need to switch screens here. Emma's troubleshooting and is going to need to change her laptop. So Yeah, it would be great actually if Dr. Donohue's animation that you created to be able to show it in visible light for those of, that might be a good opportunity while she's doing this. Or no, maybe she's quick at it. She's ready to go. And we're also coming up to 12:30, so just wanted to give you a heads up. That is when we are set to start the Q&A with Dr. Stallard and Dr. Melin. Because 1 o'clock, I think we've got Professor Emma Bunce joining us. So just to give you guys a heads up, thank you.
So I have James's animations queued up, but maybe we're at a point where we can actually see what's going on.
So we just started taking some data.
Fantastic.
You can see the shadow relatively clearly in that view. Oh, maybe not.
So it's gone dark for a really good reason, and the reason is because, as I said a while ago, the Earth's atmosphere is really hot and really bright. So nearly everything we observe is the Earth. So we have to get rid of that in some way. And so the way that we do that is that for some of the frames, instead of looking at Jupiter, this really interesting thing, we go to the most boring bit of sky we can find, and we just observe Earth, basically. We don't want anything else in that. We don't want any stars. We don't want any moons. We just want a blank bit of sky. And by doing that, we can see a lot of Earth and nothing else. And then we can take one frame, which is all of the interesting stuff of Jupiter and all of the Earth, and a second frame where there's nothing interesting at all in space and just the Earth, and subtract one from the other. And what we get as a result is just the object, just Jupiter. So it's pretty boring to look at, but it's essential for taking our data because it gives us that comparison that allows us to see just Jupiter instead of being swamped out by the Earth's atmosphere. And we have to keep taking that because as we look at the Earth, the temperature of the atmosphere is changing, the position in the night sky is changing. So what we see in the night sky will vary over time, especially because Jupiter is moving on the night sky as well as the night sky itself rotating past us. Okay, so I have, let's see if I can pull this up. James might want to talk about this.
I wanted to also ask James if he could, and I'm sorry because we're so happy you could join us, but if you could introduce yourself a little bit at this point.
Sure, yeah. Hello, I'm James O'Donoghue. I'm a researcher at JAXA now. I was formerly actually Tom Stallard's student in Leicester. So we have a history, a good history, the best history. And then I went on to live in America for 5 years. And so now I'm in Japan for the last year. I work for the Japan Aerospace Exploration Agency, which is basically Japan's NASA or like ESA or something like that, but on a much smaller scale. And yeah, I'm just, thanks for having me on. It's a pleasure to be invited. And it's really, I think this is the first time I've seen Ganymede shadow on Jupiter, especially live. I will say that it's 34 light minutes away. So as well as the delays of zoom, there's another delay of light speed.
So if I share my screen, I can show this movie, which is one that James very kindly made for us. And this is looking down, oh, let's see if I can, this one. This is looking down on the pole of Jupiter, you can see. I don't know, James, do you want to talk through what we're seeing here?
Yeah, this is a sort of a top-down view of Jupiter and Ganymede. You can just about see Ganymede moving along there. This is actually to scale in distance, but not in size. So I actually had to make Ganymede about 5 times larger, just so you can really see it. And in this sort of red line, you can picture that being sort of the line of sight between the telescope in Hawaii all the way up to Jupiter. And so this is what we're seeing tonight. Yeah, I mean, well, it's tonight here in Japan, tonight here in Hawaii, but it's in the morning in UK, I guess. But yeah, this is what we're seeing, and yeah, maybe we can go to the other. Yeah. So this is this is actually to scale. I kind of eyeballed where the Great Red Spot was, so I hope it appears on time, because the Great Red Spot actually drifts a few degrees per month, or like a 1 degree or 2 degrees per month. So you have to sort of rely on observations that actually amateur observers take to figure out where the Great Red Spot will appear. So I checked out maybe three different amateur. I don't like saying amateur. They're all professional. They're really, really amazing. Actually, there's the citizen observers. That's what they are. But yeah, I checked out something like Damien Peach's recent observations from May and June this year, and hopefully this is where the Great Red Spot will appear tonight. So fingers crossed. It looks like I got the shadow and Ganymede right anyway, so the rest should be okay.
Great, thank you, James.
Oh, one extra bit. There was a question right at the beginning of the YouTube chat earlier on, something like, how big is the shadow on Jupiter? As a function of Jupiter's size, it's about 0.03% of the surface of Jupiter. So it's very tiny. Yeah, just a small little fact there.
But in terms of its actual size, because Jupiter is so enormous, Jupiter is very, very large. It is, I think, approximately 5,000 kilometers in diameter, the shadow. So it's approximately maybe a third to a half the size of the Earth. So it's very, very big.
Yeah, it's big.
But Jupiter is very, very, very big, and so it looks really small in the image. And that's one of the really important things. Really, we wouldn't be able to see it if these things weren't so large. Jupiter is very, very, very big, but very, 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 very far away. We're 5 times as further away from the sun as we are, and so if you think about how far we are from the sun, right now Jupiter is 4 times further than that away from us. So you need a very large telescope to be able to really get a clear picture. But interestingly, not to see the shadow at all. What we're going to find out about later today, which I'm very excited about, is some of the discussions about early observations of the shadows. And we've been looking at the shadows of the moons on the planet Jupiter for more than 300 years. So this kind of observation has been done for basically almost as long as astronomy has been a science. So it's certainly something that is doable with a smaller telescope, but not necessarily in a way that gives you this kind of scientific result that we need to try and take. The images themselves are fantastic, but it's really looking through that little tiny slit and trying to break the light up and trying to build up a signal from the top of the atmosphere. And of course, the top of the atmosphere of Jupiter is not nearly as bright as the reflected sunlight that we see in the visible. So we need to look for a very long time to be able to build a strong enough signal to get the science that we want out. But we've started doing that now, so that's fantastic. Hopefully we can start looking at that a bit more.
So now that we have the telescope functioning and working, can we go back to that screen? I don't know, Emma, how are things going?
Sorry, we're just coming along to it. So yeah, I think we're now seeing the shadow you can just see on the left-hand side of the very bright circle in, well, we call, I guess, I say camera A, but frame A, which we have here on the left-hand side. As far as I believe data's going very well. We're going through our A frames and B frames.
Yep, we're taking spectra now as well as saving all these images to the file, which are nice to have. I drew a green line sort of pointing at the shadow, the dark round thing, underneath the spectrograph slit, which is the black line.
I see, the vertical line just next
Yeah, that's
to it.
right.
Yeah.
I just, I know, thank you so much for getting that sorted, Emma. I know it must be difficult switching laptops and everything, but we are just a bit past our time for Q&A right now. And I'm going to introduce to you the Nahid Chaudhry, who's a third-year PhD student at Leicester working with Dr. Stallard. He's studying Saturn's infrared aurora. He has a keen interest in outreach in astronomy and a member of the Leicester Astronomy Society. He's a STEM ambassador and has conducted outreach with the National Space Centre in Leicester and the Royal Observatory in Greenwich. So we're going to thank you, Nahid, for taking on the Q&A sessions. There's one now that we were meant to start at 12:30 and a second one coming up later. So if we don't get to your question now, there'll be another opportunity later in the day. Just looking at that time for the second session is at 3 p.m. So Nahid, on to you.
Thank you very much, Lucinda, and thanks for the intro. So we have had a few questions already in, so we'll dive right in. And the first one I'm going to ask is from Amy, who asks, what are the current theories for explaining changes happening inside and around the Great Red Spot? So who would like to try and answer that? I can repeat the question if you wish.
I think Henrik should answer that.
Yeah, it's a complicated question, and the short answer is that no one really knows, right? But we've learned a lot of new cool things quite recently, because the Juno spacecraft arrived at Jupiter a few years ago now, and it has an instrument that can sense below the cloud decks. There's a radar instrument that can sense well below the cloud deck, so we only see the top of the Great Red Spot. And one of the questions, long-standing questions, is how deep is this? Is it just a surface storm, or does it go all the way down? And what's really interesting about the results from this microwave radiometer is that the storm is actually really, really deep. It's actually as deep as the instrument can measure. So this storm is incredibly deep, which probably means it's long-lived. It's been there since ever since Galileo first looked at Jupiter. So yeah, we don't really know, but there's lots of really cool new measurements that are beginning to shed some light on this.
Okay, thank you very much.
We do know that it's been changing a lot on a long time scale. Some of the really early observations where people drew by hand suggested that it may be 2 or 3 times larger, and it certainly seems to be shrinking. But yeah, nothing as dramatic as the last 18 months in the past, I don't think.
Yeah.
All right, well,
You
thank you both for that. Oh, is that James, you want to add something?
You don't draw them by hand anymore?
Not usually.
Okay.
Okay, let's go on to the next question, which is from Yahya, who asks, where would you say is the best place in the world, or the best places around the world to see stars from, to do a bit of stargazing or to carry out observations?
It's a really interesting question, because it's actually a question not only of astronomy, but also biology, right? If you go to the top of Mauna Kea in Hawaii, the night sky view is amazing, but we would be at about 60% oxygen. And so when we look out at the night sky from the summit, actually we don't see a night sky that's particularly good, because we're being oxygen starved. And so our eyesight is not nearly as good as it would be from lower down. So if you happen to be in Hawaii and you want to see the best night sky, it's not the summit of the telescope that you would go to. It's further down, maybe 2/3 of the way up, where you've still got enough oxygen in your blood to allow yourself to see. Or you could cheat and bring some oxygen up with you, but that's something I've never done, so I can't say whether that is a good way to do it. Anywhere where you get a very clear and clean night sky is a great place to look at the night sky. There are a few in the UK. There's at least one in Scotland where it's got the highest rating of night sky available, and the profound beauty that you see on a night sky is really amazing. The main problem for looking at the night sky in the UK, at least, the main problem is the clouds, right? We always have clouds above us, but even if you have a beautifully clear sky, is the fact that we're also in a very industrial country, and so nearly everywhere there's a lot of light, street lights and things like that. So if you can get out into the countryside, you can see something very clearly. If you happen to be somewhere else in the world, going out into places that are very isolated and that are maybe a little bit higher up can be really effective. But if you're lucky enough to be able to find a really dark place, even in the UK, you'll see a completely different night sky to what we see in Leicester, certainly, because the light pollution from the street lights in Leicester basically make it impossible to see the night sky in the way that you can from a really dark place.
Okay, thank you very much, Tom, and for your question as well, Yahya. So I've spotted another question, and it goes along the lines of this. So someone's noticed that Jupiter's great red spot in the view that we're showing appears red. Now they are asking whether that's because of a chemical element in particular. I think it might be something more to do with the contrast and the colors that we're using in the viewer. Could someone try and explain that, please?
Okay, well, right now we can't actually see the great red spot. What you're seeing at the top, the bright spot that we're seeing, is actually the reflected sunlight from Ganymede. The great red spot is in the south of the disk and hasn't risen yet, but it should be rising some point through the day, and it will also be really bright. But as I said, the image that we're using is basically a single window. It's a black and white photo, effectively, that we're taking at a very specific wavelength, and that is a wavelength that we can't see with our eyes. It's a window in the infrared. And the reason why the great red spot is bright, so it would appear red to yellow, it is partly just the color scale we're using. We could switch back to a very boring black and white view, and it would be, in terms of the data, exactly the same. But it's mostly because the great red spot is an enormous storm, and the enormous storm swirls around, and as with all storms, as a really high storm head, it rises up above the surroundings. So when you look out in a lightning storm, you'll often see these anvil-shaped clouds that seem to go much higher in the sky than most clouds. And that's all the convection drawing hot air up. And as a result, at Jupiter, you've got all this hot air drawing up and making clouds that are much higher. And because they're much higher, they sit much higher against the background of all of the methane in the atmosphere that absorbs all the light. So in this wavelength, Jupiter's way darker than it should be. All of the global warming is sucking up all of that light, but the great red spot sits above that and reflects all of the light back, so it will be much brighter compared to most of the planet, and that's what we're seeing. But the actual colors are completely arbitrary. We can't see these colors at all with our eyes. If we were able to show you through some magical technology the actual wavelengths of light that the instrument is seeing, we would see nothing on the screen. It would be blank because our eyes are not able to pick up those wavelengths at all.
Okay, thank you again, Tom. So I'm gonna just ask another quick question from Arwin, who's asked this on YouTube. All right, so is Jupiter massive enough for gravitational microlensing?
So it's a really interesting question. There's an interesting counterpoint here. It is big enough, and actually it's a really good way of detecting planets around other stars. The mass of the planet, the size of the planet, is actually not that important. It's how well aligned you are. So basically, for those of you who don't know what microlensing is, light is bent by the gravitational well of massive objects. And basically, if you imagine that there's a light source in the distance, it acts as a lens. An object in the foreground bends the light that's going this way and the light that's going this way back towards you, and you get a much brighter measure of that object when there's a perfect alignment. And the size of the object doesn't really change how much brightening you get. It just changes the size of the lens. So if you have a star in the foreground, you're going to get a lot of light. It's going to be easier to bend that light. But if you have a very exact alignment with a Jupiter-sized world or an Earth-sized world even, it will also bend that light towards you. The problem with Jupiter is that it's too big in our view. Its disk is really large. So most of these objects are so far away that we can't actually resolve the object at all. So the light is going to be bent towards us by Jupiter, but it's going to hit the back of Jupiter and it'll never get through to us. So it is able to microlens, but we can't see it because the planet's just so large in the night sky that it just completely covers up that size of hole, basically.
Okay, thank you, Tom. I hope that answered your question, Arwin. I'm going to ask another question from YouTube, this time from Andreas. Okay, so he asks, There are so many moons around Jupiter. Is it possible that we'll be able to watch the shadows of the other moons today as well, and indeed at any time?
So we can do it at other times if the moon is large enough. The reason why I'm very excited about these observations is that this is something I've been trying to do for nearly 2 decades now. Back in 2003, I was observing with my supervisor, Steve Miller, and colleagues of ours from Japan and from the US, a colleague called Jack Canerney, who is famous for his magnetospheric measurements. And we saw that the moon Europa would be crossing the disk. And so we tried that time to see the shadow, but we didn't have any guiding like we have tonight. And so we weren't able to resolve that. Then maybe 9 years ago, I was in Chile, and it happened that Io was crossing the disk. And so we again tried to do these observations, but Io has, it moves much closer in, it's orbiting much closer in, it moves much faster. So as a result, the time that the shadow is there for is only about 9 minutes, and we only got a few frames. So we weren't able to see any dip at all in the ionosphere. We could see the shadow on the planet itself very clearly, but we couldn't see anything in the ionosphere. So I was very frustrated by that. And so coming back to it, I had a look at all the moons and tried to decide why couldn't I see anything, and realized that it was because Io is too close in, it's moving too fast. It's also a smaller moon, it's much smaller. So the size of the shadow is relatively small. And it occurred to me that, you know, we should go for the best case, which would be Ganymede and Callisto, where you can see things much more clearly. Any other moon than those 4, the shadow will be there, but it's going to be so tiny that there's no way we could see it from Earth, because our view is very limited in terms of how accurate a measurement we can take. And it basically would be impossible. But if you were in orbit around the planet, maybe you could see the shadows crossing the disk. And that's basically where we're at. We can see the shadows of all 4 Galilean moons for sure, but some of them aren't useful scientifically.
Okay, thank you. And I hope that answered your question, Andreas. I'm going to go back to the questions from Zoom, and this is another one about the image that we're seeing in the viewer. Okay, so the question is from Gary, and he asks, is the image that we're showing already processed against an artificial star to reduce atmospheric distortion, or is it a raw image of Jupiter?
It's a completely raw image coming in. There's no processing on it at all. There's no subtraction of the night sky either, which is why it's not a very high quality image. We could do, if we were interested in measuring the atmosphere, there's a lot we could do, lots of tricks we could take to get a much crisper and better image out. But of course, what we're using this image for, as nice as it looks, is to measure the light in the hole. That's what we're interested in. So we're trying to use this image in a way that is the best way possible to ensure that the light that goes through that gap is as high quality as possible. And so it's really important that we're able to follow the planet and guide on the planet. So we're taking much shorter integration times. We're not observing for as long as we would like to produce a nice crisp image. We would probably use a dithering pattern, would move the planet around so that any aberrations in the instrument would be cancelled out. We would do some sky frames that we could subtract off, and we would slowly build that up. So if you are talking to people like Glenn Orton, who is a fantastic astronomer that looks at the lower atmosphere, what he does to observe is very different with exactly the same telescope, exactly the same instrument. He's interested in looking at the lower atmosphere, so he employs all of these tricks to improve that image as much as possible. For us, the image is just one of the tricks that we're employing to make the data that we're taking, the spectra that we're taking, look as good as possible. And that's why the image doesn't necessarily look as nice as you might expect from other observations from IOTF.
We also had a bit of a wobble right there, a bit of a vibration on the telescope, which caused it to blur out more. So, which is now fixed.
Good to hear. And thank you, Tom, again. Another question now from Mauro, and this is an interesting one. Okay, he asks, Can you tell me a bit more about the spectra that you are collecting? Which spectral lines in particular are you going to focus on?
Okay, so there is a whole slew of possible things you can look at Jupiter, obviously. We're looking at the top of the atmosphere, and what happens in the atmosphere, and maybe I'll show this afternoon when we have a bit more time, is that basically in any atmosphere, everything's mixing up and blurred together. But as you get really high in the atmosphere, that mixing doesn't happen anymore, and everything drops out depending on how heavy the molecule is. So big heavy molecules like methane, where there's carbon and lots of atoms building up that molecule, are heavier and they drop down. So if you go high enough in the atmosphere, all that's left is the really light stuff, which is, you know, hydrogen, atomic and molecular hydrogen. So this thin layer at the top of the atmosphere is just hydrogen. Hydrogen gets whacked by anything energetic, including the sunlight. It gets ionized, and an electron gets ripped off, so you get an ion of molecular hydrogen called H2 plus. So it's molecular hydrogen H2 with that electron ripped away. That reacts more with the atmosphere and produces a molecule called H3 plus, which is the best molecule in the universe. I think everyone here would agree with that. Show of hands, is it the best? Yeah, okay, it's the best molecule in the universe. It's the simplest polyatomic molecule in the universe, at ion. It's one of the fundamental things that made us exist because it allowed chemistry in the early universe to work. It's one of the ways that you get really interesting chemistry in interstellar medium because it's incredibly reactive. If you put H3 plus near almost anything, it will react with it and make new stuff. And so it's really hard to measure H3 plus almost anywhere in the universe because as soon as you make it, it reacts and creates something else. But at the top of the atmosphere of Jupiter, there isn't anything else. It's just hydrogen. And you're whacking it with the sun, you're whacking it with auroral particles, and you produce a lot of H3 plus. And it's one of the unique places in the universe where we can see a large amount of H3 plus. So that's what we're looking at. And it's really important because it sits at the top of the atmosphere. It gets created. It's the ionosphere. It's these ions that allow us to measure interactions with the surrounding space environment. And they also get jostled by the surrounding molecular hydrogen. And they don't react with that. They get dinked about by the underlying atmosphere and heat up the H3 plus. So when we're observing in the infrared, we're literally looking at hot ionosphere. It's hot and radiating that heat out, and that's that very narrow line that we're able to measure. There's lots and lots of different lines, and actually once we get the data back, we'll be able to reduce it down and see all sorts of different lines and tell all sorts of interesting things about the atmospheric composition at that top layer. But ultimately, because of quantum mechanics, when it's hot, it doesn't just glow like an iron in a poker in a fire. It has vibrations in its molecular structure, and because quantum physics means that you can't have any old energy, you have to have fixed energies. It means that we know exactly where it's going to emit from. It's going to be very specific wavelengths of light. So by splitting the light up into lots of wavelengths, there's these little narrow lines of emission, and we're looking at ones that are very bright and also happen to be at wavelengths where the absorption of the atmosphere low down is very, very strong. So there's no reflected sunlight. All we're seeing is this halo above the planet, and it gives us this perfect measure of what's happening in the ionosphere. And so that's what we're looking at, this molecule called H3 plus, which is one of the major components in the ionosphere of Jupiter, and also happens to have really bright emission lines at exactly the wavelength where Jupiter is really, really dark. And so it allows us to get this really clear measurement of what's going on.
Excellent, thank you.
Spectra up.
Oh, perfect.
Yeah.
So I can't see that right now, but what you should be seeing is lots and lots of bands of light. And actually, we're able to subtract out the Earth's atmosphere because the instruments are able to remember what we saw away from the planet. And you can see whole bands of reflected sunlight and absorption, and every so often you'll see very narrow lines. Hopefully Henrik can find and point out one of the H3+ lines, and that shows you this very narrow emission that comes from the ionosphere itself, and that allows us to just really zone in on this thin transitory top of the atmosphere that's so interesting to us because it's influenced by all of this bulk of atmosphere underneath pushing it around, and all of the surrounding space environment pushing it around, and these two massive vast systems of energy below it and above it keep fighting each other in this very thin transitory region. And so it will do whatever above and below tells it to, and that's why it's so fascinating.
Okay, thank you, Henrik and Tom. I think we're out of time for the Q&A session for now. We will be having another one later on at 3 p.m. For now, I'm going to hand back to Lucinda, who is going to introduce our next speaker. Over to you, Lucinda.
Thank you, Nikki. Thank you so much for that Q&A. Lots of really great questions. So much science. It's in, and this feels like a sporting event. Like we're doing play-by-plays as we watch Jupiter. It's absolutely amazing, and it's only going to get better because we have with us a special guest. I'd like to welcome Professor Emma Bunce, who is the head of school for the Department of Physics and Astronomy at the University of Leicester. She's a professor of planetary plasma physics and is currently the president of the Royal Astronomical Society. So that's a position she just started this year. Congratulations, Emma. And her focus of research has been on the giant rotating magnetospheres of Jupiter and Saturn, and to understand the mechanisms which generate the dynamic auroral missions in upper atmospheres. Welcome, Professor Bunce, and may I say, what an amazing career so far. Thank you so much for being with us.
Thank you for inviting me. Yeah, it's really great to come and talk about my favorite subject.
So the screen is all yours for whenever you're ready. What are you going to speak with us about today?
Okay, so I'm going to talk to you about, like I said, my favorite topic, Jupiter and Ganymede, and future exploration of those bodies. So just give me a moment to sort my screen out.
I like your background image.
Yes, have to be done.
Thank you so much for taking the time to join us today. It's been going really great, and I'm just so blown away at everything that we've been able to do. There you go.
Fantastic. It's a pleasure. It's really great to join you all, and it's really great to see my colleagues doing their hard work, observing, which is fantastic. Okay, so yeah, I'd just like to take the next 20 minutes or so to talk to you a little bit about future exploration of Ganymede and the Jupiter system. So Lucinda has already introduced me, so I'm Emma Bunce from the University of Leicester, and as well as being the president of the RAS and the head of School of Physics and Astronomy, I'm also a planetary scientist, and I study multiple different bodies in the solar system, from Mercury through to Jupiter, Ganymede, and Saturn in the outer solar system. So I'm going to tell you a little bit about why we're so excited about Jupiter and Ganymede and the new space mission that we are launching to Jupiter, the Jupiter system in 2022. So I'm hoping that you can all see my slides and that someone will stop me if I have done something wrong.
You're looking good. We can see everything, yes.
Okay, let me just... Okay, so just a bit of a basic introduction then. As you go outward from the sun, Jupiter is the first of 4 gas giants in our solar system. I like to think of it as the planet of superlatives. It's the biggest and the best. It's the largest planet in the solar system. It's just a bit bigger than 10 times the size of the Earth and contains 2/3 of the mass of all the planets in the solar system put together. It rotates quicker than any other planet. So despite the fact that it's enormous, its day is actually just 10 hours long. Because it's 5 times further away from the sun compared to the Earth, its year, so the time it takes for Jupiter to orbit all the way around the sun, is about 12 Earth years. If I click this, you should see a nice projection of Jupiter's atmosphere. It's probably the most dynamic atmosphere of all the planets and is pretty famous for this feature here, the Great Red Spot, in which you could fit 2 or 3 planet Earths. So Jupiter has lots of interesting features. It has 79 different moons. Some of them are very small and very faint, but 4 of them are incredibly famous. And in fact, what we're finding is that the more we learn about those 4 famous moons of Jupiter, the more it sort of changes our view actually more broadly of the way planets, solar systems, and indeed the universe and how it works. So I'm going to spend a little bit of time introducing those moons to you. So Jupiter has 4 spectacular moons that are famous. These are known as the Galilean moons. And as we move outwards away from Jupiter, we first of all have Io, which is this sort of yellow disk here with some black spots on it. Those black spots are actually active volcanoes. So Io is a fiery moon covered in more active volcanoes than any other body in the solar system. So that's a pretty good start for the Jupiter system in terms of it being interesting. As you move out, then the next one in line is this body here. This is Europa, which is smooth and icy on its surface, a real contrast between how Io looks compared to Europa. And it's thought that Europa has a global underground ocean. So that's pretty exciting as well. I'll come back to the ocean aspects of the moons in just a few moments. Next in line, this is Ganymede. So this is the topic of the observations that you've been looking at today, and the shadow of Ganymede going to be moving across Jupiter. And Ganymede is a fascinating object for multiple reasons, which I am going to go into a bit more detail about. So I'm just going to keep it simple for now, but I'll give you a fact that Ganymede is known as the planet-sized moon, and I'll come back and explain why that is in just a moment. And then the last one in line here, looking quite different again compared to the other moons, is Callisto. So this is a sort of scar-covered kind of dark surface with white or paler impact craters on the surface. So they're all really fascinating in their own right. So we always say that actually these bodies that are orbiting so close to Jupiter are sort of like a miniature solar system with Jupiter at the centre, and deserve study in great detail. So these moons were discovered by Galileo, as I mentioned, an Italian scientist, just over 400 years ago. And since then, they've been studied by multiple different techniques, using even just simple backyard telescopes, by spacecraft en route to faraway destinations in the outer solar system like Voyager, and also with a dedicated mission that orbited Jupiter known as the Galileo mission. And as you can probably guess, this was named after this guy over here. So just to give you a little bit of context, Io is about the same size as our moon, and Europa is a little bit smaller than that. I've tried to put them to scale here, but they're probably not perfectly to scale. Ganymede is just about half the diameter of the Earth and is actually larger than planet Mercury. And it actually gets the prize for being the largest moon in the solar system. So more superlatives for the Jupiter system. Ganymede over here takes 3rd place in the solar system in terms of its size after Saturn's largest moon, Titan. So I could spend quite a bit of time talking about each one. But for today, given the time that we have and the topic, of course, I'm going to focus on Ganymede over here. Okay, so before I go on to tell you a little bit about the mission that we're sending to Jupiter and Ganymede, I'm just going to tell you about why we're so interested in this topic and some of the facts that we already know about the system, which drives us to send a space mission there. So first of all, we need to know a couple of things about how these moons interact with their parent planet, Jupiter, at the centre. And the first effect, which is really interesting, is all to do with gravity. Now, the orbits of Io, Europa and Ganymede form a pattern which is known as a Laplace resonance. And this is being shown on the left-hand side here. Hopefully you can see this. A little GIF of the moons moving around Jupiter, looking down on top of the plane of orbit of those moons around Jupiter. And this resonance causes the gravitational effects of the 3 large moons to actually distort their orbits into slightly elliptical shapes. Now that's not shown in this GIF, they're shown as circular. But the presence of these large moons near to each other and the presence of Jupiter in the center causes a very interesting gravitational effect. Like I say, it causes the moon's orbits to be slightly elliptical instead of perfectly circular. And so what that means is that, let me start this one over here on the right. What that means is that because the orbits are slightly elliptical, sometimes the moons are closer to Jupiter on their orbit than others. And this means that the surfaces are actually pushed and pulled to different degrees, depending on the point in the orbit. And this pushing and pulling on the surface, which is most significantly felt by Io and Europa, closest to Jupiter, massive Jupiter at the center. This pushing and pulling actually produces a source of significant heat in the interior. And actually that's how you allow, you can have liquid water underneath the surface, as I mentioned at Europa just a few moments ago. And that little movie there was of Europa being pushed and pulled in its orbit around Jupiter. And this is from the Europa Clipper mission. Okay, so that's the sort of gravitational effects that are going on and creating this interesting resonance between the moons and pushing and pulling and heating of the interiors of the moons themselves. The second thing which is really interesting about the Jupiter system, Jupiter itself and the moons, is to do with electromagnetism. So let me just explain a little bit about what I mean. So just like our own planet, Jupiter has a strong magnetic field. And the strongest part of it is quite a lot like the bar magnet picture that you may be familiar with for the Earth. And that magnetic field of Jupiter is generated deep within its interior. And here we go as another superlative. It's the strongest magnetic field in the solar system. The strength of Jupiter's magnetic field is 15 times stronger than Earth's magnetic field at the surface, or cloud tops for Jupiter, because it has no solid surface. And its magnetic moment is 20,000 times stronger than that of Earth. That magnetic field then extends out into space surrounding Jupiter and is actually stretched out by plasma mass coming from those volcanic moon, the volcanic moon of Io. So as I mentioned, Io has lots of volcanoes and it produces material that is dumped into this rotating magnetic field. So all of this produces what's known as a magnetosphere, and Jupiter's magnetosphere is the biggest in the solar system, of course, and all planets that have magnetic fields have a magnetosphere. In fact, you're sitting in one right now. So Jupiter's magnetosphere is the largest in the solar system, and just this little picture over here gives you a rough demonstration of what it would look like if you could see it in the sky. We can't, because you can't see magnetic fields. But if you could see it in the sky, if we could somehow illuminate Jupiter's magnetic field and magnetosphere, it would be significantly bigger than the disk of the moon or the sun in the sky. Okay, so the magnetosphere is controlled by the magnetic field of Jupiter, which is rotating around with the planet, which I mentioned was the fastest rotation rate of all the planets at 10 hours for a Jovian day. And so the magnetic field rotates around, and the material coming from Io, which forms the plasma, the mass within that magnetic field, sweeps past all of the moons, particularly the Galilean moons shown in this sketch here. You can see the magnetic field lines, Jupiter in the center. This will be spinning around every 10 hours and producing an interaction with each of those moons. So that's really a fascinating effect that takes place. Now, I'm a little bit biased because I was involved in the proposal for the new mission, which I'm just going to describe to you. But for me, Ganymede is the most fascinating of the Galilean moons because it has all of the features and such diverse features for us to study. So it has the largest number of different types of crater on any planetary body in the solar system. It's thought to harbour a subsurface ocean beneath the icy crust. And it turns out it has its own internally driven magnetic field, just like this bar magnet over here, just like is produced at the Earth. And we don't know very much about it, but that's why we decided we had to send a new space mission there to help explore these incredible features. So the Jupiter Icy Moons Explorer mission is the European Space Agency's first mission to Jupiter. So that's very exciting in itself. And because of all those interesting features that I described and many more that I don't have time to describe, the plan for the mission evolved over a number of years. And the European Space Agency's mission, known as JUICE, a slightly contrived acronym, as you can see from the title, is going to be launched in June of 2022 and is going to be arriving at the Jupiter system towards the end of 2029, beginning operations science data collection in 2030. And the goal of the mission is to study the Jupiter system in general, to focus a little bit on Europa and Callisto with some special flybys during that mission. But the real focus of the mission is Ganymede. And in fact, JUICE is going to be the first spacecraft to go into orbit around an icy moon. So the final part of the mission will see JUICE actually in a very close orbit of Ganymede, and that is going to give us an opportunity to collect the most fantastic detailed observations of that moon. So the science themes are unlocking the secrets of the icy moons, particularly focusing on the fact that we think they have subsurface oceans, and also studying Jupiter as a kind of blueprint or an archetype for similar planets, gas giant planets in general, and those that we know exist beyond our solar system. So let's just have a little think about Ganymede and its underground ocean. So this was actually discovered from the Galileo mission that I mentioned previously. And observations that we have so far suggest that that ocean could be up to 100 kilometers deep. So that is significant. If you think about it, that's 10 times deeper than any ocean on our planet. And as I described, Ganymede is quite large. It's bigger than Mercury. And so if you do the maths, you can work out that the volume of water for a global ocean of 100 kilometers deep within Ganymede's subsurface would produce a volume of water which is 8 times that which we have on planet Earth. Now, once there's a possibility that there's water somewhere, then of course we know this is a vital ingredient for life. And it leads us to think about the possibilities of life potentially forming in subsurface oceans that are heated by tidal interactions with Jupiter in the outer solar system. And that is a fascinating question and is the focus for some of the missions that we're seeing now, JUICE included. So how did we work out that there might be a subsurface ocean at Ganymede? Well, interestingly, it was the Galileo magnetic field data that showed us that Ganymede might have a subsurface ocean. And I've tried to sort of show this with this nice sketch here, but what was measured was a very subtle but significant perturbation in the magnetic field that was measured by the Galileo spacecraft as it flew past Ganymede on multiple flybys. And there was this perturbation in the magnetic field, which in the end could only be described by a layer underneath, or either on top of or underneath the surface of a conducting substance. And Ganymede doesn't have a significant atmosphere with a conducting layer like our planet does, known as the ionosphere. And so it's thought that, or a logical conclusion was that this perturbation, this change in the field, could be coming from a conducting ocean underneath the icy crust. The next thing that was discovered about Ganymede on the Galileo mission was that it also has its own interior magnetic field. So again, like this dipole magnetic field that's generated within the Earth's core. And that was a real surprise. So it has a combination of an internal magnetic field plus a field that changes that's due to the ocean. And then if you put those things all together, and remember that you have Jupiter at the center of the system, rotating around rapidly with that very strong magnetic field, what we actually find is that Ganymede has a magnetosphere of its own, generated deep within Jupiter's magnetosphere. So we have a miniature magnetosphere within a magnetosphere. Now, this is a quick movie of, I hope you can see this, of the JUICE orbit. So this is the final orbit around Ganymede of 500 kilometers. Now, that orbit has been designed specifically to give us the information that we need about the precise details of that magnetic field and also of Ganymede's gravity field. And we can also study the surface and get fantastic imaging from that orbit. So that should help us to answer questions about the field that's generated within Ganymede's core, but also the field due to the ocean. And if we can understand the field due to the ocean better, along with other measurements from JUICE, then we can learn more about the properties of the ocean. Now, I'm hoping I've just got time to play you this. The magnetic field of Ganymede was actually confirmed by various observations, one of which I'm hoping to sort of play you now. So these are some plasma waves observations at Jupiter's moon Ganymede, taken by the Galileo spacecraft, and they've been sort of compressed in time, and the pitch has been changed such that we can hear them with our ears. So you wouldn't hear this if you were near to Ganymede, but the frequency of the waves have been changed so that we can listen to what's become known as Ganymede's singing magnetosphere. So I'm going to play this and see if you can hear it. Hopefully you can hear those 5 pitches increasing in frequency, and that's where the spacecraft is getting close to Jupiter, getting close to Ganymede, moving through the magnetic field line, getting stronger, and you can hear the same deep pitch after. And then you can hear the frequency coming down as the spacecraft is moving away. So this is the first indication of confirmation that Ganymede has its own magnetic field. And another thing that Ganymede has as well in its very tenuous, not very dense atmosphere is its own aurora. So I'm not sure if you've been talking about aurora already this morning, but Ganymede has its own auroral emissions at the northern and southern poles. And this is an image taken by the Hubble Space Telescope. And on the right, you can see an artist's impression of what that might look like when we get close up. This study over here by Joachim Sauer and colleagues also showed that they think that the auroral ovals will actually rock according to the field that is produced due to the subsurface ocean. So we may actually be able to use the auroral emissions to help us understand properties of the ocean as well. Okay, so the Ganymede orbits from JUICE are slightly larger and slightly more elliptical. These are the ones that come before the final orbits, which I showed you just a moment ago. So hopefully if this just gets into orbit, you can see an elliptical orbit. So this phase comes before the 500-kilometer orbits that I showed just a moment ago. And this phase has been particularly designed so that we can study Ganymede's miniature magnetosphere as it interacts with Jupiter's bigger magnetosphere, and we can understand Ganymede's aurora as well. So we're coming towards the end now. I just wanted to show you, this is an image of the aurora in Jupiter's upper atmosphere. You may have seen this already this morning, so I apologise if I'm showing this again. The wrong wavelength, according to Tom and his favourite infrared. This is ultraviolet imaging of Jupiter's auroral emissions in the northern hemisphere. And I just wanted to point out very quickly a couple of features. We've got a main auroral oval, which goes almost all the way around. It's much neater on this side than over here. But what we also see are footprints of the moons. So this strong emission here is the footprint of Io. And over here you can see a footprint of Ganymede, and this one is Europa. So those moons are magnetically connected from their orbital plane to the upper atmosphere of Jupiter through the magnetic field and particles are accelerated into Jupiter's atmosphere, causing aurora. So we can study what's happening at the moons and the interaction, the electromagnetic interaction, by looking also at Jupiter's aurora. And so JUICE also has a high inclination phase of the mission. Start that playing. This is a little harder perhaps to see, but you can see that the orbit is subtly changing. It's sort of moving down out of this plane here, which contains the moons orbiting around Jupiter, and is into an inclined orbit. And once you crank the orbit up, then you can look down onto the poles of the planet much more easily. So we'll be able to simultaneously move around the system close to the moons, studying how the moons interact with the immediate environment, but also have an opportunity to look at those bright auroral emissions in Jupiter's atmosphere. I forgot to say they were the brightest in the solar system, of course. And we'll be able to study how that large interaction takes place between the magnetic field connecting through to the moons in the orbital plane of Jupiter. Okay, so just to finish up, here's the timeline for the mission. As I mentioned, JUICE is going to be launched in 2022. It takes about 7 years to get there, so we have to be pretty patient, maybe do some other things whilst we wait, and then Jupiter orbit insertion. And the first phase of the mission is to study Jupiter itself. We then have a couple of Europa flybys, and then the orbits will be reduced down, and part of that reduction maneuver will mean that we can fly past Ganymede and Callisto multiple times on what are called flybys, before finally moving into those, first of all, elliptical orbits around Ganymede, and eventually moving down to the 500-kilometer circular orbit at the end of the mission. Okay, so we always thought, well, I say we because I was lucky enough to be involved in writing the proposal for this mission, which was accepted by the European Space Agency. And we finished our proposal presentation by saying that we felt that this mission was our sort of next logical step. From the discovery of the Galilean moons in 1610 by Galileo Galilei, through to the Voyager missions studying the solar system in the 1970s, the discovery of deep habitats at the bottom of the Earth's oceans where there was no light to produce energy for life to be created. We found that there were in fact deep habitats in the dark at the bottom of the oceans. And then we also had the Galileo mission, the Cassini mission, the discovery of water worlds beyond our own solar system. And so we think that now was a great time to send a mission to discover more about Ganymede and the ocean worlds of the Jupiter system. And who knows what's coming in the future, possibly landing on one of these moons would be an excellent next step, perhaps. But as I say, we have to be patient and wait until the science begins in 2030. So for those of you listening who are perhaps young and at school and considering going to university to do physics or space science or what you're thinking about for the future, then consider that in 2030, we'll be looking for some PhD students to come and help us to analyse this data. Okay, so I'll leave it there. Thanks very much.
Thank you, Professor Bunce. That was a fantastic synopsis of like past, present, and future observations of Jupiter. We definitely have some questions. I know there was a hand up from one of our Zoom attendees. If you want to ask a question in person, you can put your hand up, but please do write your question in the chat box so that we know what to expect. But I can get straight to one. We have a few minutes left if you have some time for us.
Yeah, sure, that's fine.
Okay, great. So I think Nick has been waiting around for a while to ask this question. Will NASA's Europa Clipper or ESA's JUICE mission be able to make any further studies to these areas of research, or are they going to be only looking at the moons? Maybe you've already answered that.
Yeah, it's a good question because, you know, we have a focus on the moons and the subsurface oceans, but actually in order to get to those little moons and to get into an orbit, takes quite a while and quite a lot of hard work to get the spacecraft there. So whether you like it or not, actually, you're going to spend quite a lot of time within the system more generally. Now, of course, that is a good thing, because that means we do have time to study Jupiter more generally and the other moons along the way. As I mentioned for JUICE, the first part of the mission is the spacecraft is in orbit around Jupiter to begin with, and so we're getting a tour of the Jupiter system, and we get a chance to look at Jupiter's atmosphere and study the magnetic environment of Jupiter more generally. And then as the orbit reduces down in size to get closer to where Ganymede actually sits in the system, there'll be multiple flybys of Europa and Callisto as well. And so we'll get an opportunity to study almost every aspect, I think, of the Jupiter system that we could want to do from that particular orbit. And then we end up in an orbit very close to Ganymede, which we cannot come out of, and so the spacecraft will end up crashing into the surface of Ganymede at the end, on purpose. Not an accident.
So here's a question about Io. Besides Amalthea, are there any other moons orbiting inside the orbit of Io?
Oh, that's a good question. I'm not an expert on the small moons. Maybe some of the other guys from Leicester know more than I do. But yes, there are certainly a few small moons within the orbit of Io. I can't remember their names. Amalthea is certainly one. Yes, there are a few, and they actually are interesting because they are within the very intense radiation belts and very strong magnetic field region of Jupiter as well, and so that sort of thing can affect their surfaces. So yes, there are nearly 80 moons in the whole system.
And maybe the other astronomers can take note of that question for later, but we're about to get back to an update in a little bit, but a few more questions. Amy asks, does Jupiter's magnetosphere provide us with details about the planet's core?
Absolutely, that's one of the things that you can use the study of the magnetic field for. So we will do that at Ganymede with JUICE, and the Juno mission is currently doing that with Jupiter. So Juno is in a very close orbit near to Jupiter. The closer you get, the better. So really you get as close as you dare, you get the best measurements of the magnetic field, because it gets stronger the closer that you get to the source region. And so if the source, or where the field is produced, is inside the planet, you want to get as close to that planet as you can to get the best knowledge of the field. So Juno is very close to Jupiter, and you can measure the magnetic field very accurately. And that tells you about, once you build up a model of that magnetic field, or a picture of the complexity of that field, it gives you information about where that field is generated, whether it's right within the core alone, or whether there are in fact regions where the field is being generated. And so some of the data from the Juno mission hints at the fact that there could be a core field generated deep within Jupiter's center, but that there could be other regions that are generating magnetic fields also. So it's a really complex process. And in fact, one of the interesting things is that the generation of magnetic fields appears to be, or at least the field that is produced, is different for almost every body that we've studied in the solar system. None of them are the same.
Wow, well, thank you so much. We need to get back to, we have you're welcome. Thank you for, well, first, Professor Bunce, thank you so much for joining us in your very busy schedule. And we're going to get back, you're welcome to stay with us if you have the time, but we're going to check in with the team in a little bit, but I wanted to share my screen just to kind of give us an update on where we're at in the schedule. Just to let you know how far we've come so far, what we've been doing. So we've had a little telescope issues initially, and seen through those. And we've just finished, we just had an update on science from Dr. Stallard and a Q&A with the team. And we've had Dr. O'Donoghue join us as well from Japan, from JAXA. And we just finished with an incredible, wonderful synopsis of all the observations of Jupiter from the early times to now. So, and also to the future. So what we're going to be looking forward to in the future missions with JUICE. So moving on, we have now a check-in with Dr. Stallard and Dr. Melin. And again, we'll also have a second Q&A with them. So if we didn't get to your questions this time, Nahid will get to them in a second. Actually, in between, we're going to check in with them, and then we're going to hear from Dr. Prosser, the RAS librarian, about some more things about Jupiter. So let me unshare my screen, and you guys can take it over. Thank you.
Perfect. Okay. I guess the first thing that we need to do is try and show you what we're seeing on the telescope. And we're taking some fantastic data, it has to be said. I'm very keen to show you something of what we've gotten. I don't know whether we're able to get that up on the screen. Hopefully, Emma can pull that up. So this is the guide camera that we're looking at here. A beautiful, highly colorful image of Jupiter, and you can see we're zoomed right in. We've got this fantastic view of all of the atmospheric bands of Jupiter. The bright band at the equator is the equatorial region that is reflecting a lot more sunlight. The brightest spot you can see in the region just above and to the right of that main band is Ganymede, and that's reflecting sunlight off of the surface of Ganymede. Because it's reflecting the sunlight off the surface, that sunlight can't hit Jupiter's disk, and so there's a region where the sun is not hitting Jupiter, and that's forming a shadow immediately behind them, and it's causing an eclipse, just like the eclipses we get on Earth every so often as the moon moves in front of the face of the sun, and that's resulting in a small shadow, and you can hopefully see that just to the right, to the left, sorry, of the big bright spot that is Ganymede. Let's see if I can even get a little arrow up to show that. Here we go. Nope. So, just as we move into the night side. So what I'm seeing right now is a whole lot of nothing, and that's very intentional. As we said earlier, because the Earth's atmosphere is so hot, it's very bright, we have to take that out. So every so often we'll go to the night sky that has nothing in it and take data there. And then when we take data in a region where there's nothing, we're able to get some view of what's going on. For me, I've come back now, and you can maybe see a small hole in the light coming back from Jupiter, where my mouse is here, where the line is pointing, and that's the shadow of Ganymede on the planet. And so that region, there's no sunlight, and that's really important for the science that we're doing, because we're trying to look at how the ionosphere at the top of the atmosphere is being absorbed by the sun and creating lots of ions, making an ionosphere. If we switch the light off, then the ions aren't being made anymore, but they're still being destroyed. And so we'll see a change in the ionosphere. And then when the shadow disappears again, the light switches back on, and we're able to start making ions again, and we'll see the creation of the ionosphere. So we're really trying to understand the creation and destruction of the ionosphere, basically as a way of understanding what happens on the day side and the night side of the planet as a whole. And it's the only way we can really effectively do that from Earth. So that's what we're looking at. I don't know, Emma, if you can get the view of the instrument, the spectrometer, up. I've got a hand up. She's going to be working on that, and hopefully we can get that up so I can show you actually some of the science that we're doing. And
it's now up. Bear with me.
Perfect.
I just need to resume.
That's much less interesting, certainly much less pretty than these fantastic images that we're taking, but is actually the point of why we're here. And it's that thin bar that you see over the image. That thin bar that we see is the hole in the mirror that we're taking to take images. The light's falling through that hole, and that's going into our spectrometer and spreading the light out and allowing us to take scientific measurements. And that's what we're seeing in this new image. You can see that we've got a lovely big box that shows us what's going on in terms of the instrument measurements. And this is the spectrometer. So you can see a nice green box and then a line. Let's explain everything that we're seeing. So there's some lines in the horizontal and lines in the vertical. There's these two wide bars at the top and the bottom here. That's boring nothingness. That's where the instrument isn't taking any data. Inside of that, we're taking data from Jupiter, and it's black. The reason it's black is all of the methane in the lower atmosphere is absorbing all of the light. And so you should see loads of reflected sunlight. Other wavelengths, you can see lots of reflected sunlight. And if I move over this way a little bit, we can see a region where that is happening. Over here, we have a region where there is a whole lot of sunlight at certain wavelengths shining back at us. You can also see a horizontal line all the way across in the middle. That's reflected sunlight from Ganymede. We're clipping Ganymede and we're getting light. And sunlight is at all wavelengths. It's not got a narrow spectra. It glows in all sorts of wavelengths, so it looks like a very thin spot that's spread out in wavelength. So wavelength is left and right, like a rainbow, spreads light out from red to blue. And then the vertical is the spatial information across the planet. So at this point here, we've got lots of light in all sorts of different wavelengths spread out in the rainbow from the reflected light from Ganymede. And on the atmosphere of the planet, a lot of those regions are really dark because the methane is causing global warming at Jupiter. It's sucking up all of the sunlight and storing it as heat in the planet. Just below this long bar, you can see that there's a gap in the reflected sunlight over on the right-hand side. That's the shadow of Ganymede on the planet. So there's no reflected sunlight because the moon is in the way and it's causing that region to be shadowed. So that's what we're seeing in terms of the planet and reflected sunlight. Over here is a very much thinner, sharper line, and that's a particular molecule, a molecular ion we talked about earlier called H3+. It's a very simple polyatomic ion that we understand the way it vibrates on a quantum level really well, and we know that there has to be a specific way that it can emit heat out at a very, very narrow wavelength. This is an incredibly thin line of heat coming out from the ionosphere. So that, unlike everything else here, that's a very specific view of this very transitory region of the atmosphere right at the top. We're getting this source of light coming through. And what you can see is that we can see that across the whole of the slit. The slit's sitting right on the ionosphere now. So we're seeing the ionosphere from end to end in the slit. But there is a region, and that's where this line has been drawn on, where the shadow was. And hopefully what you can see, if I move that line out of the way, you can see that the ionosphere is dipping in brightness in that region. The ionosphere sits above the atmosphere. The light that we're seeing from it isn't sunlight, it's the fact that it's hot. So it shouldn't really change a lot in temperature in the short time that the shadow takes to cross it, because it's being heated by all sorts of different processes. We don't really understand all of those processes at all, but we know that there's all sorts of additional heat sources, not just the sun. So it should be always the same brightness. You should have the same amount of ions there that are being heated up, and it should be completely uniform in the amount of light that it puts out. The reason why it's darker in that region isn't because of the sunlight directly, it's because the sunlight isn't making ionosphere anymore. The sunlight isn't turning the neutral molecules into ions, and so the destructive processes in the ionosphere are eating away the ionosphere in that region. It's disappearing, and then on the other side, you switch the sunlight back on and ions are being made very quickly again. So this is telling us something directly. It's telling us, and this is something we haven't known at all until maybe a hint of it last week, the fact that this lines up so well with the shadow, it means that the ionosphere is being regenerated incredibly quickly. If it was a very slow process of making the ionosphere, that shadow would be very smeared out. You would see a much longer train of darkness away from the region of the shadow, but we don't see that. So this is the first time ever we've been able to say, actually, in this region, the sun is generating the ionosphere very quickly, probably on a scale of only a few minutes. Some predictions were as long as 10 minutes or 20 minutes in this region. So that's fascinating. That's proven some modelers wrong. I'm always happy when we prove modelers wrong as observers. That's our job. And it's confirmed other models. So that's why we do this, right? Understanding what's going on inside of that spot region, how quickly it's decaying away, is going to be more difficult because we're going to have to try and pull apart exactly what's going on in that region. But we're seeing it decay away. We're seeing the effect of the fact that the ionosphere is being drawn down. So that tells us at least it has to be happening on a time scale of 50 minutes, 40 minutes, which is what all the models predicted, but it's nice to show that that's true. If the ionosphere was able to exist for 3 or 5 hours, which, you know, is not anything anyone predicted, but sometimes the unpredictable happens. And if that had been the case, we wouldn't see that shadow at all. So we've got some really complicated stuff going on in here. It's quite hard to explain, but the fact that there's a dip at the same place as the shadow on the planet really tells us that the ionosphere is doing something very interesting, and we're starting to actually get answers that for decades we haven't had answers to. So it's very exciting.
Is there any way, I think that's just great to be able to see that. Do you know yet, or do you have to wait until you get all your data to know if you're kind of answering the question that you're looking for with H3+?
So there's 2 questions that we didn't know the answer to. One is, how quickly is the ionosphere destroyed? And the other is, how quickly is the ionosphere generated? So just eyeballing this, I can tell that I don't think the predictions that the ionosphere is generated slowly are real, are realistic. So the way that you make the ionosphere is you take your neutral atmosphere, which is 2 atoms of hydrogen stuck together with a bond. It's molecular hydrogen, H2, and you whack it with something energetic. You ping off an electron, and it makes this stuff called H2+, which is just 2 protons and 1 electron bound together. Some models predict that almost straight away that's going to hit into more hydrogen and immediately react with it. Other models predicted that it would take quite a long time for that process to happen. So if it took a long time for the H2+ to hit more H2 and make this molecule called H3+, which is what we're looking at right now, the brightness from that, then if that process was slow, then the hole generated in the ionosphere by having the moon move over would mean you'd deplete the H3+ completely, and it would take ages for you to regenerate. And we're not seeing that in our spectra. We're seeing it fill in really quickly, because we see a dip that's very similar to the dip from the shadow in the reflected sunlight. So it's sort of mapping 1-to-1 to where there's sunlight. So that's really exciting. That shows us that it's being generated very quickly, which is a result that we've never really had, a constraint that we've never really had before. The other question of destruction, how quickly is it being destroyed? Well, we're seeing that it's being destroyed relatively quickly. The time it takes for the shadow to move across the disk is about 50 minutes. We need to do a lot more work before we can get down to the point where we really understand that destruction rate, because our time resolution here by eyeballing it is 50 minutes or so. And we know that it's shorter than that, but all the models predicted it was shorter than that. Some models are predicting 20 minutes and some predict maybe 2 or 3 minutes. So there's going to be a lot more slow and careful analysis to really pull that out. And hopefully what we'll be able to do is really frame that question in a lot more detail. We'll be able to provide an understanding of what's going on, not just on this primary level, but there's also lots of other ways that you could potentially make H3+. You can make H3+ not only out of neutral atmosphere, but you can make it out of lots of other kinds of ions which have a longer lifetime. So we might be able to constrain that. There's also predictions that maybe just as you get precipitation from the aurora down at these lower layers, there might be other sources. Emma talked about the radiation belts, and this region maps to those very energetic regions of space. And so some people have said those radiation belts will leak into the top of the atmosphere and make H3+. So far, we have no evidence of that. By modeling this really accurately, we might be able to say that that's the case, especially when we combine it with our Callisto data, which has a shorter timescale. So if we can show from Callisto that most of the ionosphere should have disappeared in most of this data, then if there's any H3+ left after that, that means that that has to be generated by something other than the sun, and it will give us a measure to that. So I'll be working on this data for quite a long time before I can get all of those answers out. But it's nice that we can see at least one answer directly in this data.
I just wanted to let our viewers know, and you, Dr. Stallard, that Dr. Sean Prosser is here. We're going to introduce her in about 10 minutes. So there is still time to discuss what's going on and what we're observing, and maybe check out Dr. Donohue's great animation in visible light, and or talk about maybe the significance of the observations we're making today, something that hasn't been able to see before. And why was that? Like, we had this unique opportunity today to get this data, and I'm so glad that the telescopes were ready for this observation, because you were saying earlier we might have to wait another year, was it? So if you can kind of go over the significance of this observation today.
Well, I mean, it's really significant for us because there's been a lot of focus on understanding those bright aurora at the poles, and more recently, maybe in the last few years, maybe 2 or 3 years, what we've realized, basically because we've started to get instruments that can finally see these equatorial regions better, is that it's not really a surprise. Jupiter is always profoundly complicated and weird, but we've always sort of shorthandedly said anything away from the aurora is kind of uniform and boring, and there's not much going on there, mostly because we couldn't see anything there. So it's very easy to pretend that everything is simple and you understand it when you can't see it. But some of the really fantastic work that James O'Donoghue's been doing in the last few years has shown that not just Jupiter, but other planets like Saturn have profoundly unique and weird and wonderful equatorial processes. There's stuff going on in these regions that are just really odd. Some of them are actually not odd at all. If you look at Earth, Earth also has all of these fantastic features in the equatorial regions. We're all used to thinking about aurora and how it's important to go to the North Pole to see all of the wonderful kinds of aurora that you've got in your background behind you. But actually, when you look at Earth studies, there's all sorts of really interesting effects at the magnetic equator and various magnetic anomalies. And Earth is incredibly boring in its magnetic field compared to Jupiter. I think one of the people asked why the aurora is messy on one side at Jupiter. Well, that's harks back to what Emma was talking about when she was saying that maybe there's 2 magnetic fields being generated at Jupiter. That was a shock to everyone before Juno. There were models that maybe suggested that, and people were ridiculed for even thinking it, because it's so profoundly different to anything that we have at any of the other planets. The idea that you could have 2 magnetic fields being generated inside of a planet was somewhat silly to most people. But in fact, Jupiter does seem to have this very complicated magnetic field that's very unique, very interesting, and that's allowing all of this complexity and dynamics. And using this light from the equatorial regions, we're able to start seeing those because it changes the brightness of the ionosphere. So in order to understand that, we need to understand these regions. We need to be able to understand how quickly things are generated and destroyed, because if we're seeing brightening and darkening across the disk of Jupiter because of these weird and wonderful magnetic effects, without knowing anything about how it's created or destroyed or the timescales it's created or destroyed on, it makes it almost impossible to really understand what we're seeing. So we need to get back to basics. We need some basic values so that we can put those into models and get effective measurements out. But we have no measurement for that. Not only do we not really understand what those values are at Jupiter, we don't understand what they are for the molecule H3+, because measuring H3+ is incredibly difficult anywhere but Jupiter because it's so incredibly reactive. So in order to measure it in a lab, you have to have these fantastically complicated lab systems. There's one in Chicago where Professor Oka's lab is able to measure in incredible detail the measurements of H3+ using spectrometers on Earth, but those are incredibly constrained because it only needs a few atoms or molecules of oxygen or nitrogen to get in there, and you'll lose all the H3+ that you have. So measuring how it's created and destroyed in the lab is quite difficult. So what we're hoping is that at the first level, we'll be able to measure what's happening at Jupiter and understand what's happening at Jupiter. But if we're able to do this well enough, we may even be able to use it not only as a planetary measure, but also as a kind of like a lab measurement, a way of measuring what we're able to do. And we've done that before. Our measurements of the wavelengths of emission at Jupiter are as accurate as any on Earth in the lab, because our instrumentation is not necessarily as well positioned to measure, but we've got this wonderfully bright source, whereas anyone on Earth has to deal with horrible vacuum chambers and the difficulty of trying to make a lot of H3+ without having it destroyed again, whereas we've got all of the H3+ we will ever need glowing away in the top of the atmosphere of Jupiter.
So we still have a few more minutes. Is there anything that maybe Dr. Melin or Dr. Donahue want to add?
Yeah, one thing that really strikes me with these observations is that we can see the shadow even in the raw data. And that's something I'm really encouraged about. Sometimes you have to process data really hard, especially away from the aurora, like we are here, where H3+ is really weak. But the signal we're getting today here is actually really fantastic. So I think we're achieving our science goals here together, as it were, which is lovely.
Yeah, I have a. There was an earlier question about if there was any moons inside the orbit of Io. This is the kind of thing that I would usually forget the names of, but yeah, there was Amalthea is one of them. There's actually only 4 moons inside of Io, and all these other 60, 70 odd moons are actually outside the orbit of Ganymede. And actually, the 4 moons that are on the inside of Io are actually suspended in Jupiter's main rings. And so Jupiter does have a ring system, but it's kind of basically like a really weak dust. So that you don't really see it in any normal observations. You have to be really looking hard to find it. So hopefully that answers that question.
Okay, so Emma has pointed out a question to me on YouTube, which was, if H3+ is depleted in the shadow, would not the surrounding area diffuse into the shadow? And that's sort of true. You expect things to move around, but what you have to remember is the enormous scales that we're talking about here. The shadow of Ganymede is, I think we were saying, about 1/3 of the diameter of Earth. So if you think about how fast winds can blow on Earth, how long would it take for a wind to move atmosphere from one part of the atmosphere to another? And to make it move 1/3 of the Earth's diameter, it's going to take a very long time. So we can take that into account, but and often when we're looking at the auroral regions, that potentially becomes interesting. But the lifetimes of H3+ on somewhere between 10 and 20 minutes would require very, very fast winds to be able to make it move. Some of the winds we measure in the auroral region are pretty fast. They're in the order of kilometers a second. So if you have a 2 kilometer a second wind, that's going to take that's going to be maybe fast enough to start moving things on that time scale, because if you times it by the number of minutes, and then so if you're looking at an hour, it's going to be 3,600. So a 2 kilometer wind is going to move that far in an hour, say. But in a period of 10 minutes, even those very fast auroral winds are going to struggle to fill in that hole. But we don't expect those very fast winds in this region, because those winds are generated by all of these auroral currents making everything move around, and we can see those currents as a result of all of this really bright aurora. Down in this equatorial region, we're not going to get winds that fast, especially shearing in the winds that fast. And so you're going to struggle to make things move around. And so it's very unlikely that you would get filling in. potentially you could, and potentially that's something that we could actually resolve out once we analyze the data in more detail. But we hope that that's not the case for here, because it certainly seems like there's a significant hole in the ionosphere, which is what we're seeing now. That wouldn't be there if those winds were very strong. They would bleed through and fill in that hole, but we're not seeing that right now. So I think we're still able to see the shadow on the disk of the planet, or what you can see in the guide camera. We're starting to move towards the dusk limb, and as time goes on, we're going to be able to start seeing Ganymede move above the limb, and then ultimately we'll see the disk of Ganymede move above the limb too. That could be a very interesting time for us, because what we're able to do on the very limb is see the ionosphere in profile on the edges. And so we're looking through a much deeper path of the ionosphere and get a much brighter signal in that region. So potentially what we hope might happen is, as the shadow moves over that edge of the planet, it will block out that light through a much deeper path, and we may see a whole region fall into darkness at the same time, rather than this localized spot. And that might give us another source of information about how these processes are happening. We tried it with Callisto last week, and maybe we saw something. I'm not sure. We haven't had a look at the data yet. We certainly tried it back with Io on the Very Large Telescope in Chile. That was an 8-meter telescope, and we had adaptive optics switched on. But unfortunately, we were looking at Io, and Io moves even faster. It shoots across that region, and so certainly when I looked at that data, I wasn't able to get anything back, because we literally had 1 or 2 spectra when we were doing that. So my hope is that using that, we'll have another source of information that will feed into what we're doing. But you can see that we've moved along to maybe 3/4 of the way through the path, but there's still more time. We're still going to get more data. The other thing to say is that, you know, we've got this slit cutting through the whole of the region of Jupiter. At the moment, it's covering maybe pre-noon all the way to dusk. And obviously the focus of the observations right now for us is that spot. But all of that data is going to be really interesting to look at too. Right now we're seeing a scan, and it's often really hard to get data on telescopes for boring things. That's one of the unique aspects of astronomy. This is a really interesting result, and I was very confident we would get time, because I was able to sell it in the way that I was able to sell it to you guys. Chasing the shadow of Ganymede across the disk of Jupiter sounds really interesting, and we were able to sell the science that we could do. But at the same time, we haven't got a lot of information about the boring bits around that. It would be very hard to sell to a scientific community that we want to stare at a sort of boring region of Jupiter for a whole half of a night. But we're doing it anyway. And so what we're hoping we can do is, away from that spot, we can measure what the brightness of the ionosphere is as it moves from dawn to dusk. How does it change? And also we're covering quite a lot of different latitudes as well. So we'll hopefully be able to measure what the latitudinal changes are dependent on the magnetic fields that you get. So as with a lot of the work that we do, there's all sorts of different aspects that you can pull out that aren't necessarily the primary science target, but still give you really interesting and unique science as a result.
That's fantastic. Thank you so much for that update. And I hope we don't miss too much. We're going to go on to our next speaker. How long do you think we still have left to see, before I go, how long do you think we still have left to observe the shadow before it leaves the face of Jupiter?
I think we have a little while. Henrik, do you have the timing?
It's in James's video, isn't it?
Yeah.
Sorry if I kept you on your toes there by asking that question.
I've noted this down.
Well, I just want to make sure that we're going to be speaking with Dr. Sean Prosser, our RAS librarian, looking at some archive imagery illustrations, and make sure that we get back to you. We have a second check-in at 2:30 p.m., so hopefully we won't miss
Yeah, by my calculations from a week ago, which might be wrong, we should still be seeing it on the disk until about 10 to 3.
Excellent.
It's about 10 to 3, I think. Yeah.
Excellent. Well, thank you so much. Joining us now is the Royal Astronomical Society librarian and archivist, Dr. Sean Prosser, and my colleague, very happy to be able to say that. She will be sharing with us some images of early observations of Jupiter from the library's collection, and there will be an opportunity to ask her questions, so please get them ready. Welcome, Dr. Prosser. I believe you have a presentation for us. You're welcome to share your screen when you're ready.
Thank you. Is that working now?
Yes, you just need to go into, I guess, presentation mode.
Slideshow. How is that looking to you?
You're not in presentation mode. I'm not sure what this mode is called, but we don't see your full
Okay.
screen.
How about that?
Yes.
Okay, brilliant. Fantastic. Well, thank you so much, University of Leicester team and Lucinda, for inviting me to take part in this live stream today. It's just been fantastic to hear about not just the live observations, but the live interpretations being carried out by astronomers as we look at this amazing event of the shadow moving across the surface of Jupiter. So it's not been possible for some time to welcome people physically into the library, but we have been able to, conduct a few live streams and welcome people in and still keep sharing our collections. So this is the interior of the library. This is just an example of some of the amazing books and manuscripts that we have in our collections. We've been around for 200 years and we've been collecting books and manuscripts and observations by astronomers, not just from 200 years ago, but from the medieval ages, all that time. And it's our great pleasure to share these with you. So I've selected just a few images that might be relevant to people interested in the history of observing Jupiter. Starting with one of the most famous, which is Galileo's original observations of the moons of Jupiter, which Professor Bunce mentioned during her presentation. So he was one of the first people to publish his observations of, telescope sightings of the night sky. And he didn't just talk about Jupiter, he talked about his observations of the constellations, of the moon. He showed these sort of geographical features, the valleys, the mountains. And at the end of the book, we have this really fascinating section where he talks about, several weeks of observations where he observed something very interesting happening with the moon. I'm going to read a translation of the beginning of this section. We've got 3 different editions of the Starry Messenger in the RAS library, so it's quite good to be able to show people all the different multiple views of this sort of big program of observations at the same time. So he says, accordingly, on the 7th day of January of the present year 1610, at the first hour of the night, when I inspected the celestial constellations through a spyglass, Jupiter presented himself. And since I had prepared for myself a superlative instrument, I saw, which earlier had not happened because of the weakness of the other instruments, that 3 little stars were positioned near him, small, but yet very bright. And although I believed them to be among the number of fixed stars, they nevertheless intrigued me because they appeared to be arranged exactly along a straight line and parallel to the ecliptic, and to be brighter than others of equal size. And their disposition among themselves and with respect to Jupiter was as follows. And he's used these asterisks and capital zeros to show how the positions of the planets move each night. So you can tell that something really interesting is happening. He says, quoting him again, I therefore arrived at the conclusion, entirely beyond doubt, that in the heavens there are 3 stars wandering around Jupiter like Venus and Mercury around the sun. This was at length seen as clear as day in many subsequent observations. So it was just a great leap of insight to not just regard these as three fixed stars, as he calls them, but to work out, just from the way that they behaved along a sort of fixed plane, that they were orbiting around another planet. And this was just an absolutely revolutionary discovery. However, he wasn't the only person looking at Jupiter in this level of detail. I'm going to introduce another historical astronomer now, Simon Marius. You may have heard of him. He published a book called Mundus Jovialis in 1614, in which he claimed to be the first to have discovered the moons of Jupiter. Now, when Galileo found out about this, he was not very pleased, but he waited another 8 or 9 years until he published a book in 1623 calling him a massive plagiarist. But Simon Marius was a German astronomer who was perhaps treated a bit unfairly, because he did have access to a telescope. He'd purchased lenses from Venice, he'd constructed it. It's just that, first of all, he didn't publish as quickly as Galileo, but also he was using a different calendar. He was a Protestant, he was using the Julian calendar, and Galileo was using the Gregorian calendar. And scholars have examined Marius's observations, and they've revealed that he discovered the moons just one day after Galileo. However, Simon Marius was the person who coined the names for the moons of Jupiter. So familiar, we've mentioned them a lot today: Ganymede, Io, Callisto, Europa. However, the names they were not used generally, that they were not commonly used for hundreds of years after this. They kind of fell out of use and weren't used extensively until like the 19th or 20th century. So moving on to later in the 16th, 17th century rather, this is a special request from Dr. Tom Stallard to show an image of the observation of the shadow of Jupiter, of the moon, a moon passing over the surface of Jupiter from 26th of June 1666. And this observation was made by Robert Hooke, who was one of the preeminent scientists of the 17th century. And he was most famous for his book Micrographia, in which he published really intricate observations using his microscope. There's a famous picture of a flea, and he also made detailed observations using his telescope. There's some beautiful moon craters, for example. He was a very active member of the Royal Society, and this is a publication from the Philosophical Transactions of the Royal Society, where he's basically published his observation of the shadow of the moon moving across Jupiter. So moving onwards to the 18th century, we're going to talk to somebody who's very special in the history of astronomy and in the history of the society in general. This is William Herschel. Many of you will have heard of him as the person who discovered the planet Uranus in 1781. He was also a great theorist. He had he really sort of pushed forward the ideas and the thinking about how the universe is constructed. But also, he just carried out a really extensive observation program, and he was our first president in name only, because he was president in 1820, just a couple of years before he passed away. So he wasn't able to take the chair personally at a meeting. And we're so lucky to have many of his astronomical observations in the Royal Astronomical Society archives. So I'm going to share with you some of his observations of Jupiter itself. We've been talking a lot about the science, but all of us astronomers throughout time we're not insensitive to how amazing it is to look at these celestial objects. And here from 1777, William Herschel says, Jupiter was uncommonly beautiful this evening. He talks about the science, he talks in great detail, but he's really moved by the beauty of this planet. And this observation was made only a couple of years into his well, it was a hobby at that time. He was a musician, he was working and living in Bath, but he was basically a self-taught astronomer, and he was making his own instruments. I think it might have been the 7-foot telescope that he was using to make these observations. And in his early conversations with astronomers like Sir Thomas Hornby, who is the astronomer at the Radcliffe Observatory in Oxford, he was asking them questions like, well, what is the best way of observing Jupiter? I'm really interested in looking at immersions. That's what he calls that phenomenon when a moon of Jupiter moves out emerges from behind the disk. So, you know, this was just the start of his astronomical journey. I'm going to show you some more observations. This is moving into March 3rd, 1778. And in the bottom right hand of the page, you can see he's talking about a shadow again. But what's also interesting are his observations of like an emerging white belt that makes its way across the center of the planet. And I've just done some rough close-ups of this, so you can see, you know, as he started observing at 10:30 and then 10:34, 10:51, 11:14, just really brings home how fast Jupiter revolves. So you can, I don't know if you can see here we have the edge of this new white belt, and it's moving its way gradually across the disk. So these observations by William Herschel, it was right at the beginning of his career. He didn't actually publish anything. It was his discovery of Uranus that really helped him to make his name, and he became a full-time astronomer, basically. He moved to Slough, and he was made, he basically lived in a place that was very easy for him to be able to travel to Windsor Castle and set up his, by now it was a 20-foot telescope he was using for observations, and have star parties basically with the royal family. But 20 years after this, in 1797, I believe, he did actually publish his observations of Jupiter in the Royal Society proceedings. And he was able to share even more detailed observations because he was using a much bigger telescope, the 20-foot. And for example, he made a particular study of the changes in the relative brightness of the 4 satellites. And he could see that the intensity kept changing in a regular repeating position that depended on their orbital positions. So he theorized about this. It might mean tonal variations in the surfaces of the planets. And he also theorized that the planets had different magnitudes, and that was because they had different sizes. And he correctly provided evidence that Ganymede, or as he referred to it, the 3rd satellite, because remember, people were not at this time generally using the nomenclature, the naming system that Simon Marius had come up. The 3rd satellite is considerably larger than the other 3. So I'm going to move on to the 19th century. Now, just to give you examples of the richness of the observations that we have in our archives. But by now, it's not just a few lucky astronomers who've got access to the technology of telescopes. There are more people taking it up in their spare time. Telescope technology is more accessible. And the Royal Astronomical Society has a collection of 231 drawings mounted on loose sheets dating from 1856 to 1901, which has got a series of absolutely beautiful drawings and paintings of this planet Jupiter. This is one by J.G. Barclay, and we have another by Miss Hurst, another set of drawings actually. She was observing in 1875. I believe she was based in New Zealand, and she actually, Auckland, New Zealand, it says, and she actually had her observations, or at least the mention of the observations, published in our journal, the monthly notices of the Royal Astronomical Society. So that's just one of several hundred exquisite drawings that we have. And, you know, we're still capturing that sense of wonder now as we look at this amazing sort of transit of the shadow today. So I'm going to stop sharing now, Lucinda. I can see that there might be some questions and comments in the chat.
So the chat, we have a Q&A box, so you might be looking at.
Oh, okay, good.
There is a question for you, Dr. Prosser. So
Yeah.
Thank you so much, first of all, for sharing that with us and telling us a little about the RAS. It is our 200th anniversary, so, and unfortunately we weren't able to go to Bath. That would have been amazing, but we're so excited and happy that Leicester's come to us and created this opportunity and for you to share with us. Okay, so Dr. Prosser, here is your question. I see your video's off, but I think you're still there. Just want to make sure. Okay, great. So what they ask, what is the earliest observation we have of the Great Red Spot, either as a drawing or a written note by Eddie Carpenter, he asked. Do you have any idea?
I can't remember the exact date. I should have had a note of this, but I believe Giovanni Domenico Cassini from the Observatory of Paris was the first person to observe the Great Red Spot. Although there is some controversy here. Some people have asserted that Robert Hooke was actually the first person to observe it. So if you look at the literature, you can see the discussion about who had priority there. I think the general consensus now is that it was Cassini in the mid 17th century who discovered it.
And I know that recently we had some part of our collection for the sky at night. We had that they some images of the sun, I believe, some sunspots. Is that correct?
Yes, that's right. So viewers in the UK, you can still look at that episode of Sky at Night on the iPlayer. We're very pleased to provide some background imagery of sunspots to that program. They just go by the flash. The BBC Sky at Night editors did a lovely animation of a set of sunspots, you know, in a time lapse moving across the surface. So yeah, we have sunspots running from 1819 to the end of the 20th century, basically. And part of the discussion in the program was, you know, how can we use historical sunspots to improve our understanding of the cycle? There's an astronomer called Tsuyoshi Hayakawa in Japan who's been going all over the world looking at sunspot records, including one from 1140 in a medieval manuscript, and just looking again at what we can tell about the solar cycle. So yeah, it's just fascinating that scientists and astronomers and solar physicists today are still drawing on historical records for original research.
As one of our attendees here, Stephen, has mentioned that he looked it up really quickly. He says Jupiter's Great Red Spot was first observed in 1831 by amateur astronomer Samuel Heinrich Schwab.
Ah, thank you, Stephen. In fact, Schwaber is he is the person whose sunspot records are actually in the RAS archives, and they featured in the Sky at Night. I think there might be, I might need to do some more research here. I think there has been more than one red spot, and there's debate as to whether one merged into another or whether it was two separate storms. So,
if any of our esteemed guests, Dr. Donahue or Dr. Stallard or Dr. Melin, want to chime in, you're more than welcome to. We were chatting about all the amazing things you were showing, so I have a feeling that Dr. Donahue might want to ask. He was saying he was so gripped at seeing some of the illustrations. Go ahead.
Yeah, I remember looking this up maybe, I don't know, a year ago, and I think was the consensus about the Great Red Spot being observed about nearly 400 years ago now. And then there was kind of an observing gap, and then it was observed again. And that gap of hundreds of years makes it very unclear whether or not it's the same spot, or it disappeared and came back, or maybe it did something altogether weird, which is probably what happened. You know, it's shrinking and growing as well. That's another thing. Actually, I have it on my shoulder here too. I'm not very good at this side. Yeah, so I think it's bigger here than it is today. Actually, I think this is an image from maybe 20 years ago or something like that. But yeah, it's very interesting.
Yeah.
So my mother is an enormous Robert Hooke fan. She's a big fangirl for Robert Hooke. So I was delighted to be able to find a direct link back. And interestingly, in that Royal Society letter, the immediate letter after that is a report about Robert Hooke seeing a bright spot on the disk of Jupiter. So that may be the Great Red Spot, or it might be something else. We don't know. But certainly people have been seeing significant features on Jupiter's disk for a very long time. And it does suggest that there's this really interesting dynamics going on. Saturn is very rare that we see anything like that, and so it's really interesting why there's such a big difference between those two worlds. And Saturn has enormous storms every 30 years and then they disappear again, whereas Jupiter happily carries on with enormous storms for hundreds of years.
One of the things I'll add is the persistence of this storm. Basically, it's like in a conveyor belt of two bands of winds going either way, and so it's just continuously rolling along. You can have that persist on Jupiter pretty easily. There's not exactly any landforms or anything that are breaking it down. Like if you have a hurricane on Earth, you're going over a mountain or any land actually, that's when all the hurricanes, typhoons and everything, that's when they dissipate. But on Jupiter, there isn't really any kind of friction to stop it. So it just carries on. And it's always been fed from below in a mysterious mechanism as well.
Dr. Melin, did you want to say anything? There is a question in the queue, so just wanted to give you an opportunity.
Where is it? Sorry.
Oh, no, I have a question in the queue for Dr. Prosser. I just wanted to yield to you if you had anything you wanted to add or say.
No, I'm all right for now, yeah.
Okay, no worries. You're probably very focused on observing Jupiter. I'm sure. Sorry to get you out of your focus there. So, so Dr. Prosser, I've got a question here that, and maybe any of the other panelists can answer it. I saw the moons of Jupiter were used to calculate the longitude of Earth, on Earth. Do you know who created this protocol and when?
I'm answering. I might be completely wrong here. Is this Cassini again going to French Guiana to calculate longitude?
It might be.
Yeah.
It's certainly very, very long ago. It's some of the very first observations. When you look them up in the Royal Society papers, the very first observations of Jupiter, this is when the moon disappeared. This is when the moon reappeared, because, mathematically they told us something about the Earth. And we're very selfish people, usually. We are much more focused on the Earth than other worlds. So whenever we can use planetary science to tell us something about where we live, it's profoundly more interesting to us, which is understandable, I think.
Okay, well, I want to thank you, Dr. Prosser, for joining us and sharing with us those amazing illustrations. I was sort of yelling at the screen. I wanted the pictures bigger, bigger. I wanted to see detail in those beautiful illustrations of Jupiter. And what was the medium they used? I think was one used, it looked like it was colored pencils.
Well, William Herschel was using pen and ink. It wasn't really until the early 19th century that people started using pencils for observations. And in the 19th century, watercolors, ink, pencil, just a variety of media. I also wanted to say it's just so appropriate to be talking about William Herschel, who discovered infrared on the day that we're using an infrared telescope. I just realized that.
Absolutely. There are a lot of great connections. I mean, just Stephen Miller, in doing some of my looking up about this, he was the first one to what did he observe? Was it H3? Was H3 plus in the atmosphere of Jupiter? He's been working with us for our bicentenary for RAS 200. I remember last year, 2019, I was doing a demonstration on general relativity, and he came straight up to me, and I had him watching me as I did it, and he said, "Yep, that looks good." I felt that was the most sweat I ever had at working at RAS. But but just all these connections, and Tom, you worked with him. It just sounds like an amazing just experience here, being a part of it. So thank you so much.
Yeah, I mean, Steve was part of the original team that discovered H3+ on Jupiter. It's a really interesting story, actually. It's been told a few different places, including in some of the Royal Society papers. Basically, the people were looking at the upper atmosphere, neutral upper atmosphere, in fact, looking for specific lines, and they found all of these other strange lines that no one could predict. And at the time, Steve was not an astronomer. He was a theoretical physicist working out the kind of background quantum mechanics and doing the quantum mechanical calculations of where emission lines from this molecule H3+ could be. And the reason he was doing it was that computing had finally caught up to the point where this more complicated molecule could actually be measured and modeled in a computational way. So he was working with Jonathan Tennyson, who is a theoretical physicist at UCL at the time, and people came to them saying, "Do you know what these lines are? We've got these weird lines." And so Steve, being Steve, went, "I can tell you, but you have to let me come to the telescope with you." And ever since has been an astronomer. So thanks to that, everyone here has a job, because we've all come through. Henrik was one of his students, I was another, and then James, Emma, and Nahida are all my students. So they're his effective grandchildren. And then if you look up the line, if you go far enough, J.J. Thomson, who discovered H3+, was one of our doctoral antecedents. And then further than that, Newton was one of our doctoral antecedents. So this, as with all things science, we stand on the shoulders of giants, and the work continues.
Amazing.
We stand on the shoulders of giants with a telescope. It's even easier.
So you're welcome to stay with us, Dr. Foster. Thank you so much for your time and sharing with us some of the collection that we have at the Royal Astronomical Society. And hopefully sometime soon, we'll be able to invite some of these wonderful panelists we have with us to come and see the archives for themselves. But who knows when that's going to happen, but you're welcome.
I look forward to that day.
Yeah, thank you so much. So it's nearly 2:30, so we're going to be moving on. I'm going to just kind of give you a quick recap of who we are and what we've been doing. So I'm going to share my screen really quickly here, just to show that. And of course, there we go. Trying to see. Okay, so we are currently chasing shadows at Jupiter, a live stream telescope observation from the summit of Mauna Kea, happening live for you. And we have several guests and scientists, Dr. Tom Stallard, Dr. Henrik Melin. Thank you, Dr. James Donahue, for joining us. We've heard from Professor Emma Bunce with a fantastic past, present, future of Jupiter, and just heard from Dr. Sean Prosser, who shared us some amazing illustrations of early observations of Jupiter. So hello, and we only have about another half hour of observations of Jupiter, so we should check in again with our astronomers and see how things are going. I think Henrik has been really focused on them, so maybe he could give us an update, and we will also have a second session to ask them questions. So get them ready for Nahid, who will start the Q&A at approximately 3 p.m. And don't forget, if you want to tell us where you're from, give us your name. We'd love to know where you have joined us from. So I'm going to stop sharing my screen and hand it back over. Let's see if I can do this. I don't seem to have a cursor. There we go. I did it successfully. So Dr. Melin, Dr. Stallard, it's all yours.
Great. Thank you. So the shadow is quite close to the limb now, another, 20 minutes to go before it pops off. We're quite low in the sky. The telescope is angled quite a bit because Jupiter is setting in the night sky. And so we only have at most half an hour left at Jupiter. But the observations are looking really good. The spectral data show clear evidence of a dip in the ionosphere. So H3+ is being lost where the shadow is, which is exactly what we were looking for in this experiment. So that's really encouraging.
Yeah, and you can see the guide camera on your screen now, hopefully, and you can see that the bright disk of Ganymede is now moving away from the disk of Jupiter. It's on the limb as we speak. So the broad shape of Jupiter gives you that dusk limb for Jupiter, and the moon itself is now hovering above that limb. But as we said earlier, we're slightly offset from the sun, and as a result, the shadow of Ganymede falls slightly to the left, which means the shadow itself is still on the disk, and you can see it as a small dip. There is an arrow, well, a line, a vertical line pointing towards that shadow. Hopefully you can see a nice dip in the brightness. And that means that as long as that shadow is on the planet, we can continue to do observations and take more data. If we can see the instrument, the spectra that we're getting at, we can see some of that detailed measurement that that Henrik was talking about in terms of the kind of details that we can see, and the fact that we're actually able to observe the ionosphere itself and see it fading away. So if I just pull that up for myself, I don't know if we can see that yet. Hopefully we can.
Yeah.
So you can see it's changing color scheme very violently right now. So it's moving it around. Let's see if we can get it to a color scheme that works more effectively.
Yeah. Maybe not that one.
Well, as long as it holds at that, that will work really well for us. You can see a sort of cross on the image, a vertical line and a horizontal line. As we said earlier, the horizontal line is the moon, Ganymede, reflecting sunlight back at us. So the sunlight is hitting the planet and reflecting back, and sunlight, the sun, because it's hot, it jostles around, and you get basically a blurring out of all of the different species in the sun's atmosphere, and you end up with a black body radiation. Some of you will have heard of the term black body. It's basically a continuum of sunlight across all the wavelengths, and so that hits the surface of Ganymede, and most of it reflects back and gives us this continuum of light. And so in this spectra, left and right is wavelength, and up and down is the spatial information coming through the slit that we saw on the guide camera. And so there's just a reflected sunlight continuum from the quite small moon. And so you can see that horizontal line being Ganymede itself. The vertical line is the ionosphere of Jupiter. It's a very narrow emission line from the molecule H3+ that we were talking about a little bit ago. And so what you can see is that that is a continuous line across the region that we're looking at in the atmosphere. And very, very clearly, about maybe 20 or 30 pixels below that horizontal line is the shadow region, the region where the sun is no longer illuminating the surface of the planet. So in reflected sunlight, that would very obviously just be dark, but we're looking at a thermal emission from the ionosphere. We can see that thermal emission on the night side and the day side. When we're looking at the auroral region, for instance, we see the aurora just as bright on the night side as on the day side. It doesn't matter which side we're looking at. So if the ionosphere was there, we would still see it even though it's in the shadow. But the green box that's been drawn around that, you can see very clearly shows that that region is empty. It's not empty directly because the sunlight is not on it. It's empty because the sunlight isn't making H3+, isn't making the ionosphere in that region. And so the processes that destroy the ionosphere are still going. They're still eating away the ionosphere, but there's nothing generating it. And so as a result, we're seeing the ionosphere die away in the shadow of Ganymede, which is exactly what we wanted to see. That's telling us how a lot of information about how the ionosphere changes when you go from the sunlit side to the night side. And so we can use this as a way of understanding the night side of Jupiter without being able to see it, because we just can't see it from Earth. So that's a fantastic result. It really is very clear. We don't even need to reduce our data to be able to see that clarity. It's when we do the reduction and the analysis that we'll get specific values out about how quickly the ionosphere is destroyed and how quickly it is regenerated. But you can see that there's a lot of information in there that we're going to have to work towards trying to understand. There's many months and years of work in terms of taking what these raw spectra are and turning them into scientific answers about what's going on in the ionospheric region. But it's nice. One of the really nice things about doing planetary science is often the answers you get back are very immediate. We can see things happening live on the planet. When you're studying distant objects, often they change over timescales of years, decades, centuries, and you're trying to understand the context from multiple different objects. Here, we're looking at Jupiter in situ, on the fly, in an hour, 2 hour long event, and we're producing fantastic science that hopefully you can all see. So that's a really nice result for us. It's certainly a lot cleaner and deeper a hole than we were able to measure last week when we looked at Callisto, and that's because Callisto has a much faster motion against the background of the sky than Ganymede. So you're in darkness for about half as long, which means there's less time for you to eat away the ionosphere and bring it back. So by comparing those two, we're going to be able to find out even more science. So I think it's fair to say we're all very happy with these observations. I don't know if there are any questions that people have asked that we can answer. Nahid, have you got any questions queued up?
There are a few, yes. So there was one earlier from Amy, which unfortunately couldn't be asked, but I'll ask it now. So Amy asks, do we know if there is anything inside Jupiter between its thick gaseous atmosphere and liquid metallic hydrogen core?
Well, it's a really interesting question. I think maybe 3 or 4 years ago, we would have been able to tell you the answer to that without many doubts about how much we understood about that region. But what the Juno mission has done has thrown all of that into significant doubt, because our expectations of what the magnetic field of Jupiter were like and our understanding of the underlying layers really were much simpler 3 years ago, before we had the richness of data that Juno has given us. One of the real limitations for understanding the interior of these worlds is that we can't see it. Even with the Juno instrumentation that is much better at penetrating deep into the atmosphere, deep is really only the very narrow surface layer. The only way we can understand the interior of these worlds is basically using similar techniques that we use at Earth. But of course, we can't use seismology as we do at Earth, because there's no surface, there's no shaking. So the only techniques we really have are to measure the gravitational pull of different parts of the planet by having a really detailed understanding of the changes in an orbit of a spacecraft, or by measuring the magnetic fields of those that Jupiter produces. So by using gravity and magnetic field, we can start breaking things apart. But before Juno, there were no spacecraft that really ever went close to Jupiter for a very extended period of time. So that's the reason why Juno has completely revolutionized our understanding, because the first time we've had lots of orbits really close to the planet. So it's mapping out the magnetic field and gravitational pull in much more detail. And it's really shown that the magnetic field is not simple, like perhaps the Earth could be seen as being simple. There's multiple components and maybe even 2 different regions of generation, which means something weird is happening inside of Jupiter. I don't think we're at a point of really understanding what that weirdness is yet, but as the Juno mission continues, it will continue to map it out in more and more detail. And then people will take that data and turn it into magnetic and gravitational models, and be able to perhaps understand that complexity in a bit more detail.
Okay, thank you. I've had another question from someone that's anonymous. So we've mentioned Uranus, and this person is interested in knowing about some of the science that we do at other planets, apart from Jupiter. So,
a lot of the science that we're doing here is similar to the science that we do at other planets. We've talked a bit about the aurora, and I showed a while ago some of the movies that we've made of Jupiter's aurora. We are equally interested in all of the gas giants and how those differ and vary. And of course, Nahid, you know all about that as someone who is currently working on Saturn. Emma is currently working on Uranus. The only planet that we really don't have a deep understanding of is Neptune, and that's despite all of the attempts that we've made. very recently, Henrik did a several night-long observation of Neptune in the hope that we would see something. We've never seen any H2 plus from that world, and despite many hours staring, we've still not seen anything from Neptune. So that itself is a mystery, why Neptune is so dark. And so all of these questions are equally interesting at other worlds. And what is fascinating is that each world appears to be almost entirely unique. Saturn has really weird aurora that are completely different to any other aurora in the solar system, maybe driven by the upper atmosphere's winds in part, which is very odd. The equatorial regions, which is work that James has really focused on the equatorial regions of Saturn, are completely dominated by material flowing in from Saturn, from the rings of Saturn, rather than anything else. So a completely different story. Uranus is weird because the magnetic field lines are completely diverse compared to any of these other planets, and so the aurora are at the equator effectively. So again, a completely different and unique world. So the more that we understand about each of these worlds, the more we understand in general about them. But there's always more work to do. What this kind of work in the equatorial regions has really shown is that there's always more to do. Until maybe 5 years ago, we just thought that the equator was a boring region and we focused on the aurora regions just because that's all we could see in detail. But now, as instrumentation has improved, we're starting to see the variations that were always there and the complexity that's always been there, and fantastic new results, like the fact that the great red spot seems to throw energy up into the top of the atmosphere, which is work that James O'Donoghue showcased a couple of years ago. Really fascinating new insights into the way these upper atmospheric regions work. And it just again highlights that, these worlds have a very different environment than Earth. Earth's upper atmosphere is mostly just doing what the sun tells it to do. And these worlds are such strong and powerful atmospheres that it's this complete interaction between what's happening underneath and what's happening above. And it causes all of these feedbacks that are much more complicated.
Excellent. Well, it looks like the shadow is getting closer and closer to disappearing. Shall I hand back to Henrik or Tom?
Yes.
You guys can
Do
continue.
you want to talk about what you're seeing?
Yeah, we're right at the edge of Jupiter. Is it even hard to see because the sun is on the left? Is that right? I think that's right. And so we're seeing a shaded crescent. Well, we're not seeing a shaded crescent, but there is a shaded crescent of Jupiter right there. And so the shadow will move into that region and eventually off the disk altogether. So that'll happen in about 7 minutes. Like I said before, the telescope is really low in the sky, and that causes the telescope to jump about quite a bit. It's hard to guide on Jupiter, on Ganymede in this instance, when the telescope is low in the sky, just because there's lots of movement and there's lots of weight being carried by the telescope. We saw some pictures earlier of the telescope. It's absolutely enormous, and it's incredibly heavy steel telescope. But once we're done at Jupiter, we'll move on to observe a star. We use the star to calibrate our data, so we can convert the CCD counts on the detector to actual intensity units we need for the analysis to see how much the shadow of Ganymede has reduced the H2 plus population in the upper atmosphere. But after that, we'll go on to observe Uranus for an hour or so. And Uranus is really good, a really good target for this instrument. You can fit almost the entire Uranus system within this guide camera we're looking at now. So that should be quite a sight.
Can you tell us a little bit about what the position of Uranus will be on the sky when we do eventually move over to it? Will it be in a good spot or?
Yeah, so I think it'll be pretty much right at zenith. So
that's great.
So we go from very low in the sky, from very high to max, at zenith. The star will be somewhere in between those two. I did find a calibration star, similar sort of RA and DEC.
Okay. I've had another question that's just popped up. So someone's asked, would it be possible to see the aurora on Jupiter if you were standing on the surface of one of its moons?
It's a great
Okay,
question.
so on the surface of one of its moons, it depends where that moon is. So what we do know from some of the space missions that have gone there is that you can see a visible aurora, but it's much weaker than the sunlight reflected off of the disk of the planet. So it's going to be very difficult to see those aurora if you can see the rest of the planet because you're on the sunlit side. But when the space missions were able to go to the night side and see the night side, there are these aurora that are very similar to the ultraviolet aurora seen by Hubble. They're basically the same processes, just at a different wavelength. There is a filter called H alpha that a lot of people use to look at the sun. That's a hydrogen filter in the mid-red range. And using that filter, you can see a very bright aurora on the night side, a very thin arc of aurora. So certainly that would be seen, a red color. When we use spectra at Saturn, it seems like there's a combination of that and some molecular hydrogen that are sort of in the pinky purple range. So ultimately you would see a sort of pinkishy purple aurora above on the disk. But of course, it would really be hard to see because unless you're at the perfect position, you'd see this crescent of the sunlit side of Jupiter, which would be blindingly bright in comparison. So if you were able to hold your hand up, and of course you could do that on a moon because there's no atmosphere on the moons to blur things out. On Earth, we're used to the idea you can't really hold your hand up to the sun and block it out, but you could certainly do that on a moon without the atmosphere blending everything. If you hold your hand up and block that bit of Jupiter away and wait for your eyes to adapt down, and maybe you would be able to see the aurora directly, for sure. And it would be pinky purple in color.
Interesting. Okay, well, that's all the questions for now. I do invite our viewers to keep sending questions through. Of course, they can be about the science that we're doing. They can even be questions to our researchers, asking, you know, what our working lives are like, what we do day to day, that kind of thing. Wherever you like to ask, really. I don't think there'll be any limits on the kind of questions that we can take, as long as they're within reason, of course. I'm going to hand back to Henrik because it looks like the shadow is now getting super close to disappearing.
Yeah. You can see Jupiter is getting more blurry now as we get lower and lower in the sky. Still, we're guiding okay, which is encouraging. I can't quite see the shadow. Can you see the shadow?
No, but based on the line that we drew earlier, it does suggest that the shadow is basically right on the limb. So that means that we can't really see it in the reflected sunlight of the main atmosphere, but the atmosphere itself is at the same. We usually use the air pressure of Earth's surface, 1 bar, as a way of defining where the surface is, and that's pretty close to where that reflected sunlight is coming from. The layer that we're interested in, the ionosphere, is actually about 400 kilometers higher than that. So even though the shadow is right on the limb, it doesn't necessarily mean that it's passed out into that upper atmosphere layer. And we're interested in looking at that shadow as it crosses that region. So we're going to keep observing until hopefully it will have passed and we'll see the sunlight from the ionosphere lighting back up. But it's going to be a very, very tricky observation because, as Henrik said, we're moving very, very much down into the murky depths of the atmosphere now. The telescope is pointing over further than most telescopes, big telescopes in the world, are allowed to point. Some of them might have their mirrors starting to pop out at this point. Certainly most telescopes, you're not allowed to go this far down into the murk. But as I said earlier, IRTF is built out of an Italian battleship. It can do things that other telescopes can't. And so it's tilting very far over to be able to look at this murky end of the atmosphere. Nahid, is there any more questions?
There is one, which I'll just ask really quickly because I think we might be hearing from John Zarnecki at some point very soon. Just before we do, I've had a question from Amy who asks, what determined you to pursue a career in astronomy and what are some of the problems you have encountered? I think any one of us can have a go at answering this.
I think you're a bit closer to the raw edge of that. It's hard for me to quite remember why I did. Right. Now, Nahid, why have you decided to pursue a career in astronomy?
That's interesting. Well, the reason why I went into astronomy was I became really interested in looking at the moon when I was when I was in college, basically. And I borrowed a telescope. It was a 4.5-inch reflector Vixen telescope, I think, from the local Astronomical Society, the Leicester Astronomical Society, and I was able to look at Jupiter through there and Saturn. This would have been back in 2013 or 2012 when those two planets were fairly high up in the sky in the UK. And that really got me hooked, and that's what made me study physics and astronomy at the University of Leicester, and pretty much why I've ended up hanging around and working with Tom, Henrik, and everyone else on the team, you know, Emma, James, and of course Luke over in the US. So it was pretty much just a fascination with the moon to begin with. I wanted to understand why we had different phases. And once I got my head around that, I started becoming more interested in sort of planetary science. So that's my story anyway.
So what are the difficulties you've faced so far, other than me being mean to you?
Yeah, I mean, how long have you got? I'm joking. My route has been quite smooth, and I'm quite fortunate in that sense. I'm in a location in Leicester where, you know, we're very well known for the work that's done in sort of space science. In terms of, I suppose, real difficulties, I guess, would have been trying to get onto a PhD in the first instance when you're sort of applying. And sometimes you have to apply for projects that you might not necessarily want to do at other institutions, just so you have those offers on board. But aside from that, I think pretty much it's been quite smooth, and I can only be thankful for that. Really
good. Yeah, I mean, that is true. I think a keenness in science more generally is a very good way to continue. I was very interested in Venus and Mars's surface when I was an undergraduate, and someone, Steve Miller, we've mentioned his name before, said, "Do you want to do some astronomy?" So I said yes, and that's why I'm here now. Had I done what I dreamed of doing, I would have been looking at the surfaces of Venus and Mars, but thank goodness that didn't happen. I've got to know and love the wonderful molecule that is H3+ instead.
So Tom, oh, sorry.
No, please continue, James.
Oh yeah, Tom, your background was geology originally. That's correct, right?
Pretty much, yeah.
So when I explain that to people, I say, oh yeah, background in geology. Tom is a planetary scientist, so obviously he studies big gas giants. The closest you come to the geology is probably today when you're looking at Ganymede, or what it does, the rocks that get in the way for you.
That's absolutely true. And, you know, I have a colleague called Carl Mitchell who at about the same time as me was studying physics and was offered a PhD in the surface of Mars and Venus. So he went from being a physicist to being a geologist as I went in the other direction. And the great thing about that, of course, is that we can bring different skills to the roles that we have. So he made his career in doing physical models of volcanics. And a lot of geologists struggle a little bit with incredibly hard and complicated mathematics. I certainly do. So he was able to apply that physics to his geology. In a similar way, I've been able to apply a broader understanding of things like chemistry and processes to physics. And it gives you that kind of variability. The ability to adapt is really important in science.
It's also convenient that you would study volcanoes in the past, but then at Jupiter, the aurora is actually caused by volcanic things happening on Io, spewing out into space, finding their way in. So yeah, it's almost romantic that you've studied one thing, you studied volcanoes, and then you're studying aurora now.
Exactly. And one of the most recent things I've been doing is looking at possible missions to a moon called Triton around Neptune. And there is a very rich ionosphere that is probably maintained by the fact that there are plumes of volcanic material going out and filling up the atmosphere of Triton. So it always comes back around.
Right, and you observe from a volcano.
I do. Yes. The telescope right now is on the top of the most planetary-like volcano on Earth. It's the volcano that is most similar to all the volcanoes on Venus and Mars. So there you go. It's definitely a rich intermingling between geology and astronomy.
Absolutely. Thank you for your thoughts, guys. I'm gonna hand over to Lucinda, who actually has a very special guest ready for us.
Well, I don't know. He hasn't replied to my request to see if he would be willing to say a few words. So John Zarnecki, if you could hear me, I'm going to make a request to see if you would allow yourself to have your audio, your mic on, if you can maybe just kind of give us maybe your thoughts on what you've been observing today, or what do you think about this new world of digital, online, everything really. So I made a request. I don't know if he will turn up here and be with us, but he is.
Hi there, Lucinda. Can you hear me?
Yeah, thank you so much. How exciting. Wonderful to have you. Go ahead. What do you want to share with us? Say something.
Oh my gosh, you put me on the spot. Yeah, well, you saw my question, which is not really an astronomical question, it was a personal question. So can I try it?
Yeah, go for it.
So I've been watching, dipping in over the last couple of hours, off and on with my wife, Kate, who's very interested in astronomy, but doesn't have an astronomical background. And she had a very important question, which was for James, because my wife is an O'Donoghue, and so she was wondering whether James is a relative. So the question was, does James have any? So does James have any connection with the O'Donoghues from County Limerick in Ireland? It doesn't sound as if he has a very Irish accent, but maybe he's disguising it. It's disappeared.
I wish I had an Irish accent. I think I've disappointed people at conferences for about 10 years when I first speak, and they probably go, oh, okay. No, I've actually only been to Ireland once as well for about a week. But yeah, basically, my dad is half Irish, and his dad is Irish. And as far as I know, they're from Cork, actually. And we don't really have many contacts with them. So, I haven't really done any sort of recent ancestry or anything, but, there's not many O'Donoghues spelt in the same way either. There's a lot of O'Donoghues that have put an A in instead of an O, and they've got rid of the G. I don't know why there's a G in it anyway. Maybe you can tell me why there's a G in my name, a silent G. But yeah,
well, I think you've got the proper Irish spelling, so I think one's roots. It's something that you tend to get more interested as you get a few years older. So maybe 25 years time, you'll start delving into, where you all came from.
Definitely.
But anyway, I'll pass that on. I think Cork is the next county to Limerick, so could well be a connection.
It could be, yeah.
But anyway, perhaps I could just make an astronomical some comments. Is that okay, Lucinda?
Absolutely. I should say that John Zarnecki was our past president. So when I came out in 2018, he was just about to finish his 2-year term as president of the Royal Astronomical Society. And of course, you were part of the Cassini-Huygens mission. So, but yes, of course, we would love you to ask any question, John. Thank you so much.
Well, it's more of a comment, because I found this quite, it's taken me back, because I observed a few times at a telescope, and I wonder if it's still there, and I think it's next door to the IRTF, and that is UKIRT. Is it still there?
It is still there.
Infrared telescope.
It is no longer called UKIRT, of course, because we gave up the rights to it a few years ago as a country. But the telescope itself is still there and doing really interesting research. Yes.
Well, I was there observing in, I think it was 1982. it was 1 or 2 years ago, and we were observing some comets, and this was around the time, I mean, people might remember that Halley's Comet, it came to perihelion in 86, and it was discovered, I think, in 81. And of course, it was discovered in the visible, and nobody had ever observed it in the infrared. And there was a US group led by Martha Hanna from JPL, who had lots of time on the IRTF, and they were determined to be the first to pick it up in the infrared. And we had some time at UKERT to observe some other comets, and Halley was still extremely faint. And we had a little bit of time before our target comets were high enough to observe. And we'd taken the positions of Halley's Comet. And so though there wasn't really much hope of finding it, we tracked along where Halley's Comet should have been. And of course, there was nothing to see in the finder. It's just a blank bit of sky. But we tracked it and sort of added up the counts for about 30 minutes, and then went back and did the same track when the comet had gone to subtract the background. And when we did that, we found a 2.8 sigma signal. And I'm sorry, that's a bit esoteric for the non-geeks amongst us, but 2.8 sigma is sort of just on the limit of detectability, just about respectable. Anyway, it was the detection. And I mean, we were really chuffed because we'd beaten our American colleagues, and we published it as something which barely exists now, an IAU circular. This was pre-internet days, and it was the way of getting information out to the astronomical community. And anyway, that was my first time observing at UKERT, which is truly a wonderful site. And yeah, I must mention my collaborators. I remember Simon Green, Sharon Burkitt, and Andy Longmore. Anyway, in those days, observing was probably a little bit cruder than it is now, but and mapping of the coma of comets, the head of a comet and the tail. We didn't have infrared cameras, so you had a photometer, a simple instrument that just counted the light or added up the light, and we just moved it around, stepped it around in a raster fashion, the head of the comet. And yeah, so those were good memories, and there was good competition between the IRTF and UKERT. Anyway, so that's enough of my rambling probably, but and also I remember taking part in some of the very early remote observing runs, because of course then you had to go to the telescopes. And one of the interesting things about this session has been to see how I missed the beginning. I was on another telecon, but the observers seem to be scattered all over the place, everywhere other than the summit. In fact, perhaps you could tell me where are everybody? I just see them in places that look like they're living rooms rather than.
So the majority of us are in lockdown. It's still a little less lockdown today than yesterday, but lockdown in Leicester. So we weren't necessarily allowed out of our houses yesterday, but today we are allowed back. But we have not yet been allowed into pubs and restaurants as the rest of the UK are. James O'Donoghue is in Japan, in Tokyo. The telescope is obviously in Hawaii, and we have another colleague who has not come on yet, mostly because he's probably still having breakfast. He's in Boston. So we are very much spread over the world.
And do I understand that Henrik is operating the telescope?
That's right, yeah. So what is seen on the stream is one of the instrument panels that is what Henrik sees on the computer. So IRTF is one of the first telescopes to really push this. They were doing remote observing back in 2000 as a way of allowing people to observe from across the world. And it's it's one of the two ways that telescopes work these days. One of the ways that telescopes work is that you have remote observing. So Keck do that and IRTF do that. And the other is that you trust and rely on other observers to do your observations for you. So VLT mostly does that, but they do have a clause that lets us go and do observations. Gemini, UKERT do that largely. So there you are relying on other people doing your observations for you, which for a lot of astronomy works just fine because you're looking at field objects like galaxies. But we like to think that our observing is more difficult than that. So we like to be able to do it ourselves.
Yeah, I mean, stars and galaxies are easy, aren't they? And boring as well, compared with solar system objects. Though some people might disagree, I guess.
I guess some people will, yeah.
Wow, well, just fantastic to have you, John. Thank you so much for being with us. We also think, I'm trying to see if we have Steve Miller.
It's a pleasure. I hope you didn't mind my ramblings.
No, not at all. They're welcome. They're not ramblings. They're fantastic. And thank you for sharing with us. It's just been a remarkable day, and even more for having you on. So thank you so much.
Thank you.
So, nice to speak to family again.
Yeah. I hope I'm gonna mute your mic, John, and you're welcome to stay and check in with us if there's anything else you want to share with us. I was wondering if did we miss something? Was there something that happened? Henrik or Tom, is there anything?
It's muted, I think.
Okay.
Might be talking. Right now we're working on moving targets. So Jupiter is setting. It's getting so low in the sky, even IRTF can't reach it. And so we're going to do another really boring observation next. I talked about some of the boring observations we did before we even opened the telescope, which is to stick a light on that we understand is completely boring and uniform, to see what the instrument does in terms of its response. Another thing that we do really throughout the night is look at a really, really boring bit of sky away near Jupiter, but not at Jupiter, so that we can take away the Earth's atmosphere. The other problem that we have is we're measuring photons right now. So every time a photon hits the instrument, it adds 1 to the counter. And so we're just counting up photons, and that doesn't necessarily give us a good measure of absolute energy. To do that, we need to go to an astronomical object we really understand very well and measure that. And so that's what we're going to do next. It's called, it's a giant star. It's an A0 V star. And the reason we like A0 V stars is that they're incredibly boring. Even for stars, they're boring. They don't have very much spectra in them at all. They're very clean sources of just black body emission of light. They're very predictable in terms of what they will show us. So they're really important for us because they're so dull. That means that we should have a good understanding of what's happening there. And that means we can look at what light comes out from these stars and calculate what that means. So if we count 1,000 photons, we'll know what energy that relates to. So we can divide that amount of light energy per photon through all of our data, and it gives us not just a relative brightness on Jupiter, it gives us an absolute brightness. So we can use that to not just see the darkness, but we can use it to really understand how much H3+ we're looking at. So we can actually get column densities in the atmosphere if we are able to measure this accurately enough, which is, really useful because it will tell us the exact amount of H3+ and how it's died away with time. So really, really boring observations can be incredibly important. So that's what we're doing next.
This is sort of the whole purpose of this observation, isn't it? To find out about H3+. So I'm hoping you get what you need to figure that out.
Well, fortunately, it's generally a very easy observation. So this part is not as exciting, it's not as difficult, but it's just as important, really. Yeah.
I did want to, I know we're going to move on. Well, actually, I should say, they were still supposed to be doing a Q&A right now. I'm not sure if anyone has any questions. If you still want us to answer some questions, you want to be able to type them into the Q&A chat box or on YouTube. And apologies if we've missed you. We'll try to catch up on that. So it was amazing to have John Zarnecki join us. And earlier we had Steve, some guy, Steve as an attendee, raised his hand earlier. And if that happens to be Steve Miller, raise your hand again, please, because we'd love to have you on if it is Steve Miller. If not, we're definitely lots more to do and see. And we're going to be seeing Uranus after this. Is that correct?
That's right. So we have been allotted a certain amount of time on the telescope. They divvy up that based on all of the scheduling for all of the different astronomical objects. And what often happens is that there is a little bit of time when your object is set, but you haven't quite finished with your time slot. And sometimes that's when the best science of all gets done. It doesn't happen very often. Sometimes you don't get a chance to play around, but what we find is that those hours can give us opportunities to look at things that we might not have otherwise looked at. And, for instance, that is one of the ways that I started this experiment, because we had a little bit of time when there was no interesting aurora to be seen. And that's why we started looking at the equatorial regions a bit more, because the aurora had rotated out of view. And so what are we going to do? Let's look at the shadow of this moon. And that started us down this journey. Yeah, I do think there are some questions. Nahid, I don't know if you want to ask those questions. I saw a few on YouTube, so I'm happy to answer questions.
Nahid, go on.
I'm going to hand over to Emma, if that's okay. I think she has been feeding those YouTube questions.
Yeah, if that's cool. I had one from Star Tracker, who I apologize. I'll go for the second question because I think that will be nicer to try and answer. Basically asked, if we stripped away Jupiter from all of its gases, how big would the remaining rocky / metallic body be, and would this be bigger than Earth?
This is a really good question, and I'm not sure we're at a position to answer it yet. What's interesting is it's the hardest region of all to see. It's very difficult to see that region because obviously it's all based on the modeling of gravitational rotations. So the number that came before Juno was 0 to 5 times the mass of Earth. So there could be nothing, or there could be a planet that is 5 times as massive as Earth, that is made of silica and iron. And that was the limits of our understanding. What we do know is that, current theory about how planets form suggests there should be pretty significant bodies, because they have to be of some size to be able to start capturing all of the gas that it needs to make these really big worlds. But it's likely that Jupiter has a moderately sized super Earth at its core. As you move out further in the solar system, the cores seem to get bigger, which is also quite weird. So Saturn actually has a bigger super Earth in its middle than Jupiter. And then as you move out to the ice giants like Uranus and Neptune, you're including a lot of water and ammonia and ices, and those become very massive. And so those worlds, the ice giants, are actually mostly not hydrogen. But it is interesting because this has always been a theoretical question, right? What would you do if you stripped away the atmosphere? But what we're seeing now are worlds around other stars where that's a very real thing. There's a whole catalogue of exoplanets around other stars that sit really close to the star. And some of them seem to be sub-Neptunes, so they're like Neptune but smaller. And others seem to be super-Earth, so they're like Earth but bigger. And you can look at the two and see a definite separation in their orbital parameters. And it really looks like there is a whole catalogue of new planets being found that started further out, moved in, and were stripped in this exact way of this theoretical question. The sun was so powerful that it stripped out the upper layers. And some of the modeling of that is really interesting. It shows that hydrogen gets stripped away really easily, but water has this really high thermal energy, ability to hold heat and energy. So even if you superheat it, it's much harder to get rid of. So actually, if you have a planet that is smaller, made of water, or a much larger planet made of just hydrogen and rock, that hydrogen will be stripped away and the water will stick around for much longer. But ultimately, there's going to be a boundary between those two. So even though we've always talked really theoretically about what would happen if we strip away the atmosphere of Jupiter, it seems like there's a whole catalogue of worlds where that actually happened. Instead of Jupiter sticking all the way out at 5 astronomical units, the conditions in the early formation of those worlds meant that they migrated in to really, really, really close in, much closer in than Mercury, for instance, in our solar system. And they actually went through that process of having their atmosphere stripped away. So those worlds might be giving us a direct measure of what we would see at our solar system if we were able to theoretically strip away that stuff, because the suns of those worlds have done that. It's a fascinating new field that is literally 2 years, 3 years old. We didn't know any of that 3 years ago. So exoplanetary studies are amazing because of this wealth of new information that comes out year on year.
Awesome. Thank you very much for that, Tom. I'm afraid I don't have any more questions. So I might pass back to Nahid if you've got some more lying around.
There's one that's actually just coming in the Q&A box. I'm afraid I can't pronounce your first name, so I do have to apologize for that. But your middle name is Mendes, so that's the best I'm going to manage for now. The question is, do you remember from your high school what was the topic that most interested you in astronomy? And I think this one I'm going to ask you, Emma.
Oh no.
Is there a topic that interested you most in astronomy?
Goodness. I know there's the topic that I was least interested in, but that's mostly because I kept messing up my grades with it. I was not very good with dynamics, which unfortunately for physics is a very mainstream thing. So I ended up trying to do really well with it. But topics wise, I mean, I was always really big fan of electricity and magnetism. Kind of leads into being, really fascinated with magnetospheres. I think it helped with kind of the setup with in high school where we did have I think we had a couple more experiments with looking at bar magnets, the interactions like with Lorentz force, so looking at how forces can occur due to interactions between electric fields and magnetic fields. Yeah, sorry, I think I'm kind of about to go back into a circle, but I think that kind of answers on that one in terms of the topic I really enjoyed.
All right, thank you very much. There is another question.
Can I answer that question?
Yeah, please. Yeah, by all means.
So I think it's fascinating when you're really young. I think a lot of kids latch onto one or two subjects, right? They really love planets, or they really love dinosaurs. And my elder brother was a super big fan of planets and astronomy. So when I was really young, naturally, I hated them. I thought, who wants to study planets? Dinosaurs are where it's at. So maybe that's why I ended up studying geology and not astronomy. My brother was really interested in all forms of astronomy. His favorite planet was Jupiter. So obviously I hated Jupiter the most of all the planets. And then ultimately, of course, I ended up studying Jupiter as an astronomer. So you can never really follow through with your childhood dreams. My younger self would have been appalled at the fact that I'd chosen space over being able to study dinosaurs, but there you go.
It's not too late to change tack, though.
That's true. It's never too late.
But space dinosaurs.
I was super interested in quasars when I first started learning about astronomy, which are some of the most distant objects in the universe. And now I study the planets, which are our celestial neighbors. Quite a contrast, really, isn't it?
Yeah, my degree was in planetary science. So here I am. But I tried to get a PhD in looking at black holes and galaxies, which was kind of way off because my background is mostly atmospheres and planets and the solar system and the sun and that kind of thing. But I really wanted to do black holes and galaxies. That was so cool. But nobody had me for those things, which makes sense because all my experience is in planetary. And it turns out planetary was a good choice because if you actually get a telescope and you look at stars and galaxies and things, you're really just looking at what we're looking at right now on the screen, which is it's this all night, right? But when you do planetary observations, you get to see a huge disk. You get to see the rings of Saturn, Great Red Spot, moons going around, planets. Yeah, it's. I think it's much more visually appealing. It keeps you up easier on a 12-hour shift.
It's true. Whenever we're observing at a telescope, we often find the observers from the night, earlier in the night or later in the night, seem to hang around while we're observing, and you know, take pictures to send to their friends and family, which does suggest to me that what we're doing is kind of fun compared to a lot of astronomy.
My old housemate in Leicester, actually, he was a black hole scientist, but he used to record data in X-rays using an X-ray telescope, and you know, they would only receive a few photons entirely. That some people had their entire theses, their entire PhD based on one photon. So yeah, we've got a lot of photons. It's something to be proud of.
All right, I had another question. So can we suggest any robotic telescopes that people can use for class projects related to the work that we do?
That's a really interesting question that I am not sure there is a good answer to. Specifically the work that we do, possibly not, no. The region of the atmosphere, the wavelength region we look at, is really tough to look at without having someone working really closely with the telescope. Henrik talked about an exploding instrument earlier, and the reason it exploded was because it was warming up and it had coolant in it, and that coolant expanded. So in order to do the kind of science that we're looking at 3 to 4 micron, it's much more heat based than more visible wavelengths. And so you have to cool the instrument down, otherwise all you see is the instrument. So not only do you need liquid nitrogen, you actually need liquid helium as well to bring you down to temperatures of only 30 or 40 degrees above absolute zero. You need to do that, otherwise all you'll see is just the heat of the instrument itself. But that makes it much harder to do any kind of science with it, which is supremely frustrating, because I see the amazing work that gets done in the lower atmosphere of Jupiter by citizen scientists, and they don't just use visible these days. They do near infrared observations of incredible detail, but unfortunately I have yet to find a useful auroral line that they can see. I would absolutely love it if we could do that, because the science that they can do, the continuous monitoring that they can do, is really, really profound and important. There are robotic telescopes that let you look at those near infrared and visible wavelengths, but I don't have the details at hand. I don't know whether there's anyone else on at the moment that knows about those, but there's some amazing opportunities out there for that kind of science. I don't know if Lucinda is still around, whether she's gone off for now. She might know, but otherwise, I think there's some really good websites that detail this. Lucinda, do you know anything about robotic telescopes?
These, well, depending on what age group, so our GCSE astronomy students do need to use telescopes now. So we send them over to the National Schools Observatory, NSO, and they can register there to use their telescope. Open Learn from the Open University has a free astronomy course where you could use their COAST telescope on Tenerife, I believe. So those are actually the one, Open Learn. Anyone can sign up for that course and use that telescope if they, you know, to take some images. But those are the two that I know offhand.
Okay, that's really good though. Thank you. Nahid, are there any more questions?
There is a question, yes. I'll just have to find it. Ah, there it is. It's from Amy again. We've had a number of questions from Amy. Thank you very much for being involved for so long. So this question, she goes on to say, I know this question is not related to the main topic, but I've always been wondering, could a tidally locked exoplanet have liquid water on an area of its surface between sunlight and darkness?
I think it's really possible. Well, the one caveat to that really is the effect that you get at Earth. If you look at the Earth's atmosphere and you use the calculations of where heating happens on Earth, it should be all frozen. We're too far away from the sun for to have the melting point of temperature on the surface of the Earth. But the Earth's atmosphere redistributes heat through the areas, and it captures infrared light. The greenhouse effect, we always talk about greenhouse effect being bad, but actually, of course, without it, our planet would be frozen. It's just the excess of greenhouse gases that is the problem for us. That redistributes and heats the planet all the way across. So we don't have a night side that's frozen and a day side that's melted. And it's quite likely a similar thing would happen at an exoplanet that was tidally locked. There's a lot of modeling that talks about that. And the one side of the planet is always heated, but that allows you to redistribute heat all the way around the planet. So not necessarily that you would have that, but there are certainly possibilities. I see that James O'Donoghue is flaking out. That is because, by my calculations, it's about 2 in the morning in Japan, something like that. Is that right, James?
Actually, it's 11:26 p.m.
Okay, it's not too bad.
But I was up very late last night with a newborn. Yeah,
Yes.
yeah, new family here.
Fully
So
understandable.
I'm finding that it's. I used to think being up all night observing was tough, but actually it turns out being a parent is doubly tough. Doing both at the same time, I think it's I don't know. I'm flaking out because I'm just tired from the whole week.
Well, it's
Yeah,
been great to see you. Thank you so much for dialing in. It's really good that we can have a transplanetary observation of Jupiter. And I'm sure we'll see you again at some point soon. Take care. And
thank you for having me. It's been really fun seeing this. Very successful, science-wise and outreach-wise. Very nice. Thank you.
Thank you for
joining. Bye, everyone.
Bye.
Thanks, James. See you around.
See you, James.
Our observations always like this. It feels like a party, like we've had a Netflix party watching Jupiter. Ganymede.
It's a real range. I mean, sometimes we do have a kind of party atmosphere. Keck, you aren't allowed at the summit. You have to observe from down the mountain, so a town called Waimea. And so often we try and all come together for those observations. Keck time is the most precious of all telescope time in the world. It's something like $1 a second to run that telescope. So it's really important that you get that right. And so we often have Luke from Boston, James from Japan, and us from the UK all fly out so that we can work together. And there you do get that kind of party atmosphere, because some of us are doing the direct observations while some of us are analyzing the results that have already come in, because when it's $1 a second, you want to absolutely make sure you're grabbing the best possible observations. So some of us are sitting a bit apart and doing analysis as we go, so it has that party feel. Other times, it's 4 in the morning, no one else wants to drag themselves out of bed to come and observe with you, and so it can be a very isolated and quiet experience. I've walked through the park at 4 in the morning in Leicester before and just sat by myself for a few hours in my office, and so that can be quite a quiet and isolated experience. When you observe from the summit, it's never like that, because there's always at least the telescope operator with you. So that's one of the reasons I like observing from the telescope, because you get to have that interaction with the staff there. So you get a much more immediate feel. For instance, today when the telescope wasn't working, we didn't necessarily have a good understanding of why it wasn't working, or the timescales of that, or how severe a problem it was even. You'll get that immediately from just the way that the telescope operator is holding themselves. We would have known that it wasn't a huge issue by the fact that they weren't growling and depressed while they were working. So it can be really effective to be there when you're observing, and you're never alone when you're observing at the summit.
I have to say that it's been an absolute pleasure to be a part of this. Thank you so much for allowing RAS to do this with you, and for me personally as well. I'm a California girl, and I grew up with being able to see the Milky Way in the night sky nearly every night. Very, very fortunate to do that now that I've lived in the UK for about 10 years now. I do miss the night sky quite a lot. So I'd love to learn more about where I can go to see the night sky more often. We've had some beautiful clear nights out here. I'm in Oxfordshire, and of course to see Neowise at like 3-4 in the morning, as you're talking about. But time has just gone by so quickly with this observation. It's been so fun and so enjoyable. And even though Ganymede has finished its transit across the face of Jupiter, there's still more observation to do. And so Dr. Stallard and Dr. Henrik, thank you so much. They're happy for you to continue to join them to look at Uranus. And I think that's what they've got there on their screen now. But before I turn it over to them, I want to say thank you on behalf of the Royal Astronomical Society for being with us, and also to Tom and Henrik for sharing their telescope time with us and inviting us to share this observation of Jupiter with you. It has made our 200th year very special to be with this on this and to celebrate it this way, especially with the special guest Professor Emma Bunce, Dr. Sean Prosser showing stuff, and Dr. John Zarnecki showing up there. That was fantastic. And also to be able to continue to observe Uranus, which was discovered by our first president, William Herschel, in 1781, who saw it with his 7-foot reflecting telescope from his back garden in Bath, which is where we were meant to be, right? Tom, this was all
Exactly.
for our Bath Nam. So I want you all to enjoy spending the time with them. So we're going to continue to live stream and just say happy 200 years to the Royal Astronomical Society. I do want to say that, Tom, this has been fantastic, especially as I'm the chair of the National Astronomy Week, which will be taking place November 14th to the 22nd of this year. We've decided to continue to go online, and I learned so much from this that it's going to be absolutely possible for us to do remote observation in the UK for the general public and do it this way. We're going to have it every day on the 14th to the 22nd. And what our plan is to offer an hour in the morning for general public and children with the science centers who have observatories around the UK. And then to offer a more general public, maybe kind of an academic theme in the evening, as well as possibly, we're hoping to get some representatives. So because of COVID, maybe someone who can share with us what they're viewing, using digital technology, because that's kind of the forward way we're moving. So this has been a very valuable experience for me. So thank you so much again for having me. I'm not sure which one of you I'm going to make a host. Maybe you can let me know in the chat box which one of you are going to take it on. I just want to sign off, and I'm going to say I am Lucinda Offer, one of 2 very hardworking education outreach officers for the RAS, and it has been my pleasure to have shared this with you. Thank you, and on to Tom and Henrik.
Thank you
Thanks
so
so much.
And thank you,
Thank you,
Nahid and
Lucinda.
Emma as well.
Thank you.
All right, you guys take care.
Thank you. So I don't know who we should make host. Maybe either Emma or Nahid could become hosts, because they're kind of taking the reins of the running of the live stream. That would be good.
If you want to make me host, I'll be okay with that, Tom.
Absolutely, that would be great. What I would say is that Lucinda said that the time had rushed by, and that is exactly why we're all astronomers. It's such fun to observe. That's the consistent experience of whenever we observe, is that even if we're doing something much more prosaic and dull than the observations we've just shown you, time does fly by when you're looking at the night sky. And we've all spent many hours looking through telescopes at Jupiter, Saturn, Uranus, trying to get scientific results. But there is that innate joy of just doing astronomy, which makes the time shoot by whenever you're doing it. And it has definitely shot by for me today. So we're going to continue to do observations. I think maybe, Henrik, do you want to talk about what we're seeing right now?
I made a mistake here, so I'm going to have to reset the offsets. But yeah, this is Uranus, and you can see 3 of its moons. One up here, you can see that. There's one here. And I think there's a 3rd moon we can see here.
There are 3 moons. I need to work out my orientation from the view I'm currently looking at, but Miranda and Ariel are the closest to Uranus at the moment, with Auroal being closer to where Miranda is, but stuck out a bit. But yeah, I'm not quite sure which orientation we're looking at, so I don't want to give any of the moons a name just yet before I'm 100% certain.
Right. I need to redo the offsets.
I have a little look.
Okay, so that works.
So just to remind our viewers, what's the time difference between Hawaii and the UK right now?
So because we're in British summertime, we're an hour ahead of GMT. Hawaii doesn't have a summertime because it's lucky enough to be close to the equator. And so generally it has a very light summer and a very light winter. So it is always 10 hours behind. So we are currently 11 hours ahead of Hawaii time. It's 3:30 here, which means it is 4:30 in the morning in Hawaii, I believe. Is that right? Yes.
Yes, that's right.
So I've had a quick look. I think moons wise, we have pretty much straight on top of where Uranus is. I believe that's Ariel.
Yeah.
There's a very faint dot, I believe, that's closer to where Uranus is just below it, and that one is Miranda. And then to the very left, we then have Umbriel, which is slightly brighter.
Yeah, perfect. Yeah.
Very cool. Using a slightly different wavelength band for these images compared to Jupiter. This is J, so more towards the visible wavelengths, which makes it easier to see because Uranus is quite faint in longer wavelengths because it's cool and far away.
And there's a good reason for that, and that is that one of the great mysteries about Uranus is that it doesn't seem to have a lot of heat coming out of it. Very odd that the amount of heat coming out of Uranus is much, much lower than all of the other gas giants. We don't really fully understand why that is, but it's thought to be perhaps directly associated with why it is tilted on its side so much as well. And it's quite likely that maybe some weird dynamics happened in the early formation. Maybe an Earth-sized world smashed into it. Maybe it lost moons. There's lots of different theories about what could have happened. But that presumably changed the momentum of the planet and meant that it doesn't have enough, nearly as much heat. And that has a direct effect on the way the atmosphere forms, in the way the atmosphere works. And effectively, it means that there's just not as much mixing because there's just not enough heat to drive it. Just as if you have a hot pan on filled with water on a hob, if you have a low heat, it will gently simmer, and if you're at high heat, it will roil. And so, you know, Earth's atmosphere, Jupiter's atmosphere, they are very active. Lots of heat comes out and fills up what's going on, and that's just not happening at Uranus. So everything settles out a lot more, which means the top of the atmosphere is much more settled out too. And so there's a much deeper layer above the atmosphere, and there's much less in the way of winds in the lower atmosphere. So there's two things that happen. One is that all of that methane in the lower atmosphere we talked about at Jupiter is much, much thicker. It absorbs the light much, much better. And so that's why we can't use the same filters. Basically, if we look in the K band at Uranus, it's black. There's nothing to see there at all. It's very difficult to see anything. It's almost invisible. Whereas at Jupiter, there's still quite a lot of reflected sunlight and we can see stuff. So we have to go to a wavelength window where the methane absorption is much weaker. If we looked at Jupiter in this wavelength window, it would blind us with how bright it was. The instrument would not be able to cope, and we wouldn't be able to see anything effectively. So we've moved to a different wavelength window. The other thing that means is that we can see the atmosphere really deeply. The ionosphere of Jupiter, of Uranus, is actually much, much easier to observe than even Saturn, which is much closer, just because it's so deep. So the real mystery at Uranus is not so much the ionosphere, but it's the aurora, and that's something that we're actively trying to find using the data that we're going to measure now and in combination. Another really big question about Uranus is what is its temperature? What is the upper atmospheric temperature? And so that particularly, even with just an hour's data, hopefully we'll be able to get a good measure of the overall temperature of Uranus's upper atmosphere right now. And that works into a study that Henrik's been working on. He's been working on it for more than a decade, and the data that is used has come from nearly 30 years. And that's to understand the long-term changes in the upper atmospheric temperature. And something really weird is happening at Uranus. When Voyager went past, the upper atmosphere was very hot. It was maybe 800 Kelvin, so well above the boiling point of water. Now it's cooled down to maybe 500, so still above the boiling point of water, but not nearly as high in terms of the temperature. And we don't really understand why that is at all. It's very odd. And we thought for a long time that it must be a seasonal effect. So we were watching as the seasons changed, and we expected it to get hotter again. About 5 years ago, we expected the temperatures to start going up, and it's still going down. The last measurement we made was cooler than ever, which is very odd, because if you start drawing the line fit through that, it will start going into negative temperatures, which are physically impossible in about 10 or 15 years. So it's going to have to start changing at some point soon. So what we're hoping to do now is take measurements and see whether we can see that uptick, see whether we can start seeing it getting hotter again. And only once we do that will we start being able to answer, why is it so hot? Why is it changing temperature so much? And that speaks to a broader question, which is, why is it hot in the first place? Why is Jupiter's atmosphere so hot? Why is Saturn's atmosphere so hot? So it's a very much larger question that feeds into all sorts of other questions. Maybe this is related to the reason why the solar corona is so hot, which is another thing that people don't really understand. Maybe it's related to some of the temperatures that we're going to start measuring at exoplanets. Maybe we can use this to understand the exoplanet observations in a better way in the future. So it's a really important question, this question of why is Uranus changing its temperature and when is it going to stop? So even though we've only got a little bit of time left on the night's observations, we can hopefully grab enough data to get another snapshot of what the atmosphere is doing, what the temperature of the atmosphere is doing, and that will give us this new data point in that very long time span. And if we're lucky, that data point will give us a temperature that is hotter than we've seen before, and that will be very exciting.
A very quick question to ask from YouTube. I know in previous observations we have had a chance to be able to see Uranus's rings. We're just asked, at the moment with the stream we can't see the rings that clearly. I just wanted to check if that's going to be just because of the brightness of Uranus in comparison to what the rings are looking like, or if there's any additional features.
So the rings should be surrounding the planet completely. If you could see them, they would form a ring all the way around, because the planet is tilted over so much. The pole of the planet is starting to move towards us. The season at Uranus now is more inclined than the seasons you get at Earth already, and it's moving towards a season where the one hemisphere is entirely summer and the other hemisphere is entirely winter, which is going to take another 10 or 20 years to get to. But when that happens, basically there is no day and night at Uranus. There is just summer and winter, and all you have is sunlight or darkness. So it's already inclined to the point where the rings are producing a perfect circle around the planet. But at this wavelength, it's very hard to see anything reflecting off of those rings, and the planet itself is very, very bright. So while they're there in some way, I'm not sure we can resolve them out.
We can. I have seen them before in this wavelength band, but it's a very tricky contrast. Uranus is super bright, and these rings are really, really faint. I mean, there's not much to these rings. You know, there's a couple of rocks churned up, so there's not a lot of reflection, solar reflection there. Might be able to pull it out later on. But yeah, it'd be fun to see if they're there.
Absolutely, and we do see them sometimes. Partly the wavelength differences help us see that, and partly it's the way that the rings are illuminated and the way that they come through in the data that we're looking at. They are there. They certainly haven't disappeared. And you know, the rings are weak compared to Saturn, but they're the second brightest rings in the solar system. They're vastly easier to see than Jupiter's rings and Neptune's rings, which is an interesting thing in and of itself, especially if Saturn's rings are particularly rare. We believe that Saturn's rings now may be very young in comparison to what we previously thought, which does question why we see anything at Uranus. Why has Uranus got these relatively bright, relatively young, icy rings? It is an interesting question, but for now at least, the one great thing is that they don't obscure our view of the planet at all. They're not in the way in any way, and we've got a perfect line of sight at the disk of the planet. So they aren't in the data as we speak, but you know, maybe as we take data, we'll start seeing the spectra of them come through as we add that data up. I don't know. We'll see.
That's right. The rings in this picture should just surround the planet along its terminator.
I could share the screen I have of Uranus viewer if that might be helpful.
Oh, that'd be
for our
great.
viewers.
Great. Yeah.
Okay,
I've got it
bear
up
with
too,
me.
but I can't quite pull it up.
I have it's slightly delayed. This is back at 3:30 because this is just for my own viewing. Hopefully that will now come up. There we go. So this is currently what we should be seeing. I will apologize to our viewers that I can't have both Carl, our guider, and the Uranus viewers at the same time, but this just gives you a bit of a heads up that we have our 3 moons. That's Umbriel, Miranda, and Ariel, and we currently can see that Uranus, we have one rotation axis point that is tilted towards us and the other one away, and as Tom was mentioning earlier, we have the rings that should be surrounding the planet. Let me just return back.
Yeah, I mean, it's an amazing view that we get. What we're seeing, of course, is quite smoothed out. We're looking through the atmosphere, so there is a certain level of smoothing. That smoothing is, let's see, about 1/6 to 1/8 of the radius of the diameter of the moon itself. So we're seeing a pretty smoothed out ball, and we're at a wavelength when there's not necessarily a lot of interesting atmospheric weather systems. But if you look at some of the observations that you can find online by people like Imke de Pater, Heidi Hamel, there's some absolutely amazing observations of the surface, the weather systems on Uranus. The Voyager mission didn't have an infrared instrument on it. It only had visible cameras. And so it's rather unfortunately led to this view of Uranus being a boring world, because in the visible, there's a lot of haze, and all you see is the hazes above the cloud layers. And so there's this beautiful billiard ball kind of view of Uranus, but actually there's an awful lot going on at Uranus. So if you search for some of those Keck observations where they're using adaptive optics to take away the aberrations from the Earth's atmosphere, there are absolutely amazing weather systems on Uranus that you can see underneath that haze layer. For us though, since we're guiding on this object, it's quite good that there's all that haze in the way, because as I've said before, boring is really good when you're looking at things you don't want to use scientifically. You want science to be interesting, but you want everything else to be as boring as possible, so it makes things easier for you. So the fact that it's kind of like a billiard ball is really useful in this wavelength, because it means that the instrument can pretend it's a star and guide on it really effectively and give us a really good position.
Awesome, thank you very much, you both. Want to check, Nahid, did you want to take a question from Zoom, or did you want me to give you a bit of a break?
I'll ask it. So we've had a question from Graham, who asks, if the aurora on Uranus are still around the poles, then surely they are sometimes facing towards us. And then what direction do the poles point now?
Emma, do you want to put back your view? From
Back to Uranus viewer.
Yeah.
Yeah, certainly, bear with me.
So this raises a very prosaic question, which is, where is the North Pole of Uranus? It's a question that we have discussed amongst ourselves very, very many times. And it depends completely on the definition of what makes a pole of a planet. For most planets, it's really obvious. When you look at the North Pole of the Earth, it points towards the north in the same direction roughly as the North Pole of the Sun, of Jupiter, of Saturn, of Neptune, of Mars. Venus is rotating very slowly, but kind of points in the same way. Mercury. has the same direction of point, but Uranus does not have that same point. The pole that you can see right now is coming towards a northern a summer is the same pole that we would use to describe things like Earth. It's the rotational pole that is basically the one that is spinning in the same direction as Earth's North Pole spins. But you can see it's sort of pointing down a little bit. So the North Pole there is the North Pole if you use the definition that a lot of planetary scientists would use, which is the momentum North Pole. It's this pole that has the same spin direction as all of the other planets. But you can see that it's pointing south in the ecliptic. So the official Astronomical Union definition is that that is the South Pole, because from an astronomical point of view, all North Poles point north, right? It has to point north for it to be a North Pole. So in their view, the pole that is obscured on the far side of the planet is pointing slightly north, and so that's the North Pole. It causes the most confusion of anything in science that I've ever heard, because no one ever knows what you mean when you say the North Pole of Uranus. It's very confusing. Now, that's the rotational pole. There's also a magnetic pole. On Earth, that magnetic pole is very close to the North Pole. So we use compasses to find north. What we're actually doing is not looking at where the rotation pole is on Earth. We're looking at where the magnetic pole of Earth is. And it just, it happens to be very, very close to the pole. So it works very well when we're looking at maps because we basically have a very small offset between the two. So we can use compasses very effectively. That doesn't work at Uranus at all. The North Pole of Uranus magnetically is very close to the equator. And so actually, you're going to end up pointing somewhere near the equator if you used a compass on Uranus. So that doesn't help. And then, of course, that's offset from a rotational pole that is itself on its side. So you've got a rotational pole on its side, then a magnetic pole on its side. So the magnetic pole, as we would see it here, is swooping around like a lighthouse that's fallen on its side. So understanding that is even more difficult, which is why it's fascinating, which is why we really want to observe it. We want to understand that and how it works and how it interacts with the surrounding space. Does it have an aurora that looks like Earth? Does it have an aurora that looks like the planets around, like Jupiter and Saturn, or is it a completely unique interaction? And we know very little about that. Voyager made some measurements of the aurora when it was there. Laurent Lamé has led a team looking at Hubble Space Telescope observations, and using that we've been able to measure what appear to be bright spots of aurora at Uranus, and that's literally the only observations we've ever made. We are working very actively to try and find an infrared aurora like that we see at Jupiter and Saturn. That work is currently officially not found anything, so we're going to continue to work on that. That's the work that Emma is currently working on for her PhD. So we're hoping that that will yield some interesting results in the future. But at the moment, all we've been able to do is measure things like temperature across the planet more generally. So that's more than you ever wanted to know about poles on Uranus.
Excellent, thank you very much. So how are we looking with the observations themselves?
I don't know, Henrik is disappeared for the moment, which suggests that either things are really boring or really interesting. I would say that they are probably going really well. What you see is the guide camera, and you can see that we're holding very well. Because Uranus is quite small, it's actually a lot easier to observe than Jupiter and Saturn. Jupiter and Saturn are so large that we can't use them to guide on. We have to find other objects. But Uranus is relatively small in the night sky, so we can actually pretend it's a star, and the guiding system actually thinks it's a star and is able to keep us on track, which means it's actually a lot easier because we can bounce between two positions and take spectra continuously on that. I don't know if we are seeing data come through. We are going to need to look.
Yeah, it's not a lot to see yet.
Oh yeah, that's very weak. One of the disadvantages of looking at Uranus, which is one of the advantages of the science that we do, is that it's almost impossible to see reflected sunlight on the planet. Well, that's great because it means that our view of the upper atmosphere is much better, but it means that it's really difficult to tell when data is coming in because the planet's basically invisible except for the aurora. And the aurora is quite weak, so it takes a little while to build that signal up. We certainly don't see things nearly as clearly as we did at Saturn and Jupiter, where we saw all those bands of reflected sunlight. The atmosphere is so deep that it doesn't manage to do that at all.
Yeah, it takes a while to build up a decent signal at Uranus. Looking at probably half an hour or something like that. So it's 5 a.m. in Hawaii right now. What time is sunrise?
It's summertime, right? So it's probably coming up fairly soon, I would imagine.
Let me check when we need to be off the telescope.
Yeah.
I have a couple questions from YouTube, if I'm
That's
all good
great.
to shoot off. So I have one from Wayne Hall, who mentioned, I think when previously we were discussing with Uranus about the changes in temperatures that we've seen from the upper atmosphere. Wayne asks that we can't go into the negatives, which I believe the mention of that is going below 0 Kelvin, but also kind of asking a little bit about the kind of high temperatures we were seeing at Uranus being like more than we were expecting. Would you be able to go into a bit of detail into
Sure,
either
okay,
of those?
so scientifically we talk about Kelvin rather than centigrade, and we're very used to the idea of positive and negative temperatures for centigrade because they're based on a scale between the boiling point and freezing point of water. But the Kelvin scale is the same temperature gradient, but it starts at 0, and 0 is absolute 0. It's the lowest temperature that exists in the universe, and that's because as you cool things down, the energy gets lower and lower, and then at 0 Kelvin, everything stops. There's no vibrations, there's no energy at all. So it's an absolute temperature scale. And so when we talk about the temperature in Uranus, we're talking about Kelvin temperatures that are varying between 750 Kelvin, right the way down to maybe even just 500 Kelvin. So that means that it's gone on an absolute scale from 7.5 to 5. So it's continuing to cool down in absolute terms. It's effectively almost halved the amount of energy stored in the upper atmosphere in the period of 30 years. So that means that if it were to continue cooling at the same rate, which no one, I think, believes, it would eventually keep going down and down until it hit absolute 0. And you can't go beyond absolute 0. It won't, of course, do that. It must be shallow, becoming more and more shallow. But we assumed it would become more shallow much more quickly, and that at about 550 Kelvin, it would stop and then start heating up again. And we just haven't seen that yet. So it's very odd that it continues to cool.
Yeah.
That amount of energy loss, the amount that it's less energetic in the top, the amount that molecules are moving around in that region, they're basically moving with a kinetic energy that's nearly half the kinetic energy of 30 years ago, which is a huge amount of energy difference. So it is really surprising that there's that big difference. We don't really understand why it was that energetic to start with. It's a big question for why Jupiter has that much heat. It's actually hotter at Jupiter. Jupiter's equatorial thermosphere, the top layer of the atmosphere, is maybe even up to 900 Kelvin at some times. So, double the energy that you have at Uranus at the moment. And we don't really know why that is at all. And it's one of the big questions that we're trying to answer. There's some clues there that James O'Donoghue, who's left now, has found that may be giving an indication of why it might be that hot at Jupiter, but it's still not really well understood. We think for Uranus, the answer is probably the aurora that we can't really see yet. It's very likely that the aurora is seasonally changing in a way that we don't yet understand. We thought that maybe it was seasonal heating from the sun itself, just changing the amount that different atmospheres are illuminated that was changing the temperature, but that's clearly not the case. What it might be is the way the aurora work, depending on what the season are. We know that the aurora that we saw at Voyager was when it was a summer that unlike any other summer in the solar system. It's when the whole of the one hemisphere points towards the sun continually, and the planet rotates such that you don't really see a day and night. One side is always in darkness and the other side is always in light. And so presumably the aurora that generates is weird and unique in ways that we really don't understand. Of course, you know, the magnetic fields are so offset from the rotational pole that's also true now when we're moving sort of more to a sort of equatorial summer winter cycle. We're near equinox, we're near spring, or in one hemisphere now, but still it's going to have a really weird interaction that we don't understand at all. The only other way that we could really understand that would be Neptune, but we have yet to see anything from Neptune other than what Voyager saw. So there's a huge hole in our understanding, and so anything that we can do to answer that is going to help us understand both the auroral interaction as well as understanding, you know, where this heat, this excess of heat is coming from. We certainly, Neptune was also really, really hot when Voyager went past. And if it is as hot as we expect, and the atmosphere works in the way that we expect, we should see H3+, and we don't. So there's another big question. And one of the answers might be that Neptune is much cooler. If Neptune is much cooler, that throws a huge spanner in the works, because Neptune doesn't have a big season like Uranus, and yet both worlds have cooled down by hundreds of degrees. So yes, huge gaps in our understanding, which is, you know, really why we want to study these worlds and answer some of those questions.
Awesome, thank you very much, Tom. I was going to ask, is it cool if I still kind of go through another one, or are we ready to start looking at some results?
We can go through another question.
Okay, cool. So yeah, we've got two more. I have another one from JF Chardon, who asks, more kind of an astronomy-based one. What kind of wavelength/sensor would you use if somebody calculated the location of that planet X? I'm not quite sure on planet X, possibly exoplanet, and you had a telescope time to point at it.
So I think what they mean by planet X is the supposed planet that is currently theorized to orbit very far out. And the way that they've discovered that is very, very similar to the way they discovered Neptune. The way we originally, the way science originally discovered Neptune was that they looked at the orbits of the other planets and showed that there was something big out there. And then they were able to go and have a look for that. And so the question really is, when we look at these Kuiper belt objects very far out, they all seem to have a really weird orbit that lines up. So there's a theory that there is a big, maybe super Earth-sized world very, very far out. If we were able to find it, it would completely rewrite our understanding of solar system dynamics and how the solar system formed. But it's still very much theoretical until we are able to measure it. It may just be chance. The likelihood that it's just chance is pretty low. It's like 1% or something, but you know, people go gambling on much better odds than that. So it's possible that the solar system just rolled a natural 20 and we have a planetary system that appears to have something but doesn't actually have anything there. The way that you would look for that is very much dependent on what you think that world is like. But the easiest answer is probably you would use visible, because visible light is very easy to look for. We don't know what the surface composition is, but it's probably somewhat similar to Earth, or probably more like Kuiper belt objects. So they're icy. If it's an icy surface, it's going to be very white. If it's not, then it's going to be much darker, but it's still going to be dark no matter what wavelength you're looking at. It's unlikely to have methane in the atmosphere, but if it did, it would be much, much harder to see in infrared anyway. We don't have to contrast it against anything. When we're looking at exoplanets, one of the big things that we have to think about is how bright the star is, and the star gets in the way very easily. What we need is something really easy to measure. So radio is really easy to measure, but there's nothing bright really to reflect off of the surface. If it was actively kicking out radio, we'd use radio signals. That's probably the easiest thing to see in the night sky, radio emission. But because the sun doesn't have a lot of radio associated with it, nothing's going to reflect back. So the next big window that we we would use is visible. And the reason it's the big window that we use is because that's what bathes the Earth with light as all creatures started to evolve. So as they evolved to see in wavelengths that were the biggest buckets of light they had available to them. So that's why we see in the visible, that's why the sun is yellow. It's yellow because yellow sits right in the spectrum between blue and red that we have evolved to see. So we're very good at seeing one of the biggest astronomical windows. So it seems natural to use optical as a way to track that planet down. That's what we used in the past to detect these worlds. So I think it's quite likely that will be the case. And what it will be is most likely a smaller telescope with a really good survey instrument capability. It's possible it will be a space telescope that is able to detect that, but ultimately a telescope like this where we're focusing in on a really narrow bit of the sky doesn't work well at all. There's too much sky to see. What you need is something that surveys a very large area. And so there's all sorts of science reasons for doing that. You can do it to find exoplanets by looking at the variation in the brightness of stars. You can do it to find, we talked a little bit about microlensing and where you see the gravitational pull of field stars changing the brightness of distant galaxies. Again, that's something that there's lots of surveys looking for that happen to be taking data of large swathes of the night sky. So people may well be able to use that kind of data to look for distant objects. And there's lots of people looking for Kuiper Belt objects as well that use similar types of observations. So hopefully there will be all sorts of attempts to do that kind of measurement where we're looking for various distant objects. And it will come out from that, but ultimately it will take someone being lucky because we don't know exactly where that object is. We have a rough approximation, but that area of sky is very large still. As with the eventual detection of Neptune, the physical detection of Neptune, it takes someone looking in the right kind of area at the right kind of time under the right kind of conditions and hopefully reveal it. But until we do, we don't know how the best way to detect it would be.
Awesome. Thank you very much for that, Tom. I think that's got that one answered. Nahid, I think there was a question that was posted, if you're able to take
there
that.
was. Yeah, thanks, Emma. Yeah, I've got a question here from a gentleman named Podrick, who asks, how are we able to understand the connection between the auroral processes and the effects on the neutral atmosphere? So that's a question from Podrick.
Well, I happen to know that there's a certain interest in the atmosphere from Podrick. He's a fellow researcher at Leicester, so it's a little bit of a biased question, perhaps. It's a good question, and ultimately it's a matter of gaining an understanding of different layers of the atmosphere. So what we're looking at right now is the very top layer of the atmosphere. We know that because it's a region that is glowing only in that region, because H3+ is super reactive. So if you go any deeper in the atmosphere, it just gets destroyed straight away. So we're lucky that we know that the region that we're looking at is very well located in a particular layer. But as you use observations at different wavelengths, you start sampling different layers of the atmosphere and you can start building up an understanding of all of the different layers. And what you can do is hopefully take observations of the aurora and these neutral atmosphere layers at the same time and do comparisons and wait for, say, a very large auroral storm to happen and see whether that has an effect in lower layers. And I know that some of the people that Podrick works with have been doing that, have been looking at the mid-atmospheric layers and trying to see changes when changes in the aurora are happening. And there's been some really interesting results that have shown that recently. It's very clear that there are definite ties at Jupiter, at least, between what's happening in the auroral regions and what's happening in the underlying atmosphere. The deeper you go, the harder it is. So certainly the layers that Podrick looks at, which are the deep layers of the atmosphere, aren't going to care about the aurora at all. The aurora are vastly weak in comparison to those lower layers, but those lower layers are ultimately potentially going to move layers above it and push the power that they have higher and higher in the atmosphere. So it might well be that the auroral regions that we look at will change depending on what's happening in the lower atmosphere. everything's coupled. It's a flywheel at the bottom and a flywheel up in space, and they're both trying to push energy into this thin little layer that we have and change what's happening. But it's such a thin little layer that that either of those can drive both the ions and the neutrals in that layer. So if we can get measurements of ions and neutrals at the same time, which we're hoping to do, we have some early observations from Keck, that might tell us about that coupling in a way that we've never done before.
Thank you, and I hope Podrig's question was answered there.
I do have another question that has come in through YouTube, as we're still waiting for our signal to slowly build up here at Leicester. Star Trek has asked about Uranus's moons specifically, asking about them orbiting at the same tilt at Uranus. Did they form after the tilt, like leftovers of enormous impact that tilted the planet, or is it tidal effects that moved their orbits?
I mean, it's hard to absolutely know for sure the answer to that, but it's likely that they formed later, just because they are very close in terms of the orbital plane. They seem to orbit very well with the planet. It's possible that some form of braking in terms of the tides drove them into more circular orbits, but it's unlikely. What the one caveat to that would be, you know, the conditions in the early formation are very different to now, and so maybe there was a lot of dust and gas around that caused a lot more interactions and allowed them to change orbit. But if you think about captured moons around other planets, Jupiter has a huge number of irregular moons. Those are quite happy to continue to orbit in odd configurations. Closer in, the tides are going to be much stronger, so maybe that had an effect. But there's certainly some evidence to suggest even Saturn's moons are very recent, maybe 100 million years old, some of them. There's certainly some moons that are just rubble pits around Saturn. They're just made of rubble that is basically not even a planet that holds itself together structurally. It's just the gravitational pull keeping it together, and so they're actually sort of dusty clouds that happen to be very dense dusty clouds and look like moons, but are basically ready to be ripped apart. And in some parts of Saturn's rings, we even see them forming. If you follow some of these like spokes that come off of the rings in certain places, you start to see them clump together and form moonlets. So Saturn's rings have these amazing features that we see that maybe tell us something about how they might have formed in their early system. But the fact that they are all in a very boring circularized orbit around Uranus in this incredibly tilted shape does suggest that it's more likely that they formed after that early impact. But the various models suggest that that impact probably happened very early on in the formation, so there would have still been a lot of material around. And of course, you know, the moon around the Earth is thought to be formed by an impact between a Mars-sized object and the Earth, and so it seems natural if there was a giant impact that there would be a lot of material around that would have formed a huge ring that would then have coalesced into being moons like that anyway. So it seems natural that there would be moons around Uranus as a result of that kind of impact.
Awesome. Thank you very much for that, Tom. Appreciate it. I don't know. Nahid, you might be able to back me up on this. I don't know if we have any more questions from our viewers at the moment.
Not that I'm aware of, no. So we'll wait for those to roll in as and when they do. But in the meantime, we'll just take a quick update, I think.
Yeah.
Yeah.
I think we are starting to see something very weak, Henrik.
Yeah, it is coming through very slowly. It is. If you know where to look, you can see you definitely got a signal, which is always a nice feeling. It's not very bright at the moment.
Yeah. This is probably a really good example of how an observer will see things that a normal person might not see. So if Emma, you could pull the instrument, the spectra up, we can see the kind of definite result that we're very sure of in our data, but takes certainly a certain amount of squinting to see, if not.
So here you can see clearly, well, not clearly, but there's a dark spot. Can you see my cursor?
Yes.
Yeah, that's currently there.
Oh, there, yeah. So there's a dark splodge right there, and right below it, there's a bright splodge. And so the bright splodge is when Uranus is on the right on our guiding camera. The dark one when it's on the left. Sorry, other way around. Yeah, the bright is left, the dark is right. Yeah, okay, that's good. Because we subtract one from the other, so in one frame is dark and one frame is light. And what we do, we add, well, we subtract the negative from the positive, so basically add them onto each other to get the full signal. We ideally want to build up a bit more signal than this, so another half an hour maybe, and we can get some actual science out of this. Would be nice.
Some really eagle-eyed viewers might notice an even more difficult to see squidge up in the top left-hand side. So there is another couplet of dark and bright in that kind of top left region, and that's a different emission line. And so that's really interesting because, as I said, these lines are generated by temperature. They're being heated up in the top of the atmosphere. And there's a calculation we can do to figure out the quantum physics involved in how bright each line should be. So understanding and seeing the brightness of each of those lines tells us effectively what the temperature is, because we can run it back through our understanding of quantum mechanics and say that line should be this bright and that line should be this bright if the temperature is this. So by measuring those two lines, you can understand what the temperature of the upper atmosphere is. And that's how Henrik will ultimately resolve that back into a temperature. You can see the signal is very weak, so hopefully we can build that up to a strong enough signal that we can get a good error on that calculation. But it's probably too weak to do very much more than that. But even that one data point hopefully gives us an insight into that long-term temperature trend. And so even though we've only got an hour, it's still worth looking at Uranus to try and get this measurement.
Yeah, it's going to be a really valuable data point in the long-term temperature trend of Uranus's upper atmosphere. You know, all we need is just, you know, many data points throughout the year. It's ideal.
I was going to ask, because we're taking hopefully an east to west viewing, are we going to be able to see velocities at Uranus, or am I asking a bit much?
Yeah, you should be able to see the rotation of the planet at the very least. So when Uranus is, the equator of Uranus is rotating towards us on the edge, we should see a blue shift towards us. And when it's rotating away, we'll see a red shift away from us. And so that should give this emission lines a slope in the data. Now it's a little bit hard to see that right now, but it should be possible, you know, give half an hour or something.
We saw the same thing. I didn't point it out at the time, but we saw the same thing at Jupiter. You see a very significant and clear slope. It will be in the data. If we had long enough, we would maybe start to be able to see variations in that, which is ultimately what I want Emma to go on to look at in the future of her studies, because we have got specific observations of Uranus from both this telescope and from Keck that are more dedicated and allow us to measure that with much more precision. But it is possible, because if we combine this positive and negative and then combine all of the other positives and negatives from all the other lines, and as I said, Uranus has a lot more of those than most other planets, because there's some regions where there's a lot of reflected sunlight that swamp out the lines that we might see from Jupiter or Saturn, and those don't exist. So there are a whole lot of lines that we can add together. So it is possible, even with weak data like this, that we could try and do that. I don't know what slit size that Henrik put in. I see it's the narrow one. So that actually means that, yes, the data is there. And iShell is an amazing instrument. It's one of the best instruments in the world for this kind of observation, coupled with a 3-meter telescope where they're dedicated to look at planetary observations. The IOTF and iShell are really utterly groundbreaking in the kind of observations that we can make for looking at the Doppler shifts from the top of the atmosphere of these worlds. And it gives us a view that allows us to measure how the ions are flowing around the planet. which is hopefully one of the ways we'll see whether there's an aurora there or not. We're hoping that we'll understand much more about the ionosphere by looking at that kind of measurement of the flows. We've talked a little bit in chat about how that's been so useful for the aurora of Jupiter and Saturn. So presumably there's similar currents associated with Uranus hidden in this data, and we can hopefully reveal that. Maybe not from today's observation, but certainly from past observations where we've had a much better, longer integration and being able to pull out information in a much better way.
Awesome, it's got really good to hear on that one. I do have a question. It is work related, don't worry, Nahid. Is primarily just asking because you've mainly done observations with Jupiter and Saturn, so how is Uranus for you different with those observations?
Well, Uranus is very small in the viewer, which is no surprise really given its distance from the Earth. In terms of the technical stuff, I'm very accustomed with Jupiter, especially to just setting up the instrument slit at the top of the planet and then letting it drop down and basically scan the northern aurora or the southern aurora. And when it comes to Uranus, it's of course different because usually it's a case of keeping the slit across the planet in either an east to west cut or a north to south. So there are differences there, a bit like what you're seeing right now on screen actually. Yeah, it's one of the other things that we've done in the past that's interesting with Jupiter as well, to be fair, is we've tried scanning the Great Red Spot using the same slits and trying to collect data from that. One of the useful things with the Great Red Spot is that you can guide on it, basically, a bit like how we were guiding on, or at least how we were using the moon today to guide on. So it is different, and I certainly like leaving Uranus to the more experienced observers such as Henrik and Emma, and of course Tom. But yeah, give me Jupiter any day. Aurora, I'll take that kind of data easy. Saturn as well, to be fair, is slightly different because Saturn is another planet that's a little bit dim, and especially with IOTF, you do need to employ a scan pattern, or I should say, an observing pattern where you're keeping the instrument slit trained on the planet for a prolonged period of time. So it's not quite in your face like Jupiter's aurora are, which are just sort of there, they're big, they're powerful. It's a bit more of a drawn out process, but you still get decent data. And indeed, the data that I'm analyzing, or I will be analyzing very soon, will include IOTF Saturn data, which Tom collected a few years ago now. So yeah, there are differences. And I'm a bit of a happy observer watching you guys observe Uranus, to be fair. But of course, if you need me to do anything, let me know.
Awesome, thank you very much for your answer, Nahid.
That's fine.
I think we're having a few clouds coming in actually.
Okay.
Or maybe it's just sunrise. The sunrise is at 5:45, which is in 25 minutes time.
Do we want to see if we can pull up one of the webcams, Emma, put it over the top of the window?
So I'm afraid I can't share both at the same time. It's not quite like the stream. I would only be able to show the camera or show card.
Well, I can share it. Hold on, I'll see if I can pull it up.
I had noticed whilst we shift over, I think we have a good question from Thomas on Zoom. Mentions, what is the spectral resolution of iShell, please?
Okay, so just briefly before we say what it is, we should say what spectral resolution means, and that's ultimately how narrowly you can split the light up. So if you think about a rainbow, it splits red to blue from the sun, and so it's how finely scaled you can pull out. So if we say that the rainbow has 7 colors, we probably see more than 7 colors, but if we just say it's 7 colors, and you're moving between about 350 nanometers and 600 nanometers, so you've got maybe, let's say 6, 7. You've got 7 bins of that. You're going to have a spectral resolution of about 50 nanometers each. Each of those colors gives you 50 of the 350 nanometers of the rainbow. So it's basically a measure of how well you can pull out information, how well you can define what you're seeing. And when you talk about spectral resolution on spacecraft, typically, say, the VIMS instrument on Cassini had a spectral resolution of about 400. So it could split the light up into 1/400th of the resolution of the wavelength that they were looking at. iShell has a resolution of 70,000, so it can split the light by nearly 200 times finer than VIMS on Cassini could. That resolution 400 is very similar to the resolution on Juno as well. And that's one of the reasons why we can't use Juno to do the observations on Jupiter that we want. It's a fantastic instrument. It's got amazing science outputs, but when you're looking at a very weak signal like this behind a planet, it makes it very difficult with only 400 spectral resolutions. Whereas when we looked at our data, that line was incredibly narrow, completely separated out from the light. So basically, because it's 200 times higher, in order to think what you would see in Juno, you'd have to take 200 pixels wide of that spectra and add them together. And you can see that that's going to impinge on all of the atmospheric stuff behind it. That's the resolution of iShell, which is one of the highest there is. There's an instrument on VLT called CRIRES, which is 100,000, which is even higher. That's at this particular wavelength. If you're in the visible, you can actually go much finer than that, but it's much harder to do very fine resolution. And there's a fantastic mid-infrared instrument that is called HITWAC that sometimes visits the IRTF, but again looks up at the million resolution, spectral resolution. But certainly in the wavelength region that we're doing for the science that we're doing, iShell is about as good as it gets in terms of the way that you can split up the light in a really effective way.
Awesome, thank you very much, Tom. I was gonna very quickly ask if we're thinking of going over to an IRTF camera. Did you want to continue doing that, or did you want me to take over?
I can just pull up a view of view out west from the ridge above IRTF. I don't think I can see IRTF in it, but we can look out towards, let's look northeast. If I share my screen, there we go. You should be able to see. This is an current updated webcam. It's 5:30 in the morning in Hawaii, and you can see a beautiful dawn rising over the mountains of Hawaii. It's very pretty up there. You can see that the clouds that we feared would cover us are mostly clear, but there are still some wisps of high cloud up. This is cirrus cloud, which is one of the major banes of any astronomer. But most of the clouds in Hawaii sit very far below you. Hawaii is actually a very cloudy place usually, especially out towards the east, which is the rainy side. Hilo is somewhere below us in this image, is the rainiest city in the whole of America. And the rainiest place on Earth is on another of the islands of Hawaii. So there's constant rain in the afternoons in Hawaii. It's very, very cloudy during the afternoons there. But all of that cloud nearly always sits well below you at the summit of the mountain. Sometimes when there's thunderstorms, you see them rise up, and that's the worst you can have as an observer, because it will basically mean that it's impossible to open the telescope. The very worst is when they're near but not quite at you, because you can see beautiful night skies but the atmosphere is so damp that if you opened the dome, all of that water would start attaching itself to the mirror, and you can't allow that to happen. You have to keep the temperature in the mirror up to stop that from condensing. So the most frustrating time as an observer you'll ever have is when you've got a very high humidity but beautiful clear skies, because you can sit above and see wonderful skies, but you're not allowed to open the telescope at all. But this is much more typical, where you've got some wisps of cirrus above, and they're particularly obvious on the horizon. So you produce these lovely sunsets and sunrises, but most of the clouds sit way, way below you, and you can see the mountains rising out of that. You can see different views around the mountain, where you can see the telescopes far above, and you can see that it's light enough to see very clearly now, even though the sun hasn't risen yet. And so CFHT, one of the telescopes near IRTF, is shut already. Most of the telescopes will be shutting now. IRTF is uniquely infrared. It doesn't do any visible observations. And so they're much more comfortable with the idea of observing not only into dusk, but actually into the day. And so certainly over this week, IRTF has been open for most of the day as well as the night. You are able to observe infrared objects even when the sun is up in many cases. It's much more difficult to do that, but we've certainly done it for the aurora of Jupiter, specifically when Juno is taking specific observations of the aurora. We want to take observations at the same time, and the only way we can do that sometimes is by observing during the day. And IRTF, one of the specialties of IRTF is that they are willing to open the telescope all day as well as all night. And but the conditions are so clear in Hawaii that it allows you to do that and actually be able to observe astronomical objects, even though the sun is up in the sky. So we're going to stop observing fairly soon, because the sun is coming up, and that's going to make our observations of Uranus much more difficult. And we're not even supposed to be looking at Uranus. Our target has already set, and we're basically in calibration time. But it may be that another observer comes on after us. I'm not sure whether, I haven't seen the schedule for after when we're observing, but certainly this week other people have observed during the day.
Yeah, there are observations straight after ours, starting at 6:25 in the morning. Could you show the view of IRTF from Gemini and the Gemini cams?
Yeah, let's have a look if I can hold that up. Now, I think this is old, is that right?
Oh yeah, July 13th.
Yeah. So this is from June. I don't know why it's taken so long, but this is a view that you would see from Gemini, one of the telescopes up on the ridge, down at IRTF. So down here, this wonderful little telescope, which has a silver dome and a white square base, is the telescope that we're using to observe. It's a smaller telescope now on the summit. It's one of the oldest telescopes on the mountain, but because it's specifically for planetary science, it's been able to continue to produce very unique science. Over on the left, you can see one of the two Keck domes. This is a 10-meter telescope that's still basically the best telescope in the world. And somewhere down the mountain a little bit behind here, in the future, may be the site for the 30-meter telescope that is planned to be built. You can see all these bright, bright lights down here to the right of where IRTF is. That's the town of Waimea, which is where you observe using Keck from. So you'd sit in a room down the mountain here. On all these little lights between IRTF and Keck are the coast, the west coast of Hawaii. So there's lots of little resort towns along there. And then out on the horizon, you can see a glow above a mountain. That's Maui. So the town of Maui sits between two mountains down here, and then here's Haleakala, the highest peak outside of the Big Island that this is being taken from. And then there's a bright glow in the horizon over here. That's Honolulu. It sits beyond the edge of the Earth, but the glow of it is so bright. Honolulu is such a bright city that it glows in the night sky. So that's the kind of view that you can get looking out from the summit ridge. And it's a very similar view to the kind of view that you see when you step out of the front door, which is over here looking towards Keck. So when we're observing, we'll often go out and look out at the surrounding space, and as your eyes adapt, you often see Waimea below you and the glow of Maui and Honolulu in the distance. It's a very similar night to tonight, actually. This old image, you can see the thin cirrus clouds above us, and then most of the clouds sit far, far below. But this is the night sky as we see it. Sunrise is coming, and then this is a weird looking image. This is 2 frames of the night sky subtracted from each other. And so when there are lots of clouds, you see lots of these weird structures and shapes. You're seeing a few, but that tells you that actually it's pretty clear there now. Normally you get this weird cross hatching that just means you're not really seeing much of anything, which is what you want as an observer. Okay, I think that will do for that.
I think we're going to have to stop the observations now. It's becoming hard to see Uranus. The sun is saturating the sky. Or scattered sunlight, I should say.
You have a quick look at that.
Yep, let me just bring up. I do have a question actually about Kyle, which we might add on just as we're going to be closing for today's observations, if everyone's okay with that.
Yep.
So we had a good question with Zoom from Ami, who asks, what does the bubble surrounding Uranus represent? Currently the pink purple.
Right, yeah, it's the field of view of the instrument. So it has a sort of a circular aperture. So anything that's purple now is what we can see on the sky. You can see the edge of the aperture is sort of this wonky sort of circle around it. So that's just the entry of the instrument. Yeah, I can see we can barely see Uranus at all.
Mm.
Yeah, it's getting rather hard to see in that, unfortunately.
I'm going to stop this.
Okay. So hopefully we built up a little bit of data, enough to get at least one temperature out.
I think so.
And that kind of brings our observations to a close. So what we'll do now is, scientifically, is that Henrik probably will go on mute and he'll talk to the telescope about the fact that we're done. If there's an instrument change, they can change the instruments over. Some telescopes have very clever technologies for that. Subaru has a robotic arm, but unfortunately that robotic arm takes about 8 hours to change the instrument. Other telescopes use an extra optical path. So they have instruments that are on different positions and a mirror flips the light between them. So certainly Keck and VLT do that. But IOTF relies on the strong arms of the telescope operator. They get a spanner, they undo the nuts, and they slide one instrument off, they slide another on, and they bolt it back in place. That is a much more kind of muscled approach, but it's also a very fast approach. It takes about 15 minutes to change your instruments over, but allows that instrument to be in that primary position on the telescope so you don't lose light by having a mirror. So it's not necessarily an ideal way to do things, because it does mean you need people who are willing to lug very heavy things around at the top of a mountain, but it is a really efficient way to get very good instrumentation in the right place at the right time. So if there's an instrument change, they'll want to get on with that so that they can get on to the next telescope. Otherwise, basically, as soon as we're done, there's no sense in us blocking up the telescope for the other observers. Someone else is able to look at things in the day sky. And so it makes sense for us to hand over to them so that they can get on with their science. And that's the daily life of a telescope. As a telescope operator or someone supporting a telescope, you'll see a vast array of different science through a night or through a series of nights. The next observer may be looking at something else in the solar system. They may be looking at something in the near galaxy. They may even be looking at galaxies in very distant from ours. Because of the way IRTF is set up, it's more common that there are planetary targets. But generally speaking, you'll be looking at targets from all over the night sky. So that's something that they're going to be moving on to. And because of the way ITF works, generally it's the observer that does a lot of the work in terms of doing the actual instrument setting and things like that. So the view that you can see now of our instrument, you can see that we're logging out and saving our data. We'll log out of that instrument. The next observers will log in with theirs on the same view, the same window, and then ultimately we'll start taking data. So we're logging off of an instrument that other observers will now log on to. So it's a very interesting way of working. You basically use the instrument while you need to, and then they take over and start doing their observations.
Tom, very quickly, I'm pleased you mentioned our telescope operator. I have had a question earlier from Graham, who asked, what are the dangers for people that are working at altitude sort of regularly with telescopes? So what kind of things do they have to consider? I mean, but it's different for them, surely.
There's a lot of things that you have to think about. Generally speaking, you will always have at least two people in a telescope. What's interesting about altitude sickness is that there is really no way of predicting who is going to be affected by altitude sickness. This is something that, military planners, when they're invading high altitude places like Afghanistan, they will have a natural attrition rate of people in the army, because even though people in the army are super fit and healthy, there will be a percentage of them that can't handle altitudes. And there's no way really of knowing who that will be. But obviously, if you're a telescope operator, you're probably really good at handling altitudes. Otherwise, you would want to get off the mountain as quickly as you can. It can still affect you, though. But generally speaking, they're very careful about how to monitor that. And that's why they always have at least two people up at the mountain. So generally speaking, it will be an undergraduate student or someone working at the university in that capacity, or a volunteer who just sit up there and watch movies, or sit up there and do some of their coursework for the modules that they're working on. Just as someone there who can drive the telescope operator down the mountain if there is a medical emergency. That's never happened as far as I'm aware at IRTF. But that's one of the real dangers that I guess you face every day. Other than that, it's amazing how difficult it is to think straight in that kind of environment. At 60% oxygen, it's very easy to make mistakes. When observers make mistakes, it's usually something stupid, like forgetting to open the shutter on the instrument and taking data on a blank canvas continuously for an hour, which does happen more than it should, especially when you're observing from the summit. But obviously, if you're working with liquid nitrogen, liquid helium, working with instrumentations, there can be greater dangers. And as Henrik described earlier, there's sometimes real dangers in terms of these being cutting-edge scientific facilities. With the engineering in these facilities is very much on the cutting edge of what we're capable of. We want them to be incredibly detailed and incredibly powerful places, and so there's a natural danger that is associated with that. I think IRTF has been very good at safety, but you can never get complacent. I know that there have been people injured and killed in building telescopes in Hawaii because the working conditions are so difficult because of that lack of oxygen. So that can be a real danger, and you have to be very aware of it. I know that there have been guests visiting the telescope that have done very, very silly things. There's a famous story from one of my colleagues I won't name, who famously drank a swig of what he thought was a juice drink, but was actually antifreeze. And so there was a mad panic getting him down the mountain so he wouldn't die of antifreeze poisoning. The joyful end of that story, of course, is the curative for antifreeze is alcohol. The only way that you can prevent antifreeze from attaching itself to your liver is by swamping it with alcohol so that it can't do it. So he was on an alcohol trip for 3 days. So that's a good way to end a story where you were driven down a mountain in mad panic. It's the kind of thing that probably should never happen normally, but because you're in altitude, it's easy to make those kind of mistakes. So I mean, that's one of the real dangers, I think, of being at the summit. And they're very careful. They're very health and safety conscious. They're always aware of people having potential altitude sickness issues. So that does make it a lot more difficult as an observer. I think you have to be careful about that kind of thing.
Perfect. All right. There is another question, if you don't mind my asking. What is the meaning of the yellow vests?
Well, Nahid, I think you should answer that question.
Okay, so the yellow vests, you might have noticed, 3 of us are wearing them. So 5 of us went to Hawaii in 2017 to run some observations. It was around about May, end of April. And Tom walked into the Target store in Hilo, and he found these jackets at a cut rate price of $5 a piece. So he bought 5, 1 for each of the members of the trip. And so we've pretty much kept hanging on to them since. We've worn them to a conference in Japan when we happened to go together last year. And we've brought them out again today for this remote observing run. So I hope that explains why we're wearing yellow vests. They've become our de facto uniform in a sense.
Yeah, we're going to have to change it now, though. Now that Emma doesn't have access to one, I think we're going to have to find something new. But they're a memory of a really interesting observation. That was the one that we did just before. We did some observations, then we drove around the mountain, then the volcano exploded and there was a giant earthquake. And we didn't do any more after that. So it's an interesting time. A badge of honor, I guess.
Definitely, yeah. It was a sort of near-death experience in for some of us. So, yeah, think of it as a lucky charm as well, I guess.
Bad luck charm.
Good luck charm.
So there was a question on YouTube about what the stars we were looking at. It was a little while ago. I'm sorry we didn't get back to that. But I thought maybe I could talk a little bit more about that. Star Tracker asked, is the star we're looking at a main sequence star? And Florence said, I think it was mentioned that it was an A0V star. It is a main sequence star. The different stars have different categories based on how hot they are. Our star is a G2 star and it is a V star. V is an expression of the size. So it goes from giant all the way through subdwarf and dwarf. The V represents the 5th category of size, and it is a dwarf star. So our star is a G2V star. It's a dwarf star that is moderately hot. The categories go something like O, B, A, F, G, K, M, something like that. I'm not an expert on stars, but those different stars are heated at different levels and have different atmospheric conditions in them, in the layers. Ours is a G star, so it's relatively hot. It glows in the yellow. As you move up to hotter and hotter stars, they tend to glow more and more blue. The reason why A0V stars are particularly useful is that they're incredibly boring spectrally. They don't have a lot of spectral lines in them at all. The upper atmosphere of the corona of our star has different gases in it, and those start lighting up and giving you spectral signatures inside of the gas of the star itself, which is frustrating if you want to try and use them to get rid of the calibration on your own measurement. You want a boring black body so that you can measure what the outputs are. They're also really interesting because that's the kind of star that Vega is. Vega is a sort of the ultimate calibration star. It's one of the brightest stars in the night sky, and it gives us this perfect measure. And that's the measurement that all absolute magnitudes are taken from. So it's a particularly useful kind of star because it matches really well with Vega, and there's a lot of them about. They're not nearly as common as other kinds of stars, but they're really bright because they're super hot and super powerful. So we have a long list of all of the star A naughts, V stars in the night sky, all the way around the 24 hours of the night sky. And so we're able to pull that list out at any time and find a star nearby our object, either before it or after it, and take calibration data very close to the position of the night sky that we're actually wanting to look through. And so that's ultimately why that's something that we want to look at. If it was not a boring main sequence star, it would have, you know, planets forming around it, or some disk, or it'll be old and exploded and have all sorts of wonderful rich science associated with it, which would make it completely useless for us. We want the dullest, most boring object possible, because we need that so that we can predict as accurately as possible what it is that we're seeing. So it's the boringest main sequence star possible, and we hope that it isn't got secret hidden interests in it, basically.
Awesome, thank you very much for that, Tom. Yeah, I tried to vaguely explain it before, but I don't think I did it in as much justice as you had. Well, we're coming up to the last 10 minutes of, I guess, observations. I'd say observations, we're kind of done at Uranus now, so it's mostly just us. Everyone has to watch. Yeah, I don't know. Do we have another question? No, we do have some very useful mnemonics. Do appreciate those to remember about the stars. I mean, I can discuss about the Royal Astronomical Week. I do appreciate it's a little early. I'm happy to, I don't know, discuss for another 5 minutes on a topic. I do appreciate that both Henrik and Nahid have both gone, and I don't know if that's a hint that I should.
No, I think that would be really good, actually. I think it would be great to talk about the week
Yeah.
that's planned, because there's some really fun stuff coming up.
Well, I'm happy to go into that a little bit. I will apologize, I might not cover everything, and I'm very happy to have anyone add in bits if they remember. But I have been let know by Lucinda that there is the National Astronomy Week. There we are. That is from the 14th to the 22nd of November 2020, which is a Royal Astronomical Society event. That will be running for, you know, the midweek in November, so I would definitely put that down in your calendars. Even if you can only attend for a day or maybe for the whole week, you'll certainly see a lot of interesting stuff with the science that's going around. For the UK, apologies, thank you, Lucinda. Equally, one of the big things is getting ready for the Mars encounter. Tom, do you know more on the Mars encounter discussion?
Well, there's plans to do observations from across the UK, and the hope is that we can get some amateur astronomers to show their observations in a similar way to the way that we have. And to be honest, that's not a difficult thing to do these days. The way that astronomy works in terms of professional astronomy has been, you know, for maybe even 30 years, we've used CCDs attached to the telescope to record data. And, you know, we've been doing remote observations for maybe 20 years. But of course, you know, the natural result of the way that we need to record data means that that's a preferred way to do things. I think, you know, there is a natural inclination, and certainly that's true for me when I'm looking through a telescope, to want to look with my own eyes. And so that has been a way that a lot of amateur astronomers have worked. But what James talked about earlier today is that really there is a category of astronomer now that falls outside of professional and amateur. They're citizen scientists. They're working at a much higher level. And I think that boundary, as we've seen with, you know, a lot of photography more generally, is dropping. It's more and more easy to take really interesting results digitally now with telescopes. It's quite easy to find mounts that let you attach digital cameras or even phones to relatively small telescopes. And so in doing that, you can have a display on your computer screen. So that's not really novel anymore. But of course, what we found in the last few months is a vast season shift in people's appreciation of how easy it is to communicate online. And so it's really a small step between talking in using a video feed like this and changing that to share your screen. It's literally a button at the bottom of the Zoom window. And so I think people haven't really talked about it or thought about it until now, but it's certainly something that is very easily done. And so the plan is for the National Astronomy Week is to have a sequence of observations of Mars using these smaller telescopes around the UK. And they're going to have people sharing their screens and showing what they can see, which is fantastic. It's a really good way of sharing astronomy across the UK and showcasing what people can do with relatively small telescopes or much larger amateur telescopes, and the range of things that you can do as an interested person in the UK.
Awesome. Thank you very much for that, Tom. We're just now having Lucinda share their screen. This is basically the banner for the National Astronomy Week, which we do very much encourage everyone to come along and have a look. And hey, perhaps even if you're interested in doing your own astronomy, get involved with. The links for I have put in the Zoom chat. I can probably copy those through into the YouTube chat if possible. That's at www.astronomyweek.org.uk. Additionally, can be found on Twitter at @NatAstroWeek or on Facebook at Astronomy Week. I don't know if, Lucinda, there's any more that you want me to add on at all. I know I did have quite a very useful comment from John Murrell on YouTube, who mentions that sometime this month all the planets apparently will be visible in the early morning sky from the UK at the same time, which includes Pluto and Ceres. So that'll be a pretty interesting idea for those of you that are very much involved with your telescopes. I'll see if I can get involved. I know, Henrik, you've got a Raspberry Pi set up with a telescope, so that's something to look out for yourself.
It's actually a really fascinating alignment. It's completely chance, of course, but it gives us an opportunity to do some really unique observations, and we have some planned for the coming year. So one of the really unique aspects of this is the alignment between Jupiter and Saturn. So these are two planets that orbit around the night sky completely independent of each other, but once every 25 years or so. And it's to do with the year of Jupiter, which is about 12 years, and every other year, Jupiter year, so every 24, 25 years, they align in the night sky in a way that means that the magnetic field of Jupiter stretches out and is pushed downwind of the sun all the way down to Saturn, and Saturn actually moves into the magnetic field of Jupiter. Normally, Saturn sits by itself, but its own magnetic field shields the planet from the solar wind. But what we found in the past, when Voyager was looking, this happened 50 years ago now, I guess. Is that right? Is it that long ago? My goodness. It must be something like that, 40 years ago or something. Is that the aurora just switched off on Saturn. No one really understands quite why it did, but it tells us something really profound about Saturn's aurora. And so with that alignment between Jupiter and Saturn, we're hoping the same thing will happen again. So we have Hubble Space Telescope observations in October, trying to look for that. And we also have a whole sequence of IRTF observations. I'm not sure if I'm excited or appalled by the observations that we have. We have 26 separate nights of observations, each of which is about 2 hours long. All of them about 4 in the morning UK time. So that's going to be a lot of fun to do. And it basically allows us to do some really interesting science with this sort of chance alignment between the worlds, because what we're hoping is with that sequence of observations, we'll start to see the aurora of Saturn disappear and reappear again as a result of effectively a very similar eclipse as to what we saw today. That instead of an eclipse of sunlight on the disk of the planet, it's an eclipse of the magnetic environment that drives the aurora, and we'll maybe see the aurora switch off and switch on as a result. And in exactly the same way, we will look at the ionosphere and see how the heating of the ionosphere changes as it switches off and on. So we're hoping that that will give us some really interesting information from something that only happens once every 24 years. So that's going to be a lot of fun. And there's all sorts of other obviously interesting observations that you can do as an amateur. The alignment is even better than just these two worlds, of course. It covers pretty much all of the planets are pretty close to each other at the moment. So there's a lot of interesting stuff to see there. But I thought it would be nice to talk about some of the really interesting novel science that we can do as well with something like that. Well, I think we're starting to wind down. I haven't seen any new questions from anyone recently. So that obviously means we've resolved all the questions about astronomy in the world, which is good. This has been an absolute delight to do. Thank you to the RAS for hosting it. I've done a few of these over the years, but none have been nearly as successful as this. We've had fantastic interest from all of you watching, some really great questions, really pointed questions that have really brought the science out. I'm very glad that John Zanecki did not ask a really technical science question. I was quite terrified when John came on saying you had a question. It could have been almost anything that would have thrown me completely. So thank goodness it was about genealogy and not astronomy. It's been great. Thank you to all of the other observers that have been observing with me. Emma and Nahid, you've done a great job fielding questions, and Henrik, you have done a sterling job of making sure we stay on the planet. It's been really good. I know Lucinda is out there. Thank you so much for all of the support that you've done in terms of getting this to work. Presenting Emma Bunce, who did a great job of exploring and explaining the wider science. It's been great fun, and hopefully we could do this again. There's no reason to wait another 200 years, I don't think. Certainly we've done presentations like this before, and that would maybe be a really good idea to do it with the RAS again, because it's worked so effectively. We're hoping that now Leicester has opened up a little bit. Maybe we can have a nice weekend where we're allowed to go outside of our houses. I think that would be a good way to end what was a very successful day of observing. I don't know if any of the rest of you have anything you'd like to say.
And thank you to you, Tom. It's been fantastic. A fun afternoon, fun day, really. Yeah, let's do it again.
Yeah, absolutely.
Yep.
Well, maybe we'll do another 26 at 4 in the morning.
You're on your own.
Yes, I know. Brilliant. All right. Then I guess we will sign off. Thank you all for sticking around. There's still another 30 people on the Zoom chat and another 65 people watching. So it's great that people have stuck around all the way through the bitter end. We're not even looking at anything now. It's just us, and you're still here. So that's wonderful. Make sure to tune in November for all of the fantastic observations that you'll see from the UK exploring Mars. And I'm sure if you look at the links, you can get back to the some of the YouTube channels that we run, and we'll maybe see a future observation either with the RAS or through some other means. Have a lovely weekend, and I guess I should log out now.
Yep. All right. See you.
Thanks, everyone.
Bye-bye.
Thank you. Take care.
Bye-bye.
Bye.